So good morning, everybody. We'll be starting in a minute or so. We have about 80, more than 80, 83 participants at the moment. Okay, let's go ahead and get started. Good morning, everybody, and welcome to the 27th Annual CESM Workshop. I'm Gokhan Danabasoglu. I'm the Chief Scientist for CESM. Before we get going, I just wanted to remind everybody our code of conduct here at NCAR and CESM, and please offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation for the work presented, and please be open to new ideas. And please treat your colleagues with respect. So with that, I would like to pass our virtual floor on to our NCAR director, Everette Joseph. Everette, please go ahead.
Thank you, Gokhan. Can you hear me okay?
Yes, I can hear you fine.
Okay, thanks a lot, Gokhan, and good morning, everyone, and welcome to the 27th CESM Annual Workshop. I first want to thank the CESM team and the workshop organizers and Gokhan for the invitation to open this workshop here this morning, and also for just all the hard work in putting together what really looks like a fantastic and engaging workshop that's really important for our community. First, I want to share just say that I share the strong desire that I know many of you have to include an in-person component to this workshop. And we hope that we were able to return next year as a hybrid event, finally, as we also desire for this meeting. But as we look forward to that return to an in-person meeting, one positive aspect to hosting this again virtually is that, as we have seen from so many of our events, our virtual events, the past couple of years, this virtual format has been a significant draw and has had significant numbers relative to post-pandemic events in terms of participation, on the order of, I would say, almost an order of magnitude in participants increase over previous meetings. And I think that's the same when we look at the registration from this year's workshop. So looking ahead, I hope that we can find pathways to preserve this high community engagement in future workshops. So as we convene this 27th annual workshop, I have to say that the interest in CESM science is as strong as ever, driven in part by the world-class performance of CESM simulations that are really enabled by many community contributions to the system, including from many of you attending the workshop here now. Looking at the agenda, the workshop agenda is impressive, very impressive. In addition to the important report outs from the working groups, the agenda includes critical, and I will say very timely discussion topics on how the CESM community can better engage our science within the context of diversity, equity, and justice, both through more inclusivity, especially the marginalized communities, and by applying CESM science to aid community and local resilience. This exploration of socially relevant, actionable science that we see planned for the workshop is really in strong alignment with the NCAR strategic goals and our mission of science with and for society. The two cross working group sessions that are planned will really be high points of the workshop, and I think we're all looking forward to that. The first of these is on justice and climate change. And this, as you recall, emerged from the last meeting and also from the recent CAB meeting this winter and spring, where there were discussions on environmental justice, and I was really pleased to be a part of some of that. The other cross working group discussion is on actionable science and CESM. And we anticipate very rich and informative discussion on both of these topics, again, which is well aligned with the NCAR strategic plan. In addition to all of this, there will be two plenary talks from invited speakers. The first talk will be delivered by Robert Jackson from Stanford Universities, whose interests include climate change, reducing environmental impact on global warming, global carbon project, and environmental justice. The second presentation, which will be about machine learning for climate modeling, will be jointly given by Galen McKinley from Columbia University and Laure Zanna from NYU. This talk will update us in the work of the recently funded NSF STC, the Center for Learning the Earth with Artificial Intelligence and Physics, or LEAP, which involves really close and very nice collaboration within the CSM community. So I sincerely extend all my thanks to all the speakers, and again, as well, to those who worked incredibly hard to organize this very rich and I think forward-looking workshop agenda. So at NCAR, we continue to be very proud and we continue to invest in CSM. We continue to be very proud of CSM. We continue to invest in its continued development as an institutional priority. And as we continue to serve and enable the needs of the broader research community, unified modeling is a critical component of our latest, is a critical priority for us as reflected in our latest strategic plan. And we are implementing strategies to bolster our capabilities to address societally relevant actionable science. We are also actively developing our capabilities by bridging our modeling systems, enabling large eddy through climate simulations within a unified modeling framework built by NCAR and with and for the, I would say, broader user community. I'd be remiss if I don't acknowledge NSF. We continue to be very grateful for our partnership with the National Science Foundation. They have been critical in supplementing our modeling system development efforts across the board, especially, for example, through CAM7 development. Yet we are particularly indebted to you, our community, and we look forward to working with you in the co-design and the co-development of CSM version 3. So just some final thoughts to get you going here this morning. I hope that you have an exciting and very productive workshop, and look forward to hearing more about how we can work together to understand climate change and vulnerability, really to meet the needs of the nation, our community, and the global society. So Gokhan, thanks again. And I wish you and the community a great and productive workshop, as I know you'll have. So thanks again, Gokhan.
Thank you very much, Everette. Thank you very much. Okay, so I'll share my screen now. Hope everybody can see this properly. So again, good morning. And for those of you who joined us late, I am Gokhan Danabasoglu. I'm the CESM Chief Scientist. And welcome again to the 27th Annual CESM Workshop. Before I give the first presentation, I just wanted to indicate that for this virtual workshop, we are using Zoom webinar. And there is a Q&A feature for the participants. And I'll be monitoring that feature. If you have questions for this morning's speakers, time permitting, I will direct your questions from Q&A, and then they'll be answered by the speakers. So please use Q&A for that purpose. I will not be monitoring chat that can be used for sort of other communication purposes. So with that, I'll start with a brief overview of some of our activities during the past year. And in particular, I'll be focusing on diverse applications of the CESM in line with the NCAR strategic plan and also in line with the CESM strategic plan that's being sort of worked on at the moment. Before doing so, however, I just wanted to say that over the past few years, we have not been producing official CESM releases as the need for such releases has been diminishing continuously over the past few years. That's because our code versions are already readily and publicly available on CESM GitHub side. So anybody who is interested in using our latest and greatest code version can do so by simply downloading the code base from our GitHub site. And also the previous model versions are also readily available from that site. Another announcement concerns an updated, significantly modified data management and data distribution plan for the CESM project. This is also available from our website, and I included the website link here for the new updated document. This document contains guidelines for storage and distribution of CESM datasets, particularly produced by running CESM simulations by various university projects, as well as running simulations at other at non-NCAR facilities, both nationally and internationally. And it is intended to, including cloud-hosted data sets, and it is intended to essentially provide guidelines and sort of what needs to be done for the distribution of these data sets. So if you're interested in, please take a look at this document. So with that now, I would like to start with an update on equilibrium climate sensitivity, or simply referred to as ECS. And this is going to be from a paleoclimate perspective. As many of you know in the audience, CESM is one of the climate models with an equilibrium climate sensitivity of higher than sort of expected. And we are not alone. There are, I believe, order 10 other coupled models which have a high equilibrium climate sensitivity. So our Paleoclimate Working Group members have been looking at this, why that is happening, and in particular from the paleoclimate perspective. And this particular effort is led by Zhang Zhu, and he is an incoming co-chair of the Paleoclimate Working Group. What is shown here on the on the plot on the left side is equilibrium climate sensitivity value is plotted against LGM, last glacial maximum, that's LGM, surface global cooling. And you can see that there are shaded regions here. The ones along in the horizontal are various estimates of IPCC, from IPCC reports of equilibrium climate sensitivity ranges. The vertical shaded region indicates a paleoclimate estimate for the surface cooling during LGM. So the black lines or the black dots here show the CCSM, previous CCSM version, equilibrium climate sensitivity and surface cooling values. And you can see that there's a strong relationship between ECS and surface cooling. And the previous CCSM simulations or CESM simulations were within these sort of shaded regions. CSM2 result is shown here in red, and it's clearly outside the range of both expected range of and estimates of equilibrium, expected range of equilibrium climate sensitivity, as well as it produces too cold surface temperatures during last glacial maximum. So over almost a 1.5 to 2 year period, Zhang Zhu and collaborators looked into various aspects of the model. And at the end, they ended up adjusting two aspects of the cloud microphysics, focusing on the mixed phase clouds. And then they produced a simulation, coupled simulation of the LGM again, and they call it the paleo-calibrated CESM2. This particular version is using 2-degree atmospheric model. And if you, with this paleo-calibrated version, they got the blue dot here. So it is clearly showing lower equilibrium climate sensitivity, and also the surface temperatures or surface cooling is in line with paleoclimate or proxy estimates. Of course, another important aspect of these adjustments is to see what's happening in the historical period. So what is shown on the right side is the temperature anomaly for the historical period from 1850 to 2020 period. The black lines here show observational estimates for the surface temperature evolution. The green line and the shading is for CESM1 large ensemble. The red, orange, and the pink lines show 3 ensemble members of CESM2. The paleo-calibrated version of the model is shown by the thick blue line, and you can see that in its general variability features, we see good agreement between CESM2 and, more importantly, observational estimates. So it's doing essentially a reasonable job of reproducing the historical temperature time series. And these adjustments will be available in future versions of the CESM. And if you want to learn more about it, you can talk to Zhang about these changes. Now, I introduced last time a new CESM2 large ensemble. And this is a partnership with the Institute for Basic Science, Center for Climate Physics in Busan, South Korea. And this is now completed. And the manuscript given here is documenting these ensemble simulations, as well as presenting first results from these simulations. So what these simulations represent, they have 100 ensemble members for the 1850 to 2100 period. For the future scenario parts, they used SSP 370 scenario. And the ensemble spread or ensemble members were obtained using a combination of so-called macro and micro initialization approaches. For those of you who are not familiar with what these are, macro represents essentially different states for each component, for each ensemble member for each component. In contrast, micro initialization approach uses the same state for all component models, except that the ensemble spread is obtained by round-off level perturbations in the restart file for atmospheric potential temperature. For the first 50 members, we used CMIP6 specified biomass burning emissions. For the second 50 member set, we used a smooth version of this biomass burning data set for the 1990-2020 period. I'm not going to go into details of why that was done. And again, you can refer to this particular manuscript to learn more about those details. All of the data sets are available to the community, and you can access these data sets through our CSM2 website. You can either search for CSM2 large ensemble or go to this particular address for this purpose. So a complementary ensemble to the CSM2 large ensemble is our single forcing large ensemble set. This is using smooth biomass burning emissions. And in these simulations, forcings are being kept constant at 1850 levels, except for the ones that we are interested in changing. So in this case, we have 4 ensembles of 15 members each for the 1850 to 2050 period. And we have greenhouse gases only, anthropogenic aerosols only, biomass burning aerosols only, and everything else only simulations. Just to be clear, for example, greenhouse gases only simulation uses time evolving historical greenhouse gas concentrations or emissions, but all the other forcings are kept constant at their 1850s levels. The plot here shows temperature, global mean surface temperature anomaly. It's with respect to this reference period, 1920 to 1940, and the plot is from 1920 all the way to 2050. The shading here represents some kind of measure of ensemble spread in each case. The black line is the Lens 2 simulation, large ensemble, CSM2 large ensemble. The red, the blue, the brown, and the green lines then show greenhouse gas only, anthropogenic aerosol only, biomass burning only, and everything else simulations. Just to give you an idea about the linearity or nonlinearity of the system, you can take a look at this dashed purple line, which is right here, and it is showing the sum of all these individual only experiments. And its difference from the black line here shows the nonlinearity or the degree of linearity of the system. Ayla Simpson is leading the manuscript documenting these simulations as well as some first results. That manuscript is anticipated to be completed sometime at the end of this month or early next month. And as soon as that's submitted, all of the data sets from these simulations will be available to the community. One application area of these large ensemble simulations is shown here, and it is concerning reduced predictability of runoff and drought in the future. This effort is led by Wildfire and his colleagues. So a relationship between the snow water equivalent, or SWE, and runoff can be considered as a measure of predictability of runoff from snow water equivalent. What is shown on the plot here is total runoff plotted against maximum snow water equivalent. The baseline period is shown by the blue color, and baseline in this case is 1940 to 1969, the 30-year period. You can see that, and the thinner lines here show individual ensemble regressions, whereas the thick line is the ensemble mean regression. And you can see a close relationship during this period between total runoff and maximum snow water equivalent. So this essentially says that snow accumulation buffers the effects of stochastic precipitation events on runoff, therefore leading to highly predictable runoff from snow water equivalent. This can be contrasted with what's anticipated to happen in the future, and that's shown by the SSP 370. It's essentially using the CSM2 large ensemble by the orange color. And the individual ensemble regressions are shown by the thin lines, and then the ensemble mean one is shown by the thicker line. You can see a major reduction, a significant reduction in the regression between these two variables. Essentially, the loss of this snow buffer in the future with a warmer climate means that runoff quantity and timing more closely reflect the stochastic character of precipitation. So there is no sort of buffer in between, reducing the correlation between snow water equivalent and runoff. This in turn suggests a reduced predictability of runoff and drought from seasonal snowpack in the future. Skipping now to ocean biogeochemistry, over the past year, we are using in the ocean model or in CESM for ocean biogeochemistry, a marine biogeochemistry library that's referred to as MARBLE. It is capabilities have been expanded over the last year. In particular, it now contains 2 zooplankton groups, micro and mesozooplankton. And this way, this offers improved estimates of food resources for fish and other higher trophic levels. The output from MARBLE can feed into a fish model. In this case, we are collaborating with our university colleagues, and we are using fisheries size and functional type model, Feisty model, for fish modeling purposes. So an important and very practical application is shown here of this system. This is an NSF Convergence Accelerator project. It is referred to as Climate Change Adaptation Tools for California Current Fisheries. In short, the acronym is CATCH, as shown here. This represents a rather large collaboration of all the entities listed here, including the fisheries managers for California or West Coast region. They are included here. This is truly a collaborative convergence accelerator project. We actually interviewed fishermen and fisheries managers to understand what their needs are and what they need to be able to know in order to tell the fishermen where to go and where not to go and when to go, for example, with respect to different fish species. So what is being done at CESM at high resolution at 1/10 of a degree ocean and 1/4 degree atmosphere, including ocean biogeochemistry represented with Marvel, is being used in Earth system predictions. This is up to annual to 2-year timescales. The output from Earth system predictions from the physical side then feeds into fish model predictions using the Feisty model that I introduced that essentially provides information as to where the fish species, certain species will be on the West Coast of the United States, their abundance, their locations, and this feeds into a web-based decision support system tool. Again, this is designed after interviewing fishermen and fisheries managers. And this is supposed to be intended to be a very useful product for the California West Coast fisheries. So other application areas in this example is shown from Polar Climate Working Group, and it concerns the Antarctic. In particular, the focus here is sea ice biological interactions. Starting with the upper left here, they are looking into variability and change of sea ice characteristics. The focus here is polynyas, their formation, their sizes, their locations, and how it's changing, how those are changing from the past to present and into the future. Then those are connected to biological activity, as shown on the upper right here, which shows the phytoplankton concentrations and its seasonal cycle. And they are looking into this concentration in sea ice zones versus inside polynya regions to identify biologically important regions. Lower left panel shows actionable information for marine protected areas. Those are MPAs. The existing ones are shown by the light blue color. The protected areas that are under consideration are shown by gray color. And then the white areas here are the regions. They are in the planning stages. All the 26, I believe there are 26 member nations that they need to agree on that these areas should be also perhaps considered for MPAs. In this case, CESM model is being used to provide ice and biology projections to end users and decision-making bodies. The final example here at lower right is showing the predictability in sea ice and also biology and their links, looking at seasonal to multi-decadal timescales and also changing predictability in a warming climate. These efforts, by the way, are led by, as I said, Polar Climate Model Working Group with Marika Holland, Laura Landrum, Dave Bailey, and Alice de Riviere leading certain aspects of these studies. Sticking with the prediction team, I'll be showing here the predicting impacts of sudden stratospheric warmings, or SSWs, on surface temperature. The panels here show surface temperature anomalies. They are forecast for weeks 3 to 4 after a stratospheric sudden warming event. And in this case, it is after the event on January 5th, 2021. The upper left shows the verification data set. That's a reanalysis product, MERA2. And the other panel shows our predictions, subseasonal predictions from NCAR high-top model version, that's CSM to Wacom 6. And the correlation coefficient is rather good. We were quite pleased with that number. So I'm going to show you now additional plots. These are like postage stamp plots from other centers. And you can take my word for it. A CSM2 Wacom 6 high-top version indeed shows the highest skill among the sub-X models. These are the subseasonal models listed here. So it's quite successful. Moreover, this study was led by Nick Davis, and they found that stratospheric southern warmings have a limited impact in this variability. They determined that thing by using sort of randomized, shuffled initial conditions. They indeed found that the tropospheric circulation and coupling between the troposphere and stratosphere were dominant contributors to this variability. Another example of prediction simulations is provided here, and it's looking into impacts of Australian wildfire fires that occurred during 2019-2020 period, and it's looking into its impacts on Nino 3.4 predictions. What is shown here is the temperature anomalies for this region, 3.4 region, as a function of a 2-year period starting from August of 2019 all the way to half year of 2021. SMILE experiments, and I'm sure you'll hear more about those stand for seasonal to multi-year large ensemble, do not include the impacts of Australian wildfire emissions, and they show a relatively weak La Nina condition in 2020 to 2021 with a magnitude of about half degree C. But when the impacts of Australian fire emissions are included, you get the red line here. You can see that the observational based estimate is shown here by the blue region here. And in DJF, the Hadley Center based estimate is actually in quite, well, I should say the model prediction is in quite good agreement with the observational estimate shown here. So this is actually indicating the importance of including these emissions in these simulations. And I believe John Fasuli is going to present more about this on Thursday's Earth System Prediction Working Group meeting. Switching gears now to high resolution whole atmosphere modeling, there is a spectral element, dynamical core version, modified to allow for extension into the upper atmosphere, referred to as SE Wacom X version. The simulations with this model use 1/4 degree horizontal resolution and 273 vertical levels. Resolved gravity waves agree with the middle upper atmosphere observations, and resolved gravity wave forcing leads to better representation of the circulation and composition. The plots on the right, in the upper panel, plots on the right show the simulated perturbations in the ionosphere electron density. The top is from the model, the bottom is from the observations. And you can see that the SE Wacom X reproduces small-scale concentric wave fluctuations in the ionosphere that are consistent with observations. And these are also important for understanding space weather. Something about atmospheric chemistry. These are simulations, planned simulations or ongoing simulations with MUSICA. MUSICA stands for Multi-Scale Infrastructure for Chemistry and Aerosols. I'm showing 2 examples here, and they both make use of the spectral element dynamical core and it is variable resolution feature. The top part is looking into regional refinement to study Asian summer monsoon. And in the region of interest, the model resolution is 30 kilometers. It gradually coarsens to order 1 degree resolution. And this region of interest covers clearly deep convection regions. The second example shown in the bottom panel is for studying air quality over India. And in this case, the model resolution over this region is 14 kilometers, and it gradually again coarsens to nominal 1 degree resolution. This study is looking at long-range transport effects on regional air pollution, as well as regional scale chemistry and dynamic treatment effects on global modeling results. Again, all of these are with our university colleagues. A few things about paleo ice sheet simulations. CESM and Community Ice Sheet Model, that's CISM, are being applied to the North American ice sheet complex. And this is for the last glacial maximum, roughly 21,000 years ago. The plot here shows the surface velocity or ice streams from this simulation. And CESM generates ice streams in good agreement with the paleoclimate record. But more importantly, I think what needs to be stressed here is that ice streams are controlled by different mechanisms. So the pink line, the regions that are indicated by pink lines here are controlled by steep bed topography. The dotted cyan line regions, in those regions, ice streams are controlled by inclusion of hydrology, subglacial hydrology. And finally, in the green regions, it is controlled by bed strength or weak basal till. Although these simulations at the moment use an offline coupling, CESM and CESM are now enabled for multiple coupled ice sheets, including Antarctica, and the efforts of the CESM software engineering group have been really instrumental here. In particular, Marianne Wertenstein and Bill Sachs are the primary people involved with this effort. And finally, just an example for simulating transitions into ice ages. Exactly 10 years ago, Marcus Jacob led one of the very first coupled studies using CCSM4. And in this case, this was one of the, I believe, to my knowledge, one of the first coupled systems that simulated perennial snow cover in glacial inception sites due to improved orography representation. At that time, he couldn't use an ice sheet model because CCSM did not have one. Fast forward 10 years to today, another Marcus, with slightly different spelling of the first name, led an effort where CESM2 was the first ever CMIP class Earth system model with an interactive ice sheet model, in this case CESM2, simulating the Northern Hemisphere glacial inception. And it is shown here on this plot in terms of ice sheet thickness, and these are the regions of glacial inception. With that now, I would like to come to sort of where we are going with the model. I've provided you examples of diverse applications of CESM2, its simulations and its data sets. And on the side, well, not on the side, in parallel with that effort, we have been busy towards creating a new model version and preliminary coupled simulations that use the developmental versions of the component models have actually begun. And these include MUM6 for the ocean component, our new ocean model, CI6, and I called it not CAM7 because it's not there yet, CAM6 Plus with 58 vertical levels. We have started with our nominal workhorse version of the model, nominal 1 degree horizontal resolution, in which the ocean component has 2/3 degree horizontal resolution. This has been a substantial effort led by, in particular, Gustavo Marquez and Cecil Henney, but plus many other folks from development working groups. There have been quite a few and continues to be many technical and scientific challenges, particularly associated with realistic surface boundary conditions of the ocean model. We need to, for example, in addition to regular conservation properties, we need to be mindful of enthalpy conservation issues. Of course, this new model opens up new research opportunities and new science opportunities, for example, related to sea level changes, and of course, better represents near surface processes. So with that, and then this is showing from one of our preliminary simulations, 100-year time series from a coupled simulation of the global potential temperature horizontal vertical profiles as horizontal mean. This is obtained with the FV dynamical version of the atmospheric model. Finally, I just wanted to touch on provide a quick update. As you know, if you've been attending the CESM workshop over the last many years, you know that we have been having our meetings at NCAR, and that was since 2017, and that was partially due to the collapse of the roof of our meeting place at Breckenridge. That was the 10-mile room, and this is the newspaper sort of clipping that collapse occurred on January 11th of 2017. So it looks like, based on the pictures that I received from Ayla yesterday evening, that particular room has been quite nicely renovated. So perhaps in the future, we may consider going back to our old tradition, having these meetings at Breckenridge. And with that, I'll stop. And if you have any questions, I'll try to take them within the next 1 or 2 minutes before I introduce the recipients of the CESM Awards. And thank you very much for your attention. Doesn't look like I have any questions. I should mention that many of the highlights that I presented here will be discussed in detail during the working group meetings as well. So you can ask your questions during that time. Okay. I'll just wait a minute. Okay, so we'll move on, I guess. So this is the fun part of this job. I get to present the recipients of this year's CESM Awards. And I'll start with the CESM Distinguished Achievement Award. This year's winner, or this year's, I should say, recipient, is Steve Yeager. Congratulations, Steve. Steve was nominated for this award for leading many aspects of CESM's Earth system prediction efforts. He led the CSM1 decadal prediction large ensemble, as well as the more recent CSM2 seasonal to multi-year large ensemble simulations. And those are the ones that I introduced earlier. They are referred to as SMILE simulations. And these and other related efforts are instrumental in putting CESM at the forefront of intraannual to decadal Earth system predictions worldwide. And Steve's efforts have been instrumental in this, in getting CESM recognized as a major contributor to multi-annual to decadal predictions. Steve is also serving as one of the co-chairs of the Earth System Prediction Working Group. So as everybody knows, well, I mean, the award is there, and I'm hoping to present the award in person to Steve sometime during this week, since now we are able to be at NCAR. In any case, so without further ado, floor is yours, Steve. And again, congratulations. I'll stop sharing my screen and you can share your screen, Steve.
Okay, thank you very much, Gokhan, and I want to thank the committee for this award. I was really surprised and delighted to hear that I would get it. It's truly an honor. And I'm grateful for the spotlight that this award shines on prediction research using CESM and the opportunity it gives me to present to this plenary some of our recent work in this area. The title of my talk is A Decade of Decadal Prediction Research, Advancing CESM Near-Term Prediction Capabilities in the Face of Drift, Shock, and Noise. I started doing decadal prediction research about 10 years ago. And so I thought I'd use this opportunity to present a kind of retrospective tour of some of the challenges faced and progress made during that time. And of course, I can't cover everything in a 30-minute talk. And since this is an award presentation, I thought it would be fitting to convey a sense of what my specific contributions have been on this topic. Decadal prediction is a non-trivial endeavor. It requires group effort to pull off. And so from the start, I'd like to acknowledge all of the colleagues who have contributed in one way or another to the results that I'll be sharing with you today. In the interest of time, I won't list all their names, but I hope these people will be familiar to many in the audience, and you'll see many of their names in the slides to come. I do want to specifically acknowledge Gokhan's contribution. I've worked with him for many years on the decadal prediction efforts, and also Jerry and Joe, who have been stalwarts of initialized prediction research using the CESM model. And finally, I want to specifically call out Ping Chang, who's become a key outside collaborator on decadal prediction research. I wanted to start this talk with the basic premise that we're interested in advancing understanding of and capacity to predict regional environmental change on climate timescales. And so it's useful to conceptually split the drivers of regional change into those associated with forced variability and change versus those associated with internal variability that's intrinsic to the climate system. Now, this schematic isn't perfect because we can envision that there's coupled interactions between forced drivers and internal drivers. For example, a volcanic eruption could energize specific modes of internal variability that color how you interpret regional environmental change. This conceptual split has proved to be scientifically powerful for advancing our understanding, and in particular, SMILES, which are single model initial condition large ensembles, such as the CESM1 and CESM2 large ensemble, are specifically designed to decompose regional change variance into these two contributions. The ensemble mean, or the signal from a large ensemble, gives you a measure of the forced variability and change, while the ensemble spread, or the noise, gives you a measure of the internal variability. In the context of SMILE studies, the internal variability is frequently referred to as irreducible uncertainty. But the point of initialized decadal prediction research is to further reduce this irreducible uncertainty. And so initialized decadal prediction ensembles are quite analogous to SMILE experiments, but they're initialized from observed states. And so the ensemble mean signal from an initialized decadal prediction system gives you a quantification of the forced variability and change in addition to the predictable component of internal variability. The latter, on decadal timescales, is predominantly associated with slow oceanic modes of variability, as exemplified here by ENSO or AMOC variability. And the ensemble spread, or the noise, in a decadal prediction system reflects the unpredictable internal variability. And ideally, this should better represent the true irreducible uncertainty associated with a chaotic system like our climate. In decadal prediction, it's relevant to ask the question, which matters more for Earth system prediction, internal variability or forced climate change? And the answer depends on spatiotemporal scale. And this cartoon helps illustrate that point, showing the relative influence of internal versus forced components of variability as a function of time scale on the x-axis and spatial scale on the y-axis. Now, the lower left represents the regime where internal variability dominates. This is the weather regime. Weather forecasts don't need to consider forced climate change. And conversely, at the upper right of this diagram, we're looking at large-scale change over centuries, where force drivers dominate the variability. Decadal prediction is concerned with this gray area in between. We're concerned with decadal variability on regional timescales, and so both internal and force variability is likely to be important. And recent work in decadal prediction has validated that hypothesis. So accurate decadal prediction of regional change requires constraining the internal component of variability in climate models in addition to the force component. And as in numerical weather prediction, constraining internal variability can be accomplished through initialization. Now, the field of decadal climate prediction really had its genesis in the 2000s. This is a smattering of some papers from that time that give a sense of the state of the science. At that time, it's not meant to be comprehensive. But around that time, people were doing perfect model predictability experiments, like the one by Griffiths and Bryan, and then the one by Mail et al., that were starting to highlight the potential to do decadal predictions in the Atlantic and Pacific sectors. And then in 2007 and 2008, a pair of seminal papers came out by Smith et al. And McKinley et al. That were the first to implement these ideas in practice to test the viability of real-world initialized decadal prediction. And then in 2009, Jerry led a paper that included many other well-known figures in the decadal prediction field, including Gokhan, that laid out the scientific rationale for a decadal prediction protocol for CMIP5. And this is what really got the ball rolling internationally as far as coordinated efforts to explore this decadal prediction space. I'm going to be talking about decadal prediction results, and so I want to explain what decadal prediction experiment design looks like. We start with initialized coupled model hindcasts that are initialized from some reconstruction of the observed state of the Earth system, going back in time to as far back as the mid-1950s. The hard part in decadal prediction is coming up with this black curve because ocean variability is considered to be the dominant source of memory for these systems, and the ocean is very poorly observed prior to 2000. So techniques have to be generated to allow one to reconstruct the ocean state going decades back in time. Once you have that state, you initialize hindcasts and you repeat that step as often as possible to sample different phases of the decadal variability that's been observed in the real world. And then you validate your hindcasts. You test how well those hindcasts can reproduce the variability from the observations. To the extent that they are skillful, that gives you more or less confidence in the credibility of any future forecasts that you make with the system. So our first efforts at initialized decadal prediction were around 2012. And this was my first paper on decadal prediction in Journal of Climate. We were using a 10-member system with the CCSM4 model that was initialized every 5 years from 1961 to 2006 for a total of 10 start dates. And our method of initialization was to use a forced ocean sea ice simulation, or FOSSI, that was constrained by historical atmospheric observations. Now, by this time, FOSSI simulations had become a standard tool used in ocean modeling, and in particular in the oceanography section of CGD, for exploring mechanisms of ocean variability and for vetting ocean model developments. So we leveraged that FOSSI simulation and initialized 10-member hindcasts from FOSSI. And this is just the result we got for subpolar North Atlantic heat content. The black curve is FOSSI, and the gray curves are the ensemble mean of these different decadal prediction hindcasts. Around this time, there was interest in exploring whether this mid-90s abrupt warming of the subpolar gyre was predictable in advance, and that's what we were testing with this new system. And what we found, perhaps not surprisingly, is that when we initialized from FOSSI, the coupled model shows a large drift away from the conditions that are essentially foreign to its model attractor. And the drift variance, as you can see, is quite a bit larger than the variance that we're trying to predict. But what we learned is that we can remove that drift if we have enough samples. So if we transform the decadal prediction results into anomalies from lead time dependent climatology, there is predictable signal hidden in that large drift that can be teased out. And in fact, we had quite high skill at predicting this mid-90s regime shift in the subpolar North Atlantic. So this was a first demonstration of decadal prediction skill in the CCSM model, initialized from observation-based states. And this paper also showed with a heat budget analysis that the skill in this region derives from predictable ocean heat convergence, which was something that had been hypothesized but not shown at that point. Now, initializing from FOSSI fails to leverage all of the information that's available from ocean observations. And so Alicia Karspek led this nice study in 2014 that explored the sensitivity to ocean initialization methodology. What she did was use the DART DA system to generate a set of snapshot ocean conditions going back in time to generate a new set of hindcasts that were initialized from a data assimilation state. And this is a result from her paper, again, focusing on subpolar North Atlantic SST. Here's again this mid-90s regime shift. The gray box, or the green boxes show the hindcast or FOSSI initialized prediction results, and the blue boxes show the DA initialized prediction results. And one of the takeaways from this study was that there wasn't a clean or clear message that DA improved initialization over FOSSI initialization. And in particular, in the primary region where initialization impacts are large, in the subpolar North Atlantic, the FOSSI initialization in green outperformed the DA initialization system. So this was one of the studies that kind of steered us or kept us on the track of FOSSI initialization for decadal prediction hindcasts, in part because FOSSI is so much easier and simpler than performing ensemble Kalman filter data assimilation going decades back in time. One of the other things that Alicia showed in her paper was that we had a problem in the Pacific. This is another time series focused on the equatorial Pacific region, looking at SST in the FOSSI initialized hindcasts. What we found was quite severe warm bias in the early start dates and a cold bias in the later start dates that yielded an overall negative skill in this region. So we knew we had problems in the Pacific. And then Haiyan Tang led a study in 2017 issue of Clyde Exchanges that shed some light on this. Her analysis showed that there appeared to be an initialization shock at work in the Pacific in our decadal hindcast experiments, such that early start years, those in the 60s and 70s, tended to induce El Nino conditions in the early years of the hindcasts, and later start years tended to induce La Nina conditions. And the initialization shock interpretation was an assumption that the initial states that we're using were somehow out of balance. And so there were these short-term transient effects that corrupted our prediction scale on short time scales, and that tended to ameliorate at longer lead times. We didn't know what the reason was for this initialization shock, but it was later traced to a correctable bias in zonal tropical SST gradients in the FOSSI simulation that we were using to initialize. But we did have good skill in the North Atlantic, so we forged ahead with this study that looked at our ability to predict Arctic sea ice using this CCSM4 decadal prediction system. This used an expansion of the CCSM4 DP set that was rebranded as the CESM1 DP system. We expanded the start dates from 10 to 60. So in this system, we were initializing every year between 1955 and 2014. And it's important to note that our decadal prediction efforts were going in parallel to work that was examining North Atlantic mechanisms in the FOSSI that we're using to initialize. And this two-pronged approach was quite useful in giving us insight into the oceanic mechanisms at work that expected to be underlying skillful predictions in the North Atlantic sector. So what we argued in this paper was that predictable decadal changes in North Atlantic ocean thermohaline circulation, strength, and northward heat transport that were related to low-frequency NAO buoyancy forcing translates into predictable changes in the rate of Arctic winter sea ice decline. And that's what's shown in this plot on the right that shows 10-year winter JFM sea ice extent trends as a function of time for the whole Arctic and for the Atlantic Arctic sector. The black curve here is our trends from the FOSSI simulation that we're initializing from. The red curve is the ensemble mean from our prediction hindcasts. And the blue curve is the limited observational verification that we can do from satellite. And we argued that the rapid sea ice decline in the 1990s that was observed, maximizing in this time period from 1997 to 2007, was associated with thermohaline circulation spin-up, and that ongoing and future thermohaline circulation decline associated with weak NAO forcing after 1997 is likely to result in a slowdown in the rate of Arctic winter sea ice loss. And this prediction was already somewhat confirmed by the observations available at the time. This last blue dot here is the 10-year trend from 2005 to 2015. That was the last observational data point available at the time we submitted this paper. And that last trend was already above the zero line, indicating decadal sea ice growth in the Atlantic sector in wintertime. So I've been at this prediction work long enough that some of these forecasts are now starting to verify, which is a bit dangerous. And so how has this forecast stood the test of time? On the left here, I'm showing an updated version of the blue curve that we published in our 2015 paper. The circle is the final data point that we included in the paper. And this shows what has happened since. In the Atlantic sector, the trends did go back to negative territory, indicating sea ice decline over 10-year timescales. This decline is somewhat predicted in our forecast from 2015. And then we see in more recent years a return to very neutral conditions. And the last two decadal trends that we have from the observations indicate very neutral 10-year trends that are not inconsistent with the ensemble spread from our prediction system. So I think overall our prediction that Arctic sea ice trends are unlikely to return to late 90s values has stood up quite well. Now, in the 2010s, the UK Met Office came out with a series of papers that argued that seasonal to decadal prediction systems exhibit deficient signal variability, too much noise. This work was primarily focused on, in the context of seasonal predictions of winter NAO. It started with this Scaife et al. Paper, but then was expanded to decadal timescales in this Eade et al. Paper, where they showed that this issue was not limited to the North Atlantic NAO field, but was much more predominant in these systems. And then in 2018, Scaife and Smith sort of coined the signal to noise paradox as a significant issue facing not only the initialized prediction world, but also the coupled climate modeling world more generally. And I'd like to talk about the signal to noise paradox. So this is my one slide primer on this issue. The inherent predictability of Earth's climate, which we might quantify as the fraction of predictable variability over the total variability, is not known. We'd sorely love to know what this fraction is for different fields, for different timescales, but all we have available is the denominator, the total variance from observations. We have no way of knowing what the predictable or potentially predictable variance is. However, initialized forecasts verified against observations do provide a lower bound estimate of real-world predictability limits. So the ACC, the anomaly correlation coefficient that you can achieve with a prediction system, implies that the real-world predictability is at least as high as that ACC value, if not higher. The inherent predictability of model climate can be quantified from initialized forecast ensembles. We have all this information available, the total variability, as well as the variability of the ensemble mean of an ensemble forecast system. And what the UK Met Office pointed out is that large ensemble climate forecast systems show that model world predictability is often significantly lower than real world predictability. And this is commonly quantified in terms of the ratio of predictable components. The ACC that can be achieved with a prediction system divided by the inherent predictability of that prediction system, the ACC over the signal to total fraction. And the signal to noise paradox is the regime when RPC is greater than 1. This implies that the model predicts the real world better than it predicts itself. And what this implies is that large ensembles are needed to achieve skill, to beat down excessive model noise. And it also implies that there's significant potential to improve or extend predictions by improving coupled model fidelity. So the signal to noise paradox was in the air when we set out to produce a large ensemble prediction system. And that was documented in this BAM's overview paper in 2018, where we introduced the 40-member CESM 1-1 decadal prediction large ensemble. This was a fresh start. We were now initializing every November 1st over this 64-year time period. And this was in line with the new CMIP6 protocol that had been developed by then. This was a huge experiment, 26,000 simulation years that was made possible by a CISL Accelerated Scientific Discovery Award on Cheyenne. The Pacific shock that I mentioned before, we were able to ameliorate through improved Fosse initialization. I don't have time to explain that, but this overview paper does discuss that improvement. And what we found or showed in this paper is that we're able to directly compare this decadal prediction large ensemble to the parallel uninitialized CESM 1 large ensemble to reveal widespread skill improvement associated with initialization. And I'm just going to show one plot to give an example of that. This shows summertime precipitation over the African Sahel region. On the top is the raw time series from observations from the DPLE over forecast years 3 through 7 in red, and a 40-member large ensemble. And you can see that from the raw time series, the amplitudes of variability from the model simulations is quite a bit lower than observed. But if we renormalize those curves, then we immediately see that the initialized decadal prediction large ensemble in red does a much better job of predicting decadal variations in summertime precipitation over the Sahel, with a level of skill that might even be actionable. If we had DPLE back in the 1980s, we could have predicted the drought conditions that became prevalent in the African Sahel in the 1980s. The large ensemble we showed generally improves skill and also enhances confidence in differentiating DPLE from LE. This was one of the first DP systems to include ocean biogeochemistry. And so it spawned a flurry of papers that explored the predictability of ocean BGC and carbon cycle and ocean biosphere. And it also showed evidence of this signal to noise paradox. So for example, for the Sahel precipitation, the RPC value is 2, suggesting that the model is not achieving the predictability internally that is there in the real world. Now, the DPLE showed remarkably high and long-lasting ocean prediction skill in the subpolar North Atlantic region, and that made DPLE a good system for exploring the mechanisms underlying Atlantic skill. And I'm just showing that in this plot here that again shows subpolar North Atlantic heat content as a function of historical year. These are these are annual averages. You can just compare the red line with the black line, which compares DPLE to FOSSI. And these different panels show different lead times from lead year 1 all the way out to 10 on the bottom right. And it's quite evident that our skill, our high skill, and the high skill at getting the amplitude of anomalies persists even out to lead year 10 in this system. The conventional explanation for this skill is AMOC, quite vaguely. And so there was a need to delve a bit deeper to understand what exactly was explaining the high skill in DPLE. These plots show the DPLE skill at predicting AMOC as simulated by FOSSI, what's the simulation that's used for initialization. And what you can see is that AMOC skill actually declines quite rapidly after a few years. And by this mid-pentad, there's very little skill at predicting AMOC strength at subpolar latitudes in the Atlantic. So AMOC by itself did not seem to be a good explanation for DPLE skill in the North Atlantic. And what I showed in this paper is that AMOC in sigma space is a much more relevant quantity for understanding decadal predictability in the North Atlantic. The time-lagged coupling of AMOC lower and upper limbs as a key decadal predictability mechanism is something that wasn't appreciated, but was demonstrated in this paper. And I also argued that the core of ocean memory resides in deep, below 2 kilometer Labrador seawater thickness anomalies. This also had not been widely appreciated. An important implication of that is that the lack of deep ocean observation poses a real challenge for decadal prediction initialization. Now, DPLE spawned a whole host of studies that I don't have time to list, but I did want to highlight this study that came out from DPLE. It used 40-member DPLE to be the first demonstration of skillful decadal prediction of winter NAO and blocking frequency. The time series are shown here on the right. This is high latitude winter blocking in this large region. Observations in blue and DPLE in red, and you can see by eye the high correlation skill there. And conversely, here's the time series for winter NAO. So this system was able to demonstrate skillful decadal prediction of these atmospheric quantities, which are important for extremes over Britain and Europe. And there was some evidence that the weak decadal signal was related to strong decadal ocean signals. the skill was perceptible, but doesn't saturate with 40-member ensemble. So we were really at the limits of extracting skill from the system with the 40-member ensemble we had and with the large spatial and temporal averaging that we were doing. I want to end with sort of the new chapter in decadal prediction research made possible by the International Laboratory for High Resolution Earth System Prediction, or IHESP. IHESP has recently completed a 10-member set of DP hindcasts using the high-resolution CESM 1.3. And this system can be directly compared to DPLE to isolate the impact of model horizontal resolution on prediction system performance. The overall setup of HRDP is very similar to DPLE. There's some differences in initialization method, but the real difference is in the horizontal resolution of the ocean and atmosphere components. 0.1 coupled to 0.25 atmosphere in HRDP compared to 1 degree components in the DPLE system. And what this comparison reveals is that we've got significantly improved skill for quantities like wintertime sea level pressure. These are shown in the skill maps here. Top show anomaly correlation coefficient, the bottom show mean square skill score, which is a measure of getting the amplitude of anomalies right. First of all, you can see that 40-member DPLE is better than 10-member. And we can directly HRDP 10-member to the DPLE 10-member and find that we get skill improvement over about a third of the globe in both of these measures, which far exceeds regions of skill degradation. We can also see by eye that
I think we lost Steve. Steve, we can't hear you at all. And there's a static noise. Oh, you dropped out. Okay, well, it was almost time, I guess, 9:47. Yeah, Steve unfortunately left the meeting, so I think his internet connection dropped. He's back. Can you hear us, Steve?
yes, I can. Can you hear me?
Yeah, I mean, your sound was, you're almost done, I think, right? So please
Yeah,
go ahead
if
and
I could
finish
have
it.
another minute to finish, that would be great.
Yeah, go ahead, please.
All right, great. So this was the final result I wanted to show. It's a histogram plot that compares the skill metrics in HRDP to DPLE. And what it shows is the relative occurrence of paired ACC and RPC values over the globe for DJFM SLP. It shows several things. It shows that HRDP
We lost you again, Steve.
is overall more skillful than either types than are found in DPLE.
Steve, we are losing you on and off. Okay, I think we should move on. It's 9:50. Okay, so I'll share my screen now. Okay, so this year we have two recipients of the CESM Graduate Student Award, and I'll go and introduce them in alphabetical order. So our first recipient of the award is Abigail Bodner. She graduated in June 2021, last year, from Brown University, and she is a postdoctoral researcher at Quant Institute at NYU. Abigail, congratulations. She primarily worked on frontogenesis with large eddy simulations. So she reformulated this work, her frontogenesis work, into a prediction for the frontal arrest scale based on the turbulent thermal wind balance. She has also worked together with a team to implement this scaling within the CESM as a new aspect of the mixed layer eddy restratification scaling. And her scaling is based on stronger theoretical footing than the previous scalings. So with that, I would like to congratulate Abigail again, and floor is yours. So you have, I believe, 15 minutes with hopefully five minutes for Q&A. Thank you.
Thank you very much. I'm really honored to receive this award. Let me go ahead and share my screen.
Yes, I disconnected. So.
All right, does that work?
Looks good.
Yeah, great. All right, so yeah, thank you for the introduction, and thank you so much for this award. I'm going to be talking about kind of the final aspect that came out of my PhD work with Baylor Fox Kemper in collaboration with Leah Johnson, Luke Van Rokel, Jim McWilliams, Peter Sullivan, Paul Hall, and G.I. Dong. Yeah, as Gokhan mentioned, I'm going to be talking about modifying the mixed layer eddy parameterization with a focus on frontogenesis arrest by boundary layer turbulence. So just for some motivation, because a lot of those terms might not be familiar to everyone, the parameterization I worked on is specifically tailored to capture the main effects of mesoscale fronts, which are upper ocean features such as seen in these images here. So here's a front in the Gulf of Mexico where you tend to get these very sharp fronts given from the Mississippi River, which is bringing fresh, light water pouring into the deep and dense, saltier Gulf waters, and you get these very sharp interfaces of these two bodies of fluids. Fronts are also important for transporting tracers. So here we've got oil from the Deep Horizon Gulf spill, oil spill, and just important to note for my talk specifically today, notice the large range of frontal width across this front between these two images over here, and how wide these fronts are really important for how stable they become, which will result in their mixing properties in the upper ocean, which is really the effect that we're trying to capture with this parameterization. Right down here, we've got sea ice that's being transferred also along this current along the front, being squeezed in by these larger mesoscale eddies, which are one mechanism to generate strong fronts, frontogenesis. Another one is by boundary layer turbulence, which I'm going to be talking about today. If I were to take a cross section across this front, we would see that fronts are also associated with a lot of vertical transport due to an overturning circulation and turbulence, when there are a lot of fisheries that tend to feed along fronts due to the nutrients that come up from the deeper ocean interior. So there's also a biogeochemical component in there that's essential for the climate system. So as I mentioned, the submesoscale fronts that I'm discussing today are an ocean mixed layer property. So the ocean mixed layer is the uppermost layer in the ocean. It's in direct contact with the atmosphere. So it's affected by winds and waves, heating and cooling. And all of these contribute to how well mixed and how turbulent this upper layer tends to be. And that really is significant to control atmosphere-ocean interactions, because it will determine what's being transmitted between the atmosphere to the ocean interior and vice versa. So there's a lot of effort to accurately represent the processes in the upper ocean, especially for climate simulations. However, many of these processes tend to be too small, fast, and complex, and become unresolved in GCM, such as CSM, and that's why there's so much effort to try to parameterize them. So specifically for the climate system, a lot of the important fluxes that we tend to capture from these processes are the vertical fluxes in the mixed layer. where they're dominated by submesoscales and boundary layer turbulence. So boundary layer turbulence adds turbulence and mixes the mixed layer, so it makes it more mixed and thus deeper. Whereas submesoscales or mixed layer eddies tend to re-stratify and shoal the mixed layer. So it's this interplay between these two processes that is what's going to set the effective mixed layer depth, which has really been found to be an important control parameter on the climate system as a whole. So I'm just going to review a little bit about the previous mixed layer eddy parameterization. So this was developed by Fox-Kemper et al. In several papers. What you can see over here on the top right, this is a submesoscale front, similar to the images we saw before. This front is characterized by a frontal width of LF. It lives in the mixed layer with a depth of H. And due to the available potential energy that exists by the vertical isopycnals of this front, there are instabilities that form along it, known as mixed layer eddies. And these instabilities are essentially mixing and stirring the waters in the mixed layer and thus re-stratifying and overturning the front. So they're taking these vertical isopycnals and they're turning them into horizontal ones. And this process can be captured by an overturning stream function. So this is an eddy stream function that's capturing the effect of these mixed layer eddies formed along the front. So of a special importance to the CSM group, this is parameterized by a whole bunch of variables that we can get from the climate model. And specifically, it also depends on what we would expect a typical frontal width to be, LF. In some models, such as POP, this was originally set to be the deformation radius of the mixed layer. In other models, such as MOM, for instance, it was set to be a constant, set anywhere between 500 meters and 2 kilometers. And you can see just even by this relationship of it being in the denominator, really how sharp these fronts are will determine how strong this restratification will be. And it will determine what is this balance between the mixing and the restratification in the mixed layer. However, there have been many studies that have come out since this original 2011 paper that have suggested that this original formulation for frontal width is not doing a really good job of capturing what we know should occur in the mixed layer and how fronts interact with boundary layer turbulence. So what I was seeking out in my PhD, and specifically in this last project, was to see, can we come up with a better scaling for frontal width to capture the physics of the problem where we know it should be determined by boundary layer turbulence rather than the background state. So in several other studies that I did previously, as well as others by Jim McWilliam and Peter Sullivan, there are really two separate flux processes that are helping to determine the frontal width and specifically the formation and diffusion of the front. So frontogenesis is the generation of the front. It's how the front gets stronger and becomes this sharp interface between the two bodies of fluid. And this is found to be made possible by vertical turbulent fluxes, whereas frontal arrest, which is the process where the front halts at a certain width, is found to be made possible by horizontal turbulent fluxes. So it's this vertical versus horizontal turbulence in the mixed layer that is interacting with the front as it's forming and diffusing, which is setting the effective width. So it's this interaction that we wanted to capture in this new scaling. So we focused on the turbulent thermal wind balance. For the submesoscales, the reason they're so tricky to study is because there are so many balances that are occurring at first order, and it's really hard to neglect any in the theoretical understanding of submesoscales. So turbulent thermal wind balance is one way to understand a three-way balance between buoyancy gradient, the vertical shear, and the vertical eddy viscosity. So it's essentially a three-way balance that incorporates the standard thermal wind balance together with the Ekman balance. And we followed through with this, the turbulent thermal wind balance, insisting that all the scaling laws remain consistent between boundary layer turbulence and submesoscales. And with that, we were able to come up with a new scaling for frontal width that now depends on turbulent quantities, such as the turbulent friction velocity, the turbulent convection velocity, the boundary layer depth, the Coriolis parameter, and a constant, which we found to be proportional to the Richardson number of a quarter, which is representative of horizontal shear instability. So essentially what the scaling is doing is it is the scaling that is allowing the turbulent thermal wind balance to hold. It is also representative of both frontogenesis made possible by vertical fluxes, as well as the arrest by horizontal processes. I'll also note that all of these quantities are already calculated online in the turbulent boundary layer turbulent schemes, such as KBP or EPBL. So it does not add any additional cost to the model to replace the old scaling with the new one. So great. The theory, it was really nice to follow through, but does this actually make sense? Does this agree with any simulations or observations aside from the theory? So we set out to really prove to ourselves as a proof of concept or a sanity check to see if we can come up with an argument why the scaling makes sense. So we tested in large eddy simulations. We had in our lab, just happened to have on site a whole bunch of frontogenesis submesoscale simulations together with different flavors of boundary layer turbulence. So they varied the U star and double U star parameters. And we measured all these different frontal widths together with the boundary layer turbulence that sets them. And when we compared the predicted versus measured frontal width, we found that they are roughly on the same order. Now, these were not designed specifically for this scaling, but rather this relationship came out from examining the simulations themselves. We also turned to observations using the general ocean turbulence model, where we focused on different observational campaigns that corresponded to the forcings that were used for the general ocean turbulence model. So this is in the Bay of Bengal during the June campaign, California current system, and the Porcupine Abyssal Plain during 2 times of year. And in all of these observational campaigns, submesoscales were found to be very important. And when we think of submesoscales, also we think on the order of roughly 1 kilometer, which is what the distribution of our new scaling gave when we incorporated the forcings from these campaigns. So this was also very reassuring to see that the frontal width that we get from conditions from the real observed world is consistent with what we think of for submesoscales. We then turned to evaluate this new scaling on a global scale using the MIT GCM LLC 4320. This is known as the submesoscale permitting, roughly 2 kilometer simulation. And together with Gokhan at every grid cell, Jihai Dong has several studies of that flavor. We measured what the old frontal width parameter would look like versus the new frontal width parameter. And this here is the zonal mean on the bottom. And what's really important to see is that the old frontal width is kind of averages out at about 1 kilometer, whereas the new frontal width gets much, much sharper fronts, especially away from the equator. So going back to the parameterization, what this means is that the new frontal width is able to really incorporate this restratification of much stronger fronts, whereas the original parameterization might have underestimated those contributions. So this is where the CSM component comes in. So we saw that the scaling kind of makes sense in several different scenarios. That the theory makes sense to us, but does this break the model when we implement it? So that was a big question. And it turns out that it didn't break the model, and also the results are exciting to explore new avenues. So we implemented it in CSM POP with a standard KPP. So that's what gives the turbulent quantities, W star, U star, and the boundary layer depth. We focused on 2 flavors of simulations, a fully coupled atmosphere ocean model, as well as the forest core V2 simulations. And in each one, we used the new parameterization by implementing this new scaling for frontal width, and we also compared with the old scaling, which is our control parameters, control simulation. So the top panels are winter and summer of the new parameterization. So this is the new LF scaling, and the forest parameterization. The forest simulations of the new scaling. And down here, we've got the zonal mean. So this is similar to the figure we just saw. So we can see again that the new scaling is able to arrive at much sharper fronts, especially away from the equator. Up here is the control simulations, where there's actually a limiter of a frontal width of 5 kilometers. And this really highlights the artificial nature of this old limiter as compared to what we think comes out from this scaling. To examine climate sensitivity, we focus in this paper only on the mixed layer depth to understand the impact on the climate system. We are already planning a more comprehensive study where we'll evaluate several different models with updated observations. But most importantly, right now, we're going to compare the observations to the new parameterization compared with the old parameterization. We can see that it's not drastically different. So there are some changes, which I'll touch on in a moment, but it did not break the model. It did not completely turn everything upside down. And we are still somewhat on the same order with the old implementation. So the previous slide was for winter, and this here is for global summer. And once again, you can see that we're on a qualitatively similar between the old and the new implementation, as well as with observations. However, if we did want to look at the differences, so the new versus old, so the new parameterization versus the control, which is the old parameterization. And this is again here, the mixed layer depth in the couple simulation in the top panels and the force simulations in the bottom panels. We can see that the deeper mixed layer depth is the dark blue colors, and the shallow mixed layer depth is going to be in this green mustardish color. And there are changes, there are differences, and the parts of the world that are that have these changes are important for the climate system. Specifically, the equatorial Pacific in the couple simulation is showing a shoaling, and this has been hard to achieve with boundary layer turbulence schemes, for example. We do see some deepening in the Southern Ocean, which has also been an effort of the community to better capture this effect. We also see changes in the Arctic, in the North Atlantic. So all of these modifications due to just the scale factor changes are what we're exploring in this future study. We'll also be looking at different elements of the climate system to better understand the full effect of this change. So with that, I'll summarize. I hope that wasn't too fast. So a new scaling law was developed for a frontal width as a function of turbulent fluxes. The scaling law is found to be consistent with large eddy simulations with varying forcing parameters. The general ocean turbulence model drawn from observations, the MIT GCM high resolution used in tandem with Gokhan for global estimates. And I've discussed some results from implementing the new parameterization in CSM POPs and the changes in mixed layer depth biases. And as I mentioned, we're now planning a more comprehensive study to compare with observations and really understand the full impact on climate simulations by changing the scale factor. So yeah, thank you. And if anyone has any questions, I'd be happy to answer them.
Thank you very much, Abigail. Any questions for Abigail? I had one quick one. So presumably, if I guess we need to bring this parameterization or this scaling into the MOM6 framework as well.
Yeah, so I'm in contact with GFDL to get that going in MOM6.
Okay, thank you very much.
Yeah, thank you.
Any questions? I do not see anything.
Okay.
Galen, McKinley, Galen, I see you raised your hand, but I don't think that you can directly ask a question. So you can you type it in Q&A?
What would be an impact on the biogeochemistry? I think, the mixed layer depth would definitely be one impact. I'm looking also at ideal age and sea surface temperatures. So these are all different aspects that we're looking to explore. There are also larger scale impacts, the impact on AMOC and other larger scale changes. The change in the mixed layer depth alone is really a large sensitivity to the climate system. So all of that is going to be explored.
Thank you very much. And Hansi says, great work, Abigail.
Thank you.
Okay, so we'll move to our second speaker. Before doing that, I just want to say that Steve is going to finish his talk. He has only one more slide left, 2 minutes, after our second award recipient. So again, thank you, Abigail, and congratulations. So our second recipient is Ine Wanderkellen. I should share my screen just a second before. I should have done that before announcing it. So she is she's a doctoral student at, hopefully I won't butcher this, Vrije Universiteit Brussels, and she has been primarily working on the land component of CESM. She has made significant contributions to the project, CESM project, through two model developments. For the first one, she implemented the dynamic lake area in CESM, and the inclusion of a dynamic lake area model like that in CLM actually forms the blueprint for the inclusion of dynamic urban areas. And that was later expanded within the CESM land model. Secondly, Ine just finalized the implementation of a reservoir management model in the new river routing scheme of CESM. She has also made contributions to the irrigation model, again, within CESM, within CLM. So congratulations, Ine, and floor is yours. You have about 15 minutes. I'll stop sharing.
I'll start sharing my screen.
Yeah, you can share your screen.
Yes, if everything goes all right, you can share my screen right now.
Yep, thank you. We can see it.
Okay, thank you. Hello, everyone. And I'm actually very honored, and I would like to thank the committee for granting me this graduate student award. And also thank you to the people nominating me, and congratulations to Abigail. So my name is Ine van der Kelen, and I'm completing my PhD at the Free University of Brussels in Belgium under supervision of Professor Wim Thierry, Professor Nicole van Lipzig, and Professor Anne van Greenspan. And in October, I will start as a postdoc at the Wyss Academy for Nature at the University of Bern in Switzerland. And in my research, I focused on how we can incorporate dams and reservoirs in Earth system models. And so this is what I want to talk to you about today. But first, let me take you to a river in Botswana. And as you can see on this satellite image time-lapse, a dam was built in 2011, which led to the inundation of the upstream area and the creation of a reservoir. This water area changes the surface roughness, albedo, exchanges of turbulent fluxes, and thereby the interactions between the land and climate. This is not only relevant on a local scale, but also globally, because since the start of the 20th century, humans have built more than 50,000 large dams worldwide. And these large water management infrastructures are built for hydropower production, irrigation, flood control, water supply, navigation, and recreational purposes. And especially during the 1950s and 60s, construction and the creation of new open water surfaces really rapidly increased and even halted sea level rise through their storage of water on land. And altogether, today, reservoirs cover about 7% of the Earth's terrestrial freshwater surface. While these reservoirs are very important, they're not the only way in which human alter the terrestrial water cycle. Also through irrigating crops, pumping groundwater, and water diversion, humans directly interfere with the natural cycle. However, present-day Earth system models mostly simulate the natural hydrological cycle and don't take this human water management into account. For example, only 3 models have irrigation enabled in their CMIP6 simulations, including CESM. And accounting for this human water management in the water cycle is important to reliably represent the terrestrial water cycle, as these can have strong effects on land-atmosphere interaction. And I showcase here for irrigation, it is now shown that irrigation has a strong influence on surface temperatures, which is shown here for an idealized experiment with widespread irrigation, where 2 Earth system models agree that irrigation has a cooling effect on surface temperature, albeit in different magnitudes. And the impact of irrigation is even larger for temperature extremes, where irrigation can cool the hottest day of the year up to 0.8 Kelvin averaged over irrigated land. And maybe important to mention is that these both studies assume an unlimited water supply for irrigation without constraints on local water availability. But as the focus of my research is on reservoir, my main question I wanted to answer is, what is the impact of reservoirs on the climate? And to answer this question, we needed to represent reservoirs in the community Earth system model. And by doing so, we will also improve the terrestrial water availability representation for irrigation within the Earth system. So to represent reservoirs in Earth system models, we don't need to reinvent the wheel because there are water management and catchment models representing reservoirs already, using storage and release policies, which are often derived from observed reservoir operation. And this type of parameterization are less useful in an Earth system modeling context, as there is no information available on reservoir operations worldwide. Global hydrological models, however, do solve dams with generic parameterization, which are simple relationships using limited information. And in this research, we benefited from the parameterization in those models and took them to the Earth system modeling world, where the main goal was to implement reservoirs in CESM. And this we did in two places. First in CLM, or I used here the updated name Ctsm throughout the presentation, where we represent reservoir construction and the creation of new open water area, and in the river routing model, Mesoscale, the new river routing model to be coupled in to Ctsm. This is especially relevant in the context of climate change, and this I want to showcase with an example. So the anthropogenic emission of greenhouse gases led to an excessive heat, which had to be taken up by the Earth system. And while the majority of this heat was taken up by the oceans, the share taken up by inland waters was hereto unknown. And so we quantified the total heat uptake by inland waters, consisting of natural lakes, reservoirs, and rivers, using global lake and hydrological models from the CESM initiative, including CLM 4.5. And so focusing on the reservoir component here, we see that their heat uptake is 2 orders of magnitude smaller compared to natural lakes, which is consistent to their surface area. But this increase in reservoir heat originates from warming waters at the one hand, and on the other hand, from the construction of reservoirs and water becoming available to warm at the other hand. And so the water in the reservoirs themselves also contains energy, and filling up the reservoirs redistributed this energy from ocean to land over the 20th century, as shown here by this area. This redistribution is about 10 times larger than the total heat uptake through climate change. These new open water areas interact with the atmosphere and can impact the climate. And so that's what we looked at in the following up study. We implemented reservoir construction in Ctsm. And we were hereby supported by scientists of NCAR, especially Dave Lawrence and Bill Sachs. And so we updated the original lake masks from MODIS to the new hydrolakes database, which is then coupled to the global reservoir and dam database to create a transient open water map. And we let the reservoir appear in its year of construction, which then results in this spatial distribution of reservoirs described to the model. And the dynamical lake development is already available in the Ctsm source code, and this new data set will become available in the next Ctsm tech. And so we implemented reservoirs as lakes, and lakes are solved for the lake column is contains of the lake water with potential snow on top, saturated soil below, and then bedrock even deeper below. And the water depth is constant in time, as the difference between the precipitation and the evaporation over the lake is compensated by a runoff term, which can be both positive and negative. And to stimulate reservoir expansion, we let the lake land unit grow dynamically based on the prescribed values at the start of the year. This, of course, changes the water and heat content of the grid cell, and we corrected this using water and energy correction fluxes to and from the atmosphere. So we use runoff to the river for water and sensible heat to and from the atmosphere for energy. minimize these artificial fluxes because they can get quite large due to the addition of a lot of heat contained within the lake water. We developed, in close collaboration with Bill Sachs, a baseline approach in which the reference states or baselines are subtracted from the heat and water content of the grid cell prior to the simulation. To investigate the impact of reservoir expansion on the present-day climate, we first ran land-only simulations with CTSM, one with transient reservoir construction and one without reservoir construction. And by comparing these two simulations, we can see the effect of reservoirs on terrestrial surface water over the 20th century shown here. And for grid cells with reservoirs, we see an increase in terrestrial water storage. And as expected, this increase is stronger for grid cells with larger reservoir area fractions. For albedo, we see a decrease resulting from the new darker water surfaces. And for latent heat flux, we see an increase due to the additional availability of water. Look at feedbacks between reservoir and atmosphere. We run coupled experiments with CESM for the present day period. We have two 5-member ensembles with constant land use, one with reservoirs and another one without reservoirs. And we only look at energy and temperature related variables, as precipitation and moisture variables were not distinguishable from signals were not distinguishable from natural variability. And here you see that reservoirs decrease the diurnal temperature range, and these effects are overall small, but can be substantially locally. And if you look at the seasonal cycle, we see that especially in summer, this can go up to 1.5 degrees. Reservoirs also dampen the temperature extremes, and here we show the monthly minimum daytime temperature, which is increased due to the reservoirs. And the effects are again larger for large reservoir expansion and are largest in summer and extended into the fall months. So summarized, reservoirs dampen the daily and seasonal temperature cycle and temperature extremes. The responses are localized but substantial, where reservoirs make up a large fraction. Reservoir expansion is not the only way how dams and reservoirs interact with the Earth system, and to fully implement them in Earth system models, it's important to also account for their stream flow regulation. And I'm going to showcase this for the Bhumibol Dam in Thailand, which you see here, the inflow time series into the reservoir. And the water in the reservoir is stored during the wet season to be released again during the dry season to irrigate the crops downstream. And this dramatically alters the seasonality of the river stream flow. And this behavior needs to be implemented in the river routing model. And so in the new routing model, which is being coupled to CTSM, is MISERoute, a global vector-based routing model developed by Naoki Mizukami. We implemented lakes and reservoirs as part of the stream network. And in close collaboration with Shervin Garari, Martin Clark, and Naoki Mizukami, we implemented dam operation in MISERoute by taking the dam parameterization of Hanasaki et al. 2006 and often used parameterization in global hydrological And so this parameterization has a special treatment for irrigation reservoirs using the seasonal irrigation water demand. And to infer the irrigation water demands per reservoirs, we developed an irrigation topology relating the irrigation demand to individual HRUs. And using the remapped water demands coming from CTSM. And before employing the new scheme, we need to estimate its performance, and we did 4 types of MISERoute simulation: without lakes, using runoff river as outflow conditions, with natural lakes, and using the dam parameterization with and without special treatment for irrigation reservoirs. And first, we performed local simulations for 26 individual reservoirs using observed inflows. And the results show for both outflow and storage, but here only shown for storage, show that accounting for reservoirs actually gives a much better results compared to no lakes at all, and that it outperforms for most reservoirs the natural lake simulation. In the second step, we performed global simulations using the Hdma river network and runoff from CTSM. And here we see actually an overall decrease of the skill, and we see still an added value both for outflow and storage of dams compared to no lakes, but compared to the natural lakes, the dam parameterization show a very similar skill. And then our main question was, why is there an inconsistency between these local and global simulations, and why is the added value of the dam parameterization gone in the global simulation? And so the main reason for this are biases in the inflows, here shown for reservoirs in our dataset in Canada and the contiguous United States. And we see that for these individual reservoirs, the modeled inflows in blue show quite some biases compared to the observed reservoirs in red, both in timing of peak flow, but also in overall magnitude, like these reservoirs. And these biases could have different causes, like could be the level of detail of the river network and the fact that upstream dams are not resolved. But another important reason are biases in catchment runoff coming from Ctsm and shown here as bias compared to the Iran runoff reconstruction products. These runoff biases could have different causes, like the fact that water abstraction for domestic and industrial use is not included in Ctsm, or that irrigation water use upstream is underestimated. The bias in peak of stream flow could be coming from structural biases in snowmelt dynamics. And these biases were not solved when doing sensitivity tests with high quality NL-DAS atmospheric forcing at 12th degree, which we also did in the help of Sean Swenson. Now, potential solutions for these issues are to calibrate, to do a specific parameter calibration of Ctsm for runoff, like Yifan Cheng did successfully for Alaskan basins. Another solution is to include the domestic and industrial water extraction, where a colleague of mine is working on, or to improve irrigation by including different irrigation techniques like drip, sprinkler, and flood irrigation. And finally, the hill slope model, where Sean Swenson is working on, could provide some improvement, or using a higher resolution river network of merit hydro could also improve the simulation. But still, we see when these stream flow biases would be resolved, we would see an added value of the dam parameterization over natural lakes, as it's mainly influential of the seasonality. And yeah, our approach made it possible to actually uncover these type of biases in the inflow. So that brings me to my conclusions. In my work, I advanced the representation of dams and reservoirs in CESM by implementing reservoir expansion in Ctsm and implementing a dam parameterization for stream flow regulation river routing model Mesoscale. And as model development is, of course, a never-ending story, there is still some work to be done, especially to improvements on the Ctsm runoff and on the coupling of Mesoscale to Ctsm and CESM, which is currently ongoing. And improving the terrestrial water cycle in CESM by including human water management opens up a whole new range of research avenues, as these developments ultimately will allow to answer questions related to present and future water availability and the role of human water management in terms of potential adaptation and mitigation strategies. And having a fully coupled model with all interactions embedded is really a key asset here for these type of studies. And on that note, and roughly in time, I would like to thank you for listening, and I'm very happy to receive some questions.
Thank you very much, Ine. Any questions? There is one, I believe. Let's see, from Julio. Thank you for an interesting talk. Is water temperature in rivers a prognostic variable in Mesoroute?
It's not yet included in Mesoroute. I think that's yet another step to be taken in model development in the future. Not an easy one, but one worthwhile to take to improve even better our simulations in the future.
Okay, thank you very much. Any other questions for Ine? If not, we'll move on. And again, congratulations, Abigail and Ine. Well-deserved, both of you. Thank you very much for your contributions to CESM. So I just want to give Steve 2-3 minutes to finish his talk. Hopefully this time he'll be able to do so. Steve, please go ahead.
Yeah, thanks. I turned my video off and this might work better. So I think I was in the middle of comparing these histograms, the one on the top left from HRDP 10 member, the one on the bottom from DPLE 10 member. An important point here is that high skill regions in the DPLE system are characterized by large RPC values, characteristics of the signal to noise paradox. And that situation is significantly improved in high ACC regions in HRDP, and that's associated with the higher signal to total variance ratio in HRDP given by the slope from the origin to a particular point. And so there's some deep and important implications of these results. It suggests that current estimates of climate predictability based on coarse resolution models may be overly pessimistic. They suggest that higher horizontal resolution improves coupled model fidelity, both through improving prediction skill and helping to resolve the signal-to-noise paradox. This result suggests that mesoscale air-sea interaction, which is present in HRDP but absent in DPLE, is a key mechanism involved in the transmission of predictable signals from the ocean to the atmosphere. And an interesting implication is that the inclusion of ocean noise in the prediction system has the net effect of increasing signal more than noise in the atmosphere. So this was my summary that I wanted to get to, and I hope that I've persuaded you that we've come a long way in the past 10 years. I think it's fair to say that DP research has delivered more than most of us would have anticipated back in the late 2000s in terms of refining our understanding of and capacity to predict regional environmental change years in advance. The CESM DP efforts have been at the forefront of many recent advances. And I think this is in large part due to collaborative group efforts that have built bridges between disciplines, between CGD sections, across funding streams, between NCAR labs, and between NCAR and the broader university community. I think CGD NCAR is well positioned to continue serving as a community hub for DP research. And that's something that we're trying to push forward in the Earth System Prediction Working Group. And my final thought is that advancement in DP system design have led to reappraisals of our estimation of the inherent limits of Earth system predictability on climate timescales. Indications are that we have not yet reached the true limits. And so more research is clearly warranted to explore the many outstanding questions, some of which I list here, and to push the frontiers of actionable Earth system prediction science. So finally, I want to thank you again for this award. Thank you for your attention, and sorry for the dodgy internet connection. And last but not least, thanks to all of the funding entities that have made this work possible over the years. That's where I'll conclude.
Thank you very much, Steve. I'm glad that this time it worked fine without any interruptions. Any last minute questions for Steve? We didn't get a chance to take questions. There is one, I think. Let me see. Justin says, Steve, congratulations. In high-res DP, the atmosphere resolution is also enhanced, not just ocean. Could other features than just ocean noise be important?
Absolutely. I think the implication is that it's important to resolve the air-sea interaction. And so we need resolution both in the ocean and the atmosphere to accomplish that. With the set of experiments we have, we can't address the question of which is more important. And that will have to be future work to get a clean answer to that question.
Okay, thank you very much. And again, congratulations to all the award recipients. So we will take a break here. Please do come back at 10:50 Mountain Daylight Time. That's 12:50 p.m. East Coast time and 9:50 a.m. On the Pacific side. And we'll have two plenary presentations. So 10:50, please, Mountain Daylight Time. Thank you. Rob, if you would like to put your presentation up just to make sure it's working.
Oh, sorry, you can't hear me. I will try.
Okay.
Okay, I think I'm ready. Do you see the proper screen there, or is that?
Yes, we do see the proper screen. Great.
Okay, perfect.
Yeah, just wait a couple of minutes.
Hi, Galen.
Hello, hi Rob, nice to see you. Sorry, I also had to find my Zoom screen again.
And I think 2 years in, I would no longer make that mistake, but I do still. So Gokhan, will you give me any time warnings, or do you want me to keep track? I have my
No, I
phone.
can keep it. So you have about 30 minutes. So I can do. Would you like me to give you a warning at about 25 minutes?
Sure. Yeah, I have my phone. I'm going to try and keep track of it, but
Okay.
I won't go over.
Yeah. People are joining back in, I guess. Okay, so it is 10:50 here. Let's get started. Well, welcome back, everybody. So in this session, until lunchtime, we have two plenary presentations. And the first one is going to be given by Rob Jackson. Rob is a professor of Earth System Science at Stanford University. He is interested in studying many ways people affect the Earth, particularly focusing on seeking basic scientific knowledge and use it to help shape policies and reduce the environmental footprint of global warming, energy extraction, and other issues. He is currently examining the effects of climate change and droughts on forest mortality and grassland ecosystems. He is also chairing the Global Carbon Project, which aims to measure and reduce greenhouse gas emissions. His research also includes establishing a global network of methane tower measurements at more than 80 sites worldwide, and measuring and reducing methane emissions from oil and gas wells, city streets, and homes and buildings. And today he'll be presenting something very similar to what I just indicated to you. So Rob, thank you for accepting our invitation. The floor is yours.
Well, thank you, Gokhan, and thank you all for being here and for your work with CESM. I've had the pleasure of working with a number of you over the years, going way back to people like Gordon Bonin. And today, as my title says, I'll discuss emissions of different greenhouse gases. I won't have time, or we won't have time to talk about nitrous oxide in any way, but I'll cover carbon dioxide, methane, and just touch on hydrogen at the very end. And the goal today is to do two things. I want to provide just a sort of an update on sort of where we are with various greenhouse gases, but more importantly, I hope to present some research and collaboration opportunities for work with the CESM community. And that's my real goal. So I will go from there, and thank you for having me. Gokhan mentioned the Global Carbon Project. I'll rely extensively on GCP data and materials for this talk. And we recently completed our 5-year plan, as you can see at the top, to produce regular greenhouse gas budgets for carbon dioxide, methane, and newly, a year or so ago, nitrous oxide, led by Han-Chin Tian and Rona Thompson. And what I mean by a budget is a sort of a catalog or a measurement of sources and sinks for different greenhouse gases, and also analyses that combine natural as well as anthropogenic activities, and also bottom-up and top-down approaches for estimating the various emissions and fluxes. So we're eager to, now that we have the three main or dominant trace gases, we're eager to update those regularly. We're working on new methane and nitrous oxide emission budgets now this year. And more importantly, we hope to put these gases together so that when we evaluate things like biomass energy or different scenarios, we want to make sure that when we're, say, maximizing carbon storage, we aren't losing some of the benefits through nitrous oxide emissions with fertilizer use or things like that. So our long-term goal is to put these pieces together, if you will. But I'll go through my talk and credit a number of folks who've contributed to these efforts. And I can't see the participant list, but a number of you probably have. So thank you and everyone who helps us do our work. Well, just a quick update on carbon dioxide. You may all have seen data like this, but we released, led by Pierre Friedlingstein in Exeter, our recent carbon budget. And that sawtooth you see on the right, you're looking at emissions of fossil carbon, CO2, by year going back about 3 decades. And you see the sawtooth in 2020, of course, that's attributable to COVID-19 and the slowdown in the global economy. But the take-home message in our most recent budget released last November was that emissions have essentially snapped back like a rubber band almost to 2019 levels, so that we can't expect a crisis like COVID-19 to bail us out of the climate problem. And that's been consistent with other economic slowdowns you've seen in the past. The savings and loan and financial crisis a decade or more ago, you see a similar drop down of about 1.5% for a year. And then the next year, it jumped back almost 5% to where you could almost have continued the line from before, and the turn down didn't matter. So COVID has reduced global emissions. We're coming back and worried that this year may be higher still, as brown sectors of the economy have been stimulated around the world, particularly in China and India, resulting in greater coal-based emissions. And of course, why are carbon emissions still rising despite, as everyone knows, rapid growth in renewables of more than 10% a year? And the reason is because most of the new energy infrastructure or capacity being brought online today isn't taking fossil fuel off. It's adding new capacity to supply extra demands on global energy. There are some exceptions to that. Coal use has declined here in the US and in Europe in particular, substituted in the US mostly by increased gas use, and to some extent now by renewables. So we're starting to turn the corner on coal a bit, although the last year or so have been troubling for coal, but we really haven't turned the corner yet for gas or oil use. You can see on the right of this slide the rapid rise in renewables, but how small, relatively speaking, renewables, hydro, and nuclear are compared to the 3 main fossil fuels. Well, I think more interestingly for this community is what is the fate of carbon dioxide that's released into the atmosphere from fossil carbon use or from deforestation. And about 90% of that carbon comes from fossil sources now, and about 10% from deforestation and other activities. That's the sources box on the left here. But on the right, you see where it goes. And as I think everyone on the call knows, only about half that carbon dioxide stays in the atmosphere. And almost 30% is going back into lands. Primarily, we think the stimulation from atmospheric carbon dioxide fertilization. And then, of course, a quarter or so of it's going into the oceans and slowly acidifying the oceans. And I'm sure we'll hear more about that from Galen in the next talk. Well, the airborne fraction has stayed remarkably constant over decades. This slide says 45%. It was a little higher in the previous slide, but it's around this value of about 45%. And you can see that this fraction goes back for a long time now, a number of decades. And if emissions are rising on the right, course, what that means is that if the airborne fraction stays constant, then the ocean and the land have to be taking up more carbon dioxide for that to be the case. And that is, of course, what happens or what is happening. This is the most recent estimate of the ocean carbon sink. I mean, it has continued to increase based on our budget estimates, the ocean-based carbon products, a number of sources. And it's about 10 to 11 gigatons of carbon dioxide a year, but steadily increasing, as you would expect if the airborne fraction is to stay constant. And land, it's also been increasing as it needs to, a similar amount, 10 to 11 gigatons of CO2 per year. The land sink, of course, is much more variable than the ocean sink. Depending on the year, we have large fire years, we have drought years, La Nina, El Nino years make a difference, of course. So it's rising too, but much more variable. And for a couple of decades now, there have been a lot of concerns about the extent to which the land-based sink will continue. And Pierre's work, going back 20 years ago, raised a key issue in this space with nitrogen availability and other factors, and just highlighting the variability across different models. But even apart from the models, there's some evidence that the land and ocean sinks are maybe slowing a little bit, particularly on land attributable to climate change effects. So you have, again, droughts and other factors that can reduce the land sink. And you see that here in the blue is a sink, and red is a loss in sink activity. And you see that by this estimate, climate change reduced the carbon sink on land by about 1/6 and 1/7, about 15%, and the ocean by about 5%. So you're seeing this in particular places in the tropics, in particular, to some extent, semi-arid systems. So we have a lot of eyes on this question about the extent to which the land sink will continue, and I think there are other reasons to expect it to slow this century, resulting in more of the carbon staying in the atmosphere. This was an analysis that we worked on in the last couple of years. We analyzed data from about 140 elevated carbon dioxide experiments in the field, and looked at the effects on biomass and NPP. And then we put that analysis into a random forest model. We analyzed a bunch of predictors or correlated factors, climate, nutrient status, soils, and nutrient availability, as I'll go over in a minute, land cover, and also the interactions or modifications through mycorrhizal species that are dominant in these systems. And one of the things that we found, this was work led by Cesar Torrero as a postdoc in my lab at the time, not surprisingly, is that nutrient limitations, as other folks have shown in the past, can reduce the carbon sink, the land sink. So we estimate that the CO2 fertilization effect is controlled by soil nitrogen in about 2/3 of global vegetation, and by phosphorus in about 1/4. But interestingly, the effect is moderated by mycorrhizal type. This figure on the left shows you the biomass response to CO2 enrichment as a function of soil carbon to nitrogen ratios, a very sort of crude index of nitrogen availability, but one that's readily available across the planet. And for arbuscular mycorrhizal systems, you see that the CO2 fertilization response drops dramatically as this soil seed N ratio increases or N availability decreases. So that's that sort of declining curve you see on the left. You see a different kind of curve on the right for phosphorus, though, in systems dominated by ectomycorrhizae, where the CO2 fertilization effect goes to close to zero in low phosphorus conditions, and then above a certain threshold stays approximately constant when you have enough in the system and it's available to plants. But there are large parts of the earth where nitrogen and phosphorus limitations are active and should work, we believe, to constrain the land sink, particularly as carbon dioxide concentrations continue to rise in the future. And this results in analysis we followed up just last year with an interesting interaction. What you're looking at here is the effect of elevated carbon dioxide on soil carbon on the y-axis, and on essentially plant stimulation on the x-axis. And what you see is a strong trade-off between the ability of ecosystems to add more plant biomass or to grow more and to store more carbon. You almost never see a lot of soil carbon storage in ecosystems where the plants demonstrate sort of more wood and more biomass growth. And I think the reason for that is because in systems where biomass growth is increased a lot, the plants or the microbes are mining soil organic matter, if you will, for nutrients. And so you tend to see this trade-off that where biomass or plant growth, wood production goes up, you see very small increases in soil carbon and larger increases where the CO2 fertilization effect on plants is less pronounced. So this holds for grasslands and forests. And I think it might be an interesting thing to look at in the CESM community, this trade-off that we find for soil carbon versus plant stimulation of growth. So that's one possible avenue, but I want to switch now and talk about methane and begin with sort of a question of why I believe that methane is so important right now. And methane is responsible for almost 2/3 as much warming as carbon dioxide, as assessed in the most recent IPCC summary for policymakers, which is this figure in the middle. The figure shows the contribution to warming in the decade of the 2010s compared to the last half of the 19th century. And you see that in that decade, that over that whole period of time, that CO2 was responsible for about 3/4 of a degree C warming, methane for about 1/2 degree C, and then other factors increased or reduced that amount. And so the contribution of methane is quite strong compared to carbon dioxide, although carbon dioxide is the gas of most importance long term. But methane is really the only potent and short-lived climate forcer that we have possibly under our control, if you will. If we can reduce methane emissions through mitigation dramatically, or even work to increase sinks through removal, then we have a lever that can shave peak temperatures and delay crossing thresholds. And so that's one reason I think it's so important to be focusing on methane right now. We've seen the global methane pledge that was announced in Glasgow at the recent COP. Methane is also far more potent. Its global warming potential is sort of 30 to 80 or 90 times more potent than carbon dioxide over a couple decades to centuries. We did an analysis led by a grad student in my group, Sam Abernathy, earlier this year that suggested if you care about 1.5 degree stabilization, and a synthesis of model results through CMIX-6 suggests that 1.5 C threshold might be crossed in about 25 years. That if that's the time frame you care about, that the appropriate GWP for methane should be about 75, or much closer to the 20-year time frame value than the more commonly used 1 century value. So anyway, some justification for why methane. Some other justification you've all seen this plot, I'm sure, from NOAA. Methane is rising much more rapidly on a relative basis than carbon dioxide. In 2020, it had at that time was a record jump of almost 16 parts per billion in the year. But then last year in 2021, the European data suggests a 16 part per billion increase, and the recent NOAA data release suggested 17 parts per billion. So methane not only is not becoming stable in the atmosphere, it's rising faster for reasons that are not entirely clear, although the isotopic signatures suggest a more biological source than a fossil source. We still don't fully understand the methane stasis period in the middle of this figure around 2000, but that's a far cry from now with methane going up very rapidly. This was our most recent global methane budget led by Muriel Saunois in France. And as I've already indicated, methane emissions in the methane cycle is dominated much more by human activities than the carbon dioxide cycle is globally. About 60% of all global methane emissions come from human sources, and about 2/3 of those sources, anthropogenic sources, are agricultural, and 1/3 are fossil. And that's a surprise to some people to know that cows, for instance, can emit as much methane as fossil energy infrastructure. So we really have to think about addressing agricultural and food-based emissions and energy-based emissions. And I believe to reach our climate goals, we need to reduce emissions on the left. In orange is the fossil term of about 100 million tons a year, agriculture, a couple hundred million, smaller amount of fire-based emissions. And wetlands are the largest natural source of methane, about 200 million tons a year. So we have to reduce those sources, but we also have to think now about ways to enhance the sinks of methane that occur naturally, mostly in the atmosphere from radicals of chlorine, an OH or hydroxyl, and also microbes in soil are responsible for a much smaller portion of the methane that's scrubbed from the atmosphere. So some of our work has been thinking about how to obviously mitigate methane emissions, but also begin to think about the sinks. Are there ways to speed those up or enhance them? We know a fair bit about sort of where and why methane is emitted on the planet. So these are sort of Edgar type inventory-based emissions factors and locations for wetlands, fossil sources, ag and waste, and biomass and biofuels burning. Some of these sources are amenable to detection from space and drones and aircraft, and I'm excited about those new tools that are being brought to bear on this problem. And the energy infrastructure large point sources are particularly suitable for this. And as you all know, there are a couple of new satellites that are being launched. The methane sat from EDF and the carbon mapper system from Riley-Duran, which is a private-public partnership. So I'm really excited about that work that will help us identify the super emitters and try and get them turned off more quickly than we otherwise would have been able to. So when we look at sort of how methane cycling has changed over the last few decades, this is a figure also from the last methane budget. You see that the largest increases in emissions in recent years have come in Asia in particular, and Africa. Emissions have gone up a little bit in North America, mostly here in the US. And when we look latitudinally, which is the four set of plots on the right, I should note that the two bars in each pair are top down on the left and bottom up on the right. You see latitudinally that most of the increase in emissions appears to have come from the tropics and temperate systems, and that Arctic emissions are still quite small and don't show any evidence of an acceleration or runaway methane release. And overall emissions there are low too. So that's good news, as we're all concerned about permafrost thaw and accelerated release from Arctic ecosystems. We don't see evidence for that yet. So we're still trying to understand the source of these extra emissions. In some cases, they're food-based. Some cases in the tropics, they may be related to increased wetland emissions, and I'll come to that in a minute. Well, this was a story that came out a couple of years ago. I like this title, "The Arctic Might Be a Methane Time Bomb or Not," which about covers it. And we can't predict these tipping points very well. And even in the Arctic, which we know is warming faster than anywhere else on the planet, we have a hard time predicting the balance of emissions that will come from methane and CO2 with permafrost thawing, because those emissions depend strongly on the hydrology, the local hydrology, how waterlogged the system is. So in both cases, that permafrost thawing is bad news. We'll get more methane or more carbon dioxide, but we don't know sort of where and how much and how often we'll get most of that carbon that's been locked away released as methane, because it's really hard to predict. And there's a great deal of research going into this topic right now. So something we're all concerned about, very difficult to model, and especially to integrate globally off something that's quite a small scale phenomenon and very hydrology specific. There are lots of folks and unanswered questions in the potential for wetland emissions to increase as well. This was a recent Royal Society meeting that you and Nisbet and others organized. And I just highlight a couple of papers and findings from this meeting. And the title of the meeting was "Rising Methane is Warming, Feeding Warming." And Ewan's hypothesis here was that the rising temperatures in the tropics is already speeding up the emissions of methane from tropical wetlands. And there are some papers that suggest that's the case and others that don't see evidence for that yet. But it's a reasonable hypothesis to expect that to happen, assuming all other things are equal, like rainfall and hydrology again. This is another thing to keep an eye on, and we're trying to address this in the Global Carbon Project. We just launched last year our FluxNet methane product, which is something we worked on for many years. Gokhan mentioned this, and some of you may have contributed to this. So these are publicly available flux tower data sets for 80 sites around the world. This is a collaboration with USGS and the Powell Center. These data are all publicly available and free of use online. And I also want to thank the FluxNet folks at DOE who helped greatly with this. So this is our FluxNet methane community product. It's up now, and we can use it to, to start to address some questions about warming and climate change and build out a better monitoring system. And here's the kind of figure that we can see. This is methane emissions as a function of mean, in this case, I believe soil temperature on the x-axis in this case. So methane emissions, not surprisingly, are strongly related to temperature across wetlands. Each of these dots is a different wetland around the world. Now I have to point out that this is a cross-site comparison of temperature effects, and that's not the same as warming a site individually, of course. But we know that temperature has a strong effect on methane emissions. There's good reason to expect warming to enhance methane emissions if wetness stays the same. So it's something to keep an eye on. I want to credit the postdocs in my group who contributed to this effort for years, Kyle Delwish at top and Sarah Knox in the bottom right in particular. We're also using this new flux-based product to try and understand agricultural emissions for the new satellite-based products and also for fundamental knowledge. And this is a new map of paddy rice emissions for monsoon Asia, led by Zutao Yang. So this is based on about 25 flux sites. We built a process-based model for methane emissions, and then we're using it to scale based on maps of rice paddies. And monsoon Asia comprises about 90% of global rice production and global rice cultivated area. So we have these maps now, these flux-based products for 5,000 meter resolutions, about 15-year period, 2000 to 2015. And we're working to extend those to a global map and to more recent years. And in this analysis, temperature was the strongest predictor of our model. And we estimate the paddy rice emissions across monsoon Asia are about 21 teragrams of methane per year, which is a little bit on the low end of what previous investigators have found. The map on the left shows you the location of the rice paddies. The map on the right shows you the emissions intensity. Well, just kind of coming to a close then, we're also really interested in exploring scenarios of large-scale methane drawdown in the atmosphere. That drawdown could come from mitigation activities. It could potentially come from methane removal, which is something that's still more of a concept than a scale technology, but something I'm working on a lot. And there are some interesting modeling questions for predicting the outcomes of drawdown or reductions in large-scale reductions of sort of hundreds of millions of tons of methane emissions on the atmosphere. These are a couple of papers that came out last fall with an eye to this. One was a research agenda, and another the sort of a modeling with the Hadley Center on the benefits of methane removal and proportional reductions in temperature and in surface ozone concentrations. And I'll point first to grad student Sam Abernethy's work. So Sam and my group worked with Fiona and Chris at the Hadley Center to use the Hadley Center's new methane emissions driven capability to perform these drawdown simulations. So they looked at different timings and scenarios and rates of methane mitigation or removal. And they estimate that across these simulations, each petagram of methane mitigation or removal reduced surface temperatures about 0.2 degrees and global mean surface ozone concentrations of about 1 ppb. And Sam is currently working with Ben Gobert at NCAR. They are using CamChem to model spatially explicit scenarios of mitigation and removal for methane. The left figure here shows the temperature reduction per effective petagram of methane removal by year. The blue is the sort of purplish is SSP1 2.6. And the red is the more aggressive SSP3 7.0, and the same on the right, but for ozone. And you see the benefits for ozone on the right and temperature benefits on the left. We've also proposed a a methane removal intercomparison project, but we need more Earth system models with methane emissions driven capabilities. These are some of the questions that we've proposed for this activity, to use scenarios of different timing and different amounts of methane removal, to compare the climate impacts and Earth system feedbacks of methane removal on these different scenarios. And of course, the outcomes depend on whether you're comparing low or high emission scenarios and what is happening with other greenhouse gases like carbon dioxide and nitrous oxide. We'd like to do spatially explicit simulations of methane removal that prescribe locations and latitudes. And this is the aspect I applied or mentioned before and that Sam is beginning to work on. We're interested in studies of how methane's relatively short lifetime in conjunction with climate feedbacks on natural emissions influence metrics of cumulative methane removal. So methane is different than carbon dioxide in that it's more of a flow gas than a stock gas, as you know. We're interested in feedbacks of air quality, particularly tropospheric ozone. And there are lots of interactions here through OH chemistry and hydrogen, as I'll come to, and ozone. And then interactions of methane removal with other mitigation and CDR approaches. I believe if these technologies can be developed, that whenever we're removing air in, for instance, DAC systems for removing carbon dioxide from the atmosphere, when we're expending the energy to draw one greenhouse gas out of the air, we should be considering removing more than one greenhouse gas at the same time so that we maximize the benefit of moving that much air. I'll stop just with one more, just sort of a placeholder really, and a call for interaction, if you will. And at GCP, we're just launching our first hydrogen budget effort. And this is, of course, in response to increasing calls for a hydrogen economy as an energy storage technology and possibly a transportation technology. So we need to learn, I need to learn more about what is happening in CESM in the hydrogen space. And I think Jean-Francois is leading some work with CESM in this realm. And at GCP, we need help quantifying the effects of hydrogen on the lifetime of methane and other greenhouse gases, ozone in particular. When there's a lot of work that needs to be done constraining the soil hydrogen sink, which is the biggest sink, and to produce a top-down budget for hydrogen. And we're really limited in the hydrogen space by measurements. There aren't good laser-based instruments, high hertz instruments for hydrogen the way there are for methane. There's no Picaro for hydrogen measurements right now, so we don't have good estimates of methane leakage from pipelines. Flux measurements from soils are really hard to come by. So there are a lot of areas that we're going to need as a community better data for hydrogen. I'm flagging here some recent papers, none of which I was involved with. Fabian published a good one last year with GFDL and possibly, I think, with the CESM use. And there are a couple of other papers, one that just came out, Cooper et al., and then the EDF paper from earlier this year, looking at different scenarios of leakage and their climate consequences. So just a plea, if you will, to explore ways of hydrogen and interactions for a new hydrogen budget. I will stop there. I think I'm on time and probably went too quickly. So thank you all for listening, and I'd love to hear your comments and have time for discussions and questions, and look forward to hearing from Galen.
Thank you very much, Rob. This was really great. So we have one question already from Peter Gent. He's asking, do you think the COP26 agreement will lead to a significant reduction in methane emissions?
Great question. I hope it will. And the Global Methane Pledge, for those of you who don't know, is a pledge to reduce methane emissions by 30%, I think is the number. And there are more than 100 countries have signed on to that. If we keep to the Global Methane Pledge, and the US has committed to that, then it will make a difference. It's not enough to get where we need to be to reach the full goals of the Paris Accord, but it would be a fantastic accomplishment. We just need to figure out how to go even farther than that. So I hope so is my answer. I don't know if we will. I certainly hope so.
Thank you. Any other questions for Rob? I had one question. Could you clarify? It wasn't clear in my mind. How close are we, or how good is the current methane sort of mitigation technology?
for, say, mitigation or removal from?
Removal, that's what I meant. Yeah,
um,
sorry, not mitigation.
We're not close to a sort of a scale technology for removing removing methane from the air at 2 parts per million. What I've been trying to work on myself in our lab and talking with other people about is to work our way down a concentration curve. So not to start at 2 parts per million, but there are many methane sources in the environment, particularly from indoor dairies, VAM gas from coal mines and such, that are closer to 200 or 2000 parts per million. And right now there's no mitigation technology available that works below 2000 ppm or so. You have thermal oxidizers that go down to about that level, and you can flare at higher concentrations. So there are a number of microbial approaches, catalytic approaches, and aerosol-based approaches that are being explored and researched right now. And I hope that in the next few years, there'll be a bunch of papers out on the feasibility of those approaches, but we're nowhere near being able to apply this at a global scale to actually do atmospheric removal of methane. But that's one of my long-term goals. Thermodynamically very hard, low concentration, and you have to process a lot of air. So mitigation is still where the action and focus should lie.
Okay. Thank you very much. And one more question. How are methane projections set in the SSPs?
So I'm not entirely sure. I'm not entirely sure I understand the question, to be honest. Maybe you could expand for me.
Yeah, I guess socioeconomic pathways that we use for future projections, they have various pathways to get to that particular goal. So I guess this question is asking about what the treatment of methane is in those projections. That's my understanding of the question.
Sure. So I'll offer an answer, and I'm not. Okay, I see the follow-up now. I'm not positive, but I think the answer to that question is that within the SSPs, there are scenarios embedded in them of sort of food production, population, energy use, and different scenarios of fuels. And I suspect the emissions that are embedded in those SSPs are inventory-based, emission factor-based, as you would expect from the different IAMs and the different SSPs. So I suspect they're just bottom up based on the embedded energy and food production.
Okay, so it's 11:25 here, so let's move on. Thank you very much again for a very nice talk, Rob.
Thank you all, and open to collaboration for anyone who wants. Thanks for your work.
Thank you. So our second presentation is going to be given by 2 people, and I believe Galen McKinley is going to go first. Galen is a professor of Earth and Environmental Sciences at Columbia University and the Lamont Doherty Earth Observatory. And she's an ocean, carbon cycle, and climate scientist whose research focuses on the physical, chemical, and ecological drivers of the ocean's anthropogenic carbon sink. She is also the deputy director of the Center for Learning the Earth with Artificial Intelligence and Physics. That's the LEAP project, and the slide is up already. And that's an NSF Science and Technology Center that's newly formed. And she'll be tag teaming with Laure Zanna. Laure is a professor in mathematics and atmosphere ocean science at the Courant Institute at New York University. Her research focuses on the dynamics of the climate system, and the main emphasis for her work is to study the influence of the ocean on local and global scales. She is the lead principal investigator of the NOAA NSF Climate Process Team on Ocean Transport and Eddy Energy, and also M2 lines. It's an international effort to improve climate models with scientific machine learning. And she's also currently serving on the CESM Advisory Board. So please go ahead, Galen.
Great, thank you so much, Gokhan, and thanks everyone for being here. It's a great pleasure to work with Laure to present here about machine learning for climate modeling with M² lines and LEAP. I'm sorry, Rob, I'm not going to be talking much about the ocean carbon cycle in this talk. I'm going to be talking about the other hat that I wear, which is as the deputy director of this new Science Technology Center that was funded last year. And I want to provide some of the basic foundation of where LEAP is coming from and what we're trying to do. It's an overview talk, not a lot of depth here, but I'm hoping to make this a starting point for collaborations with lots of people working on CESM over the years to come. So the basic motivation for LEAP is that the coming decades are really critical to climate adaptation. And we're really focusing here in LEAP on the next 40 years or so. And in this period, if we look at the total uncertainty in our projections, which is best seen here on the right-hand side with the fractional contribution to the total uncertainty, we see that the model structure in blue is really the dominant component of that total uncertainty, dominant fraction there. And so, and this is, this is the model structure. These are the parameterizations of the parameters. Now, of course, as I'm sure many of you are thinking, adaptation doesn't happen to the global decadal mean annual temperature, but in fact, it's going to happen locally. And there, the representation of internal variability is going to become more important, as shown in the orange here, for some smaller regions, the Sahel, the Southern Ocean, and Southern Europe. The orange becomes larger, but of course, as really clearly demonstrated by Steve Yeager's talk earlier today, the model structure is really a big part of our representation of internal variability. If we can't get precipitation extremes with the right frequency distribution in the modern day with the current model, then we're not going to be able to do a good job of projecting how those will change. So, model structure is really a key focus for LEAP. And what do we mean when we say model structure? We mean parameterizations and parameters. And many of these are subgrid scale processes such as clouds, ocean eddies, and photosynthesis, all processes that to some degree, if we had infinite resolution, we could fully represent the clouds and the ocean eddies in our models. The fact that we can't is a big part of why we have spread in our temperature projections, our ocean heat content projections. There's also processes such as photosynthesis that we might know very well how it works at the, the very basic molecular level within a cell, but how then do you scale that up from the cell to the leaf, to the tree, to the global ecosystems becomes the big challenge, as Rob touched on in his talk. That leads to so much prediction uncertainty in, how is the carbon cycle going to respond to climate change? Where is the carbon cycle going? What are those feedbacks going to be? So we're really thinking across the Earth system model, thinking about model structure in a broad way. And of course, as I will return to in a few slides, it's not just parameterizations themselves, it's also the parameters that are set to build the model and couple the components together. Okay, so at the same time, we have big data really exploding in our field. We have massive data coming in from satellites, hyperspectral resolution, for example, coming in that tells us so much more about our system processes. We also have autonomous sensing. We have field data. We have so many more sources of data that aren't fully being used in our Earth system models. If we don't have massive data, we might have, for some processes such as clouds, high resolution process simulations that really can give us a good representation of clouds. There, the problem is, we know the equations, we just don't have the compute power to calculate all our predictions that we want to do with cloud resolving resolution. And so those high resolution process resolving simulations can become also a source of big data from which we can build better parameterizations. And then the key link here is machine learning, right? Machine learning has really been revolutionizing our industry and our Netflix recommendations and science just in the last 5 or 6 years. It's really just exploded and has really become an opportunity to pull in the big data into our system models. So that's where that's what LEAP is going to try to do. The goal is to harness data and advance machine learning to improve our climate projections. So LEAP's overall structure is shown by the diagram here, and our mission statement is shown on top. We want to increase the reliability, utility, and reach of climate projections through the integration of climate and data science. We have kind of 5 main components here. The first one is climate data science, where we're addressing across the Earth system components, or linking studies across the Earth system components to data science through education, as shown by the mortarboard in the center here, to create a new field of climate data science through education and integrated education research experiences. We want to create clear pathways for the knowledge derived by the research here to impact the CESM in particular. That's our primary target, although we are also working with NASA, GISS, and Model E to ensure inter-model operation of at least a subset of the parameterizations. And then we're going to work in knowledge transfer with corporate partners and the public to make sure that the information we're providing from those next generation projections is useful to our users. So we have a significant effort in knowledge transfer as well. Underlying a LEAP is a LEAP Pangeo, which is a cloud-based data infrastructure where we're going to do analysis in the cloud and store the large data sets that we want to be working with. And on top is broadening participation. Our goal is to significantly increase the representation of underrepresented minorities in both climate and data science over the course of our 5-year grant. And I wanted to introduce just the executive committee. There are many other people beyond this executive committee that are working in LEAP. We are 11 people leading this SDC from Columbia, from NCAR, from NYU, and University of California, Irvine. So specifically, I want to provide a few research objectives. I can't provide them all, but our first research objective is to improve parameterizations. We want to accelerate CSM development with novel parameterizations enabled by machine learning. Below is a video animation of some work by Pierre Gentin and Mike Pritchard and others. CAM5 is shown on the left. This is a precipitation rate. The superparameterized CAM is shown in the middle, and you can see much finer features of more intense precipitation occurring in that superparameterized version of CAM5. And then on the right-hand side, you can see the neural network CAM that was developed based on the superparameterized data output, but run at a similar integration speed as CAM5. And yet that this was able to give us those fine-scaled features in terms of the precipitation rate, really quite comparable to the superparameterized CAM. And on top of that, if we look at the distribution of precipitation, we see that the neural network is able to give us those much less frequent but very high precipitation rates down here, and also to give less of the very frequent low precipitation rates, and is quite consistent with the superparameterized CAM, and as a big change from the control. So these are some of the proof of concepts that we want to be implementing and moving forward with, implementing in more fully in CSM, and also building new parameterizations based on these kinds of ideas. We also want to enhance machine learning with physics. I mean, one of the challenges of current machine learning is that they don't automatically respect physics. You know, conservation of mass, conservation of energy are not necessarily what's going to come out of a statistical fit. So we are also working with our machine learning colleagues to find ways to build machine learning algorithms that respect physics, where whether it's in the training of the algorithm by implementing some component of the loss function, or by other kind of design of the machine learning algorithms, building them so that they can respect the physics. And also in other cases, or using them to discover causal relationships. We might have a data set, say, of an ice sheet, where we don't really know the underlying equations that we should be using, but we can use equation discovery to try to identify a parameterization that'll do a better job than what's currently in the model. Research objective 1.3 is to automatically calibrate ESMs. There's a lot of interest in finding better ways to do parameter estimation, both for independent components of the model and for a coupled model. So when we go through this cycle of model development, where we add a new parameterization to a model, we compare the data, and then we do parameter estimation to try to improve the fit. We would like to make this cycle much more efficient by using emulators to better explore the state space and then to optimize the parameter set. So this is really following on work by Katie Dagon and others at NCAR, where they showed that compared to their default community land model minus observations on the right-hand side, in many regions, although not all, but in many regions, they were able to reduce the errors in gross primary productivity on land by using machine learning-based optimization. Okay, so in order to, this all sounds well and good, but we recognize that in order for the machine learning to really make an impact on CESM, which is our goal, we need to structure the research in order to progress from proof of concept to implementation. So in LEAP, we've developed a concept of 3 levels, where level 1 is proof of concept projects, level 2 is uncoupled models or data products, and level 3 is full implementation or a metric being applied as the model is being evaluated. So what we'd like is in our year 1, we have more projects here at proof of concept and fewer at level 3. And then as we go through time, we end up with, of course, more projects by year 5 in that full implementation. And that is where that's essentially what we have now. So we've just selected 14 research projects in year 1. I don't have time to show you all of them, but I'm going to focus on the level 3 and level 2 projects. Level 1, we have 9 of them that I'd be happy to talk to you about at a different time. So we have at level 3, we have Warm Rain, led by Andrew Gettleman at NCAR. Some initial papers published there. The goal now is to fully implement this into CESM. And also superparameterization emulation, following on the work from Pritchard and Jantine that I showed you a few slides before, also working with Scott Bachman at NCAR. So those are moving forward to implementation. At the level 2, we have 2 projects in parameter estimation, one led by Greg Alsasser at NASA GISS, the other led by Dave Lawrence, Katie Dagon at NCAR on the land side, and the systematic calibration is more focused on the atmospheric side. And then I'm leading a project working with Tian Zheng here at Columbia and Matt Long at NCAR to use new machine learning-based CO2 flux products as a metric for CSM evaluation. So how are we going to achieve this implementation? How are we going to move up from level 1 to level 3? This is going to be facilitated by LEAP engaging with the working groups. And also we're hiring a LEAP integration engineer through the project who will be resident at NCAR. Here's the link if you're interested in applying for that position. We also have several postdoc positions that we are recruiting for at the present time. So in just the couple moment I have left, I want to also mention LEAP Pangeo. LEAP Pangeo is a modern data infrastructure to support research and knowledge transfer. Essentially, we're expanding and extending the Pangeo project into LEAP Pangeo. So we want to the idea of Pangeo and LEAP Pangeo is to get away from the standard approach of downloading lots of data to your personal system and analyzing it. Instead, we want to move the scripts and the analysis to the data held on the cloud, where it can be easily shared and where analysis can be reproduced. In education, we're inclusively training climate data scientists. We're really trying to provide training in climate and machine learning for the next generation of model developers. We want to forge a new discipline called climate data science through integrated transdisciplinary curricula that are also available in open source, opportunities from K-12 to graduate, and an effort to increase representation. And finally, knowledge transfer. We want to open lines of communication with corporations in the public sector. I think we're all well aware, having been in the climate modeling business for a long time, that better climate modeling alone is not going to improve adaptation decisions. So our goal is to make progress in this area with bidirectional, regular communication between scientists, corporations, and the public sector. And so we have people in the business school working with us, particularly on the corporation side, and others with public sector connections on that side. Okay, so that's the mission statement again. Thank you very much. And I'm going to end my share, and so Laure can take on.
Great, thank you very much, Galen, for the great intro of Flip, and thank you very much, Gokhan, and the rest of the CESM community for the invitation. So what I'm going to do now is focus on another project quite complementary to Leap. It's called M²Line for multi-scale machine learning and coupled Earth system modeling. So we're supported by Schmidt Futures. We started about a year ago. We actually finished our year one just about a week ago. And so we are about 30 domain scientists, model developer, machine learning experts across 9 institutions in the US and France, including NCAR and many colleagues, at GFDL, IPSL in terms of modeling centers and other universities. So the goal of M²Line is really to improve climate model skill at the LC interface using data and machine learning. So some, complementary themes to Leap that you just heard from Galen, and focusing on biases in coupled climate simulations. So, Galen motivated, greatly the need for, better climate models to improve projections. So let me show you model biases. So basically the errors between simulations and observation in 3 different models. And it's not because I'm picking on those models, but those are the 3 models that we're focusing on in M²Line. GFDL, CSM, and IPSL, and we're looking at SST biases. So all models are biased, right? So, and that's okay. We know it's hard to actually have, perfect models. And what we see here, actually, what's interesting is the SST biases, many of them are common across the models, right? So say, cold anomalies in the North Atlantic, or warm Gulf Stream, all of those are present in all the models, warmer Southern Ocean at the entrance of the Atlantic. So where are those errors coming from? And so again, Galen told you a little bit about this, right? So part of the model error, the structural errors, come from the fact that we're solving equation on the grid, meaning that all the processes that are occurring below the grid box size of the climate models that we have are not properly represented. So clouds, ocean eddies, and so on and so forth. So anything that is smaller than the grid box size of the models that we have, it's usually parameterized with some kind of semi-empirical mathematical formula, or sometimes not represented at all. Second part of the structural errors also come from the numerics, right? We have continuous equations. We need to introduce some way to do the discretization. Some of the numerics can sometimes lead to errors as well. So the combination of those 2 is really what drives some of the biases that we see up here, kind of the differences between simulations and observations. So as I mentioned, the goal of M²Line is really to improve the skill at the surface, of those climate models, of those coupled climate models. So improving basically representation of surface fields in the ocean, ice, and atmosphere on timescale of hours to century, and provide more reliable climate prediction. So we have a bit of a 2-pronged approach in M²Line. The first one is to develop new data-driven, machine learning-based parameterization with physics for subgrid processes in the ocean, sea ice, and atmosphere. So how do we do that? Again, we're going to take some kind of high-resolution simulation and observations, and then extract representation for those missing processes, again, ocean eddies, clouds, and so on, that will replace or enhance the current parameterization that we have in models, implement them, and of course, the evaluation and calibration will need to happen as well. The second part of M²Line is to actually use a different type of data set called data assimilation increments, because the goal is also to reduce structural model bias, right? So improving the physics, as we all know in climate models, is a great thing, but there are a lot of compensating errors. So just focusing on the physics, will get us one way towards improving the structural, representation of the models, but not entirely. So the data assimilation increments are basically corrections of the coarse resolution model itself for a given set of observations. So by using the data assimilation increments, what we're learning is state-dependent parameterization or correction to the coarse resolution model itself. And so again, going through those kind of 2 paths here, learning from high resolution and from data assimilation increment, we can iteratively go into the coarse resolution models at GFDL and NCAR and IPSL and focus on either the missing physics or the additional structural model errors that are appearing over time. And so this kind of iteration will help us provide more skillful simulation. So I can't do justice in 15 minutes to the entire project and the great work that people have done in the last year, but I'm going to highlight a few things that I believe are of interest to the CESM community and also the whole field of using machine learning for climate modeling. So for the first part on learning new physics from data, so here is a schematic of all the processes that we're focusing on in M². And you can see there is a heavy weight on the ocean components. And so I'm going to still focus on a few of them and hopefully give you a flavor of some of the work that's been done and how it connects to CESM. So first, parameterization of convection and microphysics. This is led by Paulo Gorman and Yanni Yuval at MIT. So they develop using data from SAM, a parameterization for convection and microphysics. So let me add this little thing here. What's important about what they've done is really finding a machine learning based parameterization that conserves energy and water. And then when implemented in an idealized simulation leads to stable implementation. And so if you look at the precipitation distribution, green line is the coarse resolution, blue line is the high res, and the coarse resolution with the machine learning neural network-based parameterization is the orange line. So you can see that the precipitation distribution is greatly improved. So what Paul and Yanni are doing right now is to actually take this new machine learning parameterization and implement it within CAM, right? So of course that requires meticulous work to make sure that all the diagnostics are properly implemented. And so I forgot to mention their inputs are moisture and temperature, and then the outputs are all the tendencies over here. So really they're trying to actually now take this machine learning parameterization and implement them into CAM. And I'll come back to that in a bit. Other parameterization that we've been focusing on, especially when it comes to radiative feedbacks. So planetary boundary layers in the atmosphere. This is led by Alex Carnelly and Pierre Gentine, and sea ice heterogeneity, but now rather than using high resolution simulation, Lorenzo Zampieri and Marika Holland at NCAR are actually using direct measurements. So for those of you at NCAR, you should ask them to show you some of the plots. It's actually pretty cool. Now for the ocean parameterization, so we know that a lot of those parameterization leads to uncertainty in the transient climate response to emission, in ocean heat uptake, and in tracer transport. So within M², we are working on improving vertical mixing. So this is led by Princeton and GFDL, especially enhancing an existing parameterization with neural networks, focusing on sub-mesoscale eddies as well, and a big core of us working on mesoscale parameterization for momentum, buoyancy, and tracers. So I'm going to show you a couple of examples that come from those parameterization that we developed and their initial implementation into MUM6, which will become technically the ocean model for CESM3, as as Gokhan showed in his talk. So a couple of parameterization that we've developed. One of them is using data from idealized simulation. What we've done is we use a machine learning algorithm to learn a mathematical expression for the parameterization. And this is this kind of stress tensor over here. So it's kind of a very simple mathematical expression. You can actually interpret it and easily go and implement it into a model. Second parameterization that we developed using a machine learning algorithm called convolutional neural network. So that's a little fancier, but nonetheless try to do the same, but in a more abstract way, using data from CM2.6, sorry. So using MUM5, basically an older generation of the GFDL model, but it's run at 1/10 of a degree, and it's a coupled simulation. So here what we learn is rather than just learning, for a given input, a given output for the parameterization, we learn a Gaussian PDF. So kind of a first step towards a stochastic parameterization for ocean mesoscale eddies. And in both instances, we're focusing only on the momentum part here. So because M² is really trying to target 3 different models, and the field is a little bit new, we decided to start with an implementation in a rather idealized configuration. So it's a double gyre, right? So it has some bathymetry in it, but it's still pretty idealized. Run it at 1/32 of a degree and 1/4 of a degree. You can see less transport. Jet is weaker at 1/4 of a degree compared to the 1/32 of a degree. And this configuration, we can test the numerics, the stability, and the learning and the communicating between Python and Fortran. And I'm happy to talk more about this. So I'll just show you a couple of plots. One where we implement the equation discovered into MUM6. So the jet is enhanced, detached better, does a pretty good job. Stochastic parameterization, now we can run an ensemble. It's not as large as the large ensemble. We can run many members. And so again, we improve upon the coarse resolution without parameterization. So first step, first implementation, and again, this is led by Alistair Adcraft and colleagues at GFDL. So what are the pros of learning from high resolution simulation, new parameterization? One is we're targeting physics, right? We're targeting processes that are directly related to physics. And so in this case, it improved transport. Technically, it's agnostic to the coarse resolution model in which we're going to implement it. again, technically. So I mean, it's transferable. And that's true for the most part. What I didn't tell you is that we have to tune, right? So there's nothing new here. And the tuning is, we still didn't quite get a handle on it. And that's something we're working on. Now, the challenges with that is, as we all know, there are compensating errors in global models, right? So it's not because we're going to fix one process that we're not going to break others, or that other, biases won't emerge because, two processes were canceling each other out. Also relies on high resolution models and not observations. So this is not the truth yet. And, the number of simulations that we have are also limited. So our strategy is, again, as I said before, targeting many processes at a time, right? So that's what we're doing with this little schematic. And of course, adapting our methods of learning and diagnostic. I think the most exciting part to some extent is that we're also targeting those data assimilation increments, meaning we're going to machine learn model error from the DA increments. So what are those? Well, they're integrated errors, right? And they project on the long-term bias. I'm going to show you a couple of plots with that. And they contain many different common and model-specific biases from the models that we're targeting. And they really focus on, again, the problem of the coarse resolution model that we have at hand, which is really our target at the end. And so I'm not going to read this slide, but this is really the premise of this work, is that, and this comes from a paper by Rodwell and Palmer, and goes back to Klinker and Sardeshmuk, which is, for a given forcing, say CO2, your biases, say in convection or ocean eddies, will take place on timescales of decades. But now the timescale associated with the process that we're considering is actually much shorter. So there's a pretty good chance that a lot of the biases might emerge on relatively short timescale, and we should be able to pick that up in this paper from short-range weather prediction mode. And so that was for entrainment rates and convection. And this is a little bit of the schematic. And the data assimilation increments provide us that, right, over a short time scale, basically the correction that we need to give a model. And so if a model is always biased in a certain direction, then the D increment should actually give us an indication of which processes are biased. So can we machine learn that model errors arising, say, from the Gent-McWilliams coefficient, the convective rates, or KPP, and so on and so forth? So first, we need to figure out if the data assimilation increments project onto the long-term bias, right? So here is PEER, so the GFDL, ocean assimilation runs. And so this is the data assimilation increments for, surface temperature or upper ocean temperature. And this is the long-term bias. And you can see that, some of the biases have already emerged after just 30 days. Now, this is work down here led by Will Chapman and Judith Berner at NCAR using DOT. So this is the free model bias from CAM. Now, those are the data assimilation increments average. So now you can see it does not project that much. And basically what they found is most of the projection of, say, the data assimilation increments was on the quality and the quantity of the observations. So now they came up with a creative solution, which is coming up with a new data set, which is a nudging increments. And the nudging actually kind of project a lot more onto the free bias of the model than the data assimilation increment. For CI, things are a little bit cleaner. So this is led by GFDL, so Will Gregory and Mitch Bushak. So this is the free running model bias in CI's concentration, data assimilation increments, and the forecast tendency. And you can see they really map onto each other quite well in many areas. That means that now they can actually, go understand where the biases are coming from, and then use machine learning to learn those corrections and really understand what are the processes that are causing those biases on short term, which will then project onto the long-term biases. And again, by using, this kind of learning in parallel from the high resolution simulation and the data simulation increment, we really can interpret, where the common biases are coming from, in which process, and then iteratively go and target the remaining processes. Okay, so let me conclude on this kind of few lines here. So, we've been working on this for about a year now on machine learning for, from data simulation, and very, very recently on learning from data simulations. Some of the new problems are kind of the same as the old one, right? Calibration, tuning, evaluation, stability. So, we're still learning, we still have a lot to do, but it's pretty exciting. But we're also relying on everything we know from, climate modeling community. The target for the next year on some projects that I think are relevant to the CESM community and it'll be great to engage is we're going to focus on component models. So ocean only, sea ice only, and atmosphere only before we move to the couple. So here are a few plans. OMIP runs with month 6 of the new parameterization that we developed. So one led by GFDL on improving the planetary boundary layer in the ocean with machine learning, and 2 others on mesoscale closures, the 2 that I showed you before, a convolutional neural network and an equation discovery. As I mentioned, Paulo Gorman and Jan Yuval are leading the implementation of a machine learning convection in microphysics into CAM, first in an aquaplanet setting. Then the rest of the project will focus on kind of, improving and refining those machine learning closures that I mentioned before, the atmospheric planetary boundary layer, sea ice heterogeneity, and so on and so forth. And then, of course, further developing those ideas of machine learning, the data simulation increments for state-dependent parameterization for sea ice ocean atmosphere. So just want to leave with that slide here. We're developing a lot of tools, and a lot of people are, trying to also work with machine learning and parameterization. So we hope that you can find a lot of useful information in our GitHub page. We're writing a Jupyter book on learning machine learning with Lawrence 96 that hopefully many of you can use if they're trying to get their feet into this project. We're developing new algorithms for equation discovery and new benchmarks as well as we develop parameterization. So hopefully you can grab a lot of those tools and learn from them or contribute, and it'll be a great way to engage with people. And so I'll leave it at that. I think I'll just hit 15 minutes. Thank you very much.
Thank you very much, Galen and Laure. It's clearly a lot of work. Any questions? Doesn't look like we have anything. It's almost 12 o'clock actually, local time. So the idea, I should have just mentioned briefly before your presentations that these are 2 important projects related to machine learning involving CESM, and we thought that it would be it would be good to introduce them upfront in a plenary session like this, so that all working groups of CESM and the CESM community would be aware of these activities. And again, as Galen and Laure said, if you are interested in, CESM is involved already in both of these projects. We'll make sure that things work smoothly, both collaboration-wise and also in the model. And if you have any questions related to both LEAP and M2 lines, please reach out to Galen and Laure respectively. Thank you again.
Thank you, Gokhan, for having us. Yeah.
Thank you.
Yeah, thanks.
So we'll take a break here for about an hour, and we'll come back at 1 o'clock local time, 3 p.m. Eastern time. And we will have 15-minute summaries from the working group starting at 1 o'clock with the atmospheric model working group. Thank you very much, and see you in about an hour. Bye.
Anybody else there yet?
Almost, Julio.
So it sounds like you'll be quote unquote driving during the presentations.
Yes, I have a license to drive. We are trying to multitask here.
Sorry.
No worries.
Yeah, I'm going to be drinking and water.
Oh my. I thought that you were drinking some other stuff.
I'll wait till after my talk.
Yeah, but if you do it before that, it'll be smoother.
You know, that's probably true. Or at least it will feel smoother to me.
That's right.
I'm so sorry.
Hi, hey Gokhan.
Yes.
Are there any questions or does it just go through?
There are no questions in this session.
Okay,
We'll just go through.
15-minute talks. Okay, thank you.
Yeah, but I'll give you probably a warning.
Oh, okay. So in the unlikely event that we finish early, what do we just?
We'll just continue.
Okay.
Yeah.
Matt has a question, it looks like.
Yeah, Matt, that should be turned on. Elizabeth will be turning it on likely. Chuck, it's good to see you or hear from you, I guess. I'm sorry that you missed the morning session. You can see my screen, right, Julio?
Yes.
So for the working group co-chairs, each working group has 15 minutes. And we will not have any Q&A for this session because all of the Q&A or questions can be asked in the working group sessions tomorrow and the next days. And I have the master sort of slide deck, and I'll advance the slides for you. And I'll try to give you a 1 minute warning if you are running sort of.
Okay.
At that pace. And it's being recorded, so whatever you say
will live forever.
Will live forever. Okay, let's get started slowly. So welcome back again to this afternoon session. So we will have 6 updates from 6 working groups. Then we'll take a break for 20 minutes, 2:30 local time. And then we'll have another update from the remaining 6 working groups. So our first update will be from the Atmospheric Model Working Group, and Julio Bacmeister will be presenting. Please go ahead, Julio.
Yeah, thank you, Gokhan. First of all, I want to acknowledge my co-chairs, Christiana Jablonovski and Kevin Reed, for their contributions not only to the talk, but also to development over the last several months and years. So next slide. This is a quick outline. I'm going to be talking about development, and I will really be focusing on what you might call development of the bones of the model. I won't be talking too much about new physics themselves. They'll be discussed more at our session tomorrow. I'll also discuss some of the timelines driving our development. Coupled results here really should read coupled plans, and I'll briefly touch on our software management burden survey, which resulted in quite a lot of feedback. So yeah, why don't we just dive in? So next slide, Gokhan. This slide is, I wouldn't call it comprehensive, but relatively comprehensive list of CAM development. I'll be focusing on the items on the left, that is what we're doing to prepare CAM for the next climate model, the next version of CSM. The main things I want to talk about today are vertical resolution. I'll be discussing a few things, or one aspect of the physics in particular, the reordering of the physics subroutine calls, and I'll briefly mention some developments in our treatment of the boundary topography for CAM. So really, as I said, kind of bones of the model sorts of development. For people in the community interested in tracking what we're doing, you can look at the development website there, github.com NCAR AMWG dev. It's a very nice website, a very nice repo designed by Cecile Hanai, and you can look there to keep up with the simulations we're doing and some of the preliminary analyses, etc. Hopefully, some of the topics on the right-hand side of the slide will be covered in our working group meeting in the winter. But as I said, I'll be focusing mostly on CAM 7 for climate in this talk. So next slide, Gokhan. This is a list of physics development efforts. As I mentioned, we have reordered the way the physics is called. I'll explain that in a little more detail in a second. This is something that Adam Harrington pioneered and has been instrumental in getting going. We have had to make changes in Jan McFarland because of the increased vertical resolution, and you'll see in a second why. The rest are physics developments that some of which will be covered in talks tomorrow. Two projects involving club. Joao Teixeira and Colin Zarzicki will talk about two CPT efforts that seek to improve our implementation of club. There are other efforts that I just want to mention, but I won't talk any more about, and I don't think there won't be talks on them. Coupling of the land atmosphere using subgrid parameterizations. That's a nice effort going on, really in collaboration with the land group. Andrew Gettleman is working on unified microphysics, and Peter Lauritsen is continuing development of a rigorous enthalpy and energy treatment for the atmosphere, because as you probably know, and we'll probably hear later, our new ocean model MOM6 requires enthalpy fluxes from components. Okay, so why don't you advance? Go ahead, Gokhan. All right, so our short-term timeline is here. It's driven by our plan, CSM plans to release, we'll call it CSM 2.x in mid-2023, which means that by late 2022, we really have to finalize the configuration of CAM to allow adequate time for coupled tuning, et cetera. So this CSM 2.x is supposed to be a viable coupled version of the model that incorporates MOM6. I should have mentioned CI6 here too, plus our L58 and L93 vertical grids, which you'll see in just a second. I want to emphasize this is not necessarily the next CMIT model. It's really meant to give the community something to work with a little sooner. What we're doing now is we've started a coupled evaluation using our new vertical grid with still mostly what you'd call CAM6 physics with some slight modifications, including reordering, some updated topography, and an enthalpy fixer to accommodate MOM6. By later this year, we hope to incorporate PUMAs, the new microphysics, as well as possibly some contributions from the CPTs that are working with Club. And then, of course, CAM will continue to develop, but we'll talk about longer term plans at our meeting in winter of 2023. So please, Gokhan, next slide. So I want to emphasize this has been talked about several times already, but I just want to kind of, just emphasize this really has kind of we're sort of this is now really a fact. We have moved CAM to a higher vertical resolution grid with the high top version, this L93 with the top around 80 kilometers, and a cheaper L58 version with the top around 40 kilometers, so that we can have a single CMIP class model that resolves the stratosphere with full chemistry as an option to sort of perform our next set of climate runs. And I want to acknowledge Isla Simpson, Brian Medeiros, for leading the vertical, for leading the process that selected these vertical grids. And as I mentioned, coupled evaluations with the L58 have already begun. So next slide, Gokhan. These slides show our new vertical grid in CAM compared with the CAM6, WACM6 versions. On the left, you see in red is our new 93 level grid. The black open circles and dots are the CAM and WACM grids. And you can see that in the free troposphere, we've gone from a resolution of over, well, it's about 1,200 meters to a resolution of 500 meters in the vertical. On the right of the slide, you see a blow up of grid spacing in the lower troposphere. You see we've dramatically increased PBL resolution. Our new model lowest level, which is critical for surface exchanges, is now at 20 meters, whereas previously it was at 60 meters. This new vertical structure has required a modification to Jean McFarland, which Rich Neal will talk about tomorrow. Next slide, please, Gokhan. So this slide just shows some L93 results to just give you some confidence that we have a reasonably good simulation of extending into the stratosphere. On the left here is the QBO in the equatorial zonal wind. You can see that our model, the lower panel, compares fairly well with ERA. On the right are some zonal mean, zonal wind plots, which show that, I would call this, just to give you an idea, this is a credible model. So next slide, Gokhan. This shows the effect of increased vertical resolution on cloud structures in the boundary layer. I'm sorry, it's since I can't really point, But on the in the lower left of each group of panels is our L58 version, and directly above it is the L32 version. And you can see that there's just a more geophysical, I would call it sort of intuitively satisfying reproduction of structures of the statistics in the model. We have to work on getting some validation data for this, but I would say for now, it's promising. Next slide, Gokhan. Another big change is the reordering of physics. The main difference is that club has moved to a position after the coupler. This is done mainly to avoid spurious high frequency oscillations in the surface layer. So can you please advance, Gokhan? So this is the old 32 level, and you can see underlined in red is club microphysics. It's before coupling to the surface models. And we've realized, Adam, as I said, spearheaded this, that since club is a vertical, it's a boundary layer turbulent scheme, in addition to being a cloud scheme and a shallow convection scheme, it really, the model works better with this advanced Gokhan. The model works better when club is called after the surface couplings. So the next slide, Gokhan, shows some impacts of reordering. On the right, on the right is our time series of 10-meter winds from 4 points in the Amazon. The light blue is the original CAM physics. And what you see, it's hard maybe to make it out, but you see these regions of kind of fuzz in the 10-meter wind. These are places where we're getting time step to time steps oscillations. And they're eliminated in the dark blue, which is the reordered physics. On the left of this plot is a annual mean shortwave cloud forcing comparing reordered physics with the original physics. And you see that there are some differences, but they're not major. So next slide. Another change we'd like to make is to, we've made some changes to the topography software. I think one important option that we will have to play with is what we're calling no-leak topography. That is, the new smoothing can maintain 0-meter elevations over ocean. And you can see that comparing the right and the left here over the North Atlantic and Labrador Sea, places where we think this might make a difference. So on the right is the new no-leak topo. On the left is the old 1-degree topography with smoothing. They're both smooth at a radius of about 180 kilometers. So you can see. So we're hoping this will make some positive differences in our air-sea coupling. Naturally, this has effects everywhere there's high coastal topography. So coupled evaluation has begun. We're now doing, in conjunction with the ocean group, of course, B1850 pre-industrial controls using L58. These are using the reordered physics with the modified Jang-McFarland, MOM6, and CI6. By fall 2002, we hope to add 93-level vertical grid and incorporate some contributions from the physics development that's ongoing now. And we also, I think, given especially some of the things Gokhan showed today, sooner rather than later, perform some additional configurations of the coupled system, 4 times CO2 or last glacial maximum. So then I think this is the last slide, the next one. You might have been aware, some of you, that we sent out a survey on reducing the software engineering workload. We received 40 responses, many of them having to do with SPCAM. It's clear to us we need to do a better job of communicating with the LEAP group, and we will be discussing this at our session tomorrow. So with that, I'll stop, and I hope to see everyone tomorrow and hear from you at our discussions. Thank you.
Thank you very much, Julio. So we'll now move on to the whole atmosphere working group. And I think Nick Davis will be starting. Please go ahead, Nick.
I will actually start.
Okay, sorry.
That's all right. So we will give a brief discussion on some of the recent developments in the whole atmosphere working group, and then also some of our future plans as well. So next slide, please. So one of the first developments to highlight is the development of the spectral element dynamical core and extending it into the thermosphere and ionosphere. So this is in the WACM-X model, which extends up to about 500, 600 kilometers. And because of the high altitude domain, it's necessary to make some modifications to the dynamical core. And so those have been implemented. And then also a regridding scheme was implemented that enables transformation between the spectral element irregular coordinate system and the geomagnetic grid that we use for the ionosphere transport and electrodynamics. And so with those capabilities, we've been able to run the spectral element dynamical core in WACM-X, and we'll be able to use that going forward. And one of the main advantages is that in the finite volume dynamical core, we had to include, especially in the high latitude region, some artificial filtering or smoothing. And if you see on the right, which shows the temperature at 400 kilometers during a geomagnetic storm, the top is the finite volume and the bottom is the spectral element. And you can see, though, the general large-scale structures are similar between the two. The SE dynamical core has much finer features to it because we can remove this artificial filtering. And some ongoing work is related to the SE development is high-resolution capabilities. I'll show more of that on the next slide. And we are also doing some work on coupling to a magnetospheric model called Gamera, which will allow better forcing from solar and geomagnetic storms, so we can study space weather-driven variability, and then also meteorological constraint through both nudging to reanalysis and also data assimilation to reproduce the upper atmosphere variability driven by lower atmosphere meteorology. Next slide, please. So the high resolution WACM-X SE has been run at a resolution of NE 120, which is roughly about a quarter degree in latitude longitude, with 273 vertical levels, so about a 0.1 scale height. And we've run for nearly 1 year with no parameterized gravity wave and a constant solar and geomagnetic activity condition. And on the left is a plot of the zonal mean, zonal means for the month of January average in the contour, and then the shading, it represents the forcing from smaller scale waves. And two things to note in this figure is first, if you look at the high latitudes in the northern hemisphere, the winds remained eastward throughout the mesosphere, which alleviates one of the biases we've had in the coarser resolution model, where this feature is driven by parameterized waves. So when we can resolve the waves, we get a better representation of the circulation. And there's also significant zonal forcing throughout the thermosphere, where the current parameterization does not add any forcing. So it seems like we get a much better representation of the general circulation throughout middle and upper atmosphere by resolving all the waves. And this could potentially be used for improving our parameterization for the coarse resolution in the future. And on the right shows some of perturbations in the total electron content, which is the ionosphere electron density at short periods. And you can see we capture a lot of small scale features, which are relevant for understanding the space weather. Next slide, please. And one other additional work in terms of dynamical core development and extension is extending MPAS into the lower thermosphere. So there's recently been some work with MPAS-A to extend to higher altitudes, which was partially supported by Hdma. And this will provide eventually capability for hydrostatic capabilities to WACM. And here on the bottom is shown the comparison of zonal mean, zonal winds on the left, middle. Left is finite volume, middle is spectral element, and right is MPAS. And these are all run with roughly the same resolutions. And you can see in general, the middle atmosphere winds are similar between all three dynamical cores. There's at least some differences, but to first order, they're the same, which suggests this extension of MPAS into lower thermosphere is working. And some more details for those who are interested will be presented on this version of the model in the working group session on Wednesday morning. Next slide, please. And one additional work that's been done is some work to better prescribe the solar and geomagnetic forcing. This is a Python package developed by Dan Marsh and others, which will allow for both easier updates to the solar spectrum that we use to force the model, and then some new production rates for precipitation. Next slide, please.
Okay, so I'll talk a little bit about the development that's going on a little bit lower down. So this is something that has been ongoing work over the last year, is an evaluation of the middle atmosphere chemistry configurations of WACM. I'm showing on the bottom right the core hour cost of a simulated year with a interactive ocean and land surface for different configurations of WACM. So here, TSMLT is the comprehensive chemistry from the surface to 140 kilometers in the WACM grid. And then MA is chemistry that's basically SMLT, so middle atmosphere, neglecting some of the organic chemistry and other fast chemistry that's important for tropospheric chemistry and things like air pollution. And so you can see that going to the MA scheme itself offers potentially a factor of 3 savings on core hours, and then dropping down to a coarser 2-degree resolution of WACM with MA is a factor of 10 savings on core hours for WACM 6. So, from a community standpoint, it's important, I think, to support and at least evaluate these configurations moving forward, because you can imagine that if you're doing long climate simulations, you definitely don't want to have to run 1-degree TSMLT if you can get away with 2-degree MA. And so on the upper left here, this is just a Gregory plot of the global mean surface temperature anomaly versus the top of atmosphere net radiative flux, which is a basic way of estimating equilibrium climate sensitivity, in this case from the 4x CO2 experiment. And essentially, we don't see any differences in the configurations in terms of climate sensitivity, which you might expect, because we're getting the greenhouse gas chemistry and emissions the same in these models. The organic chemistry in the troposphere is just not adding much. And in a forthcoming paper, we're showing that it's not just the climate sensitivities that are equivalent, the mean climate and variability are quite similar as well. There are some important differences that we've been finding. One of our folks working on this is Dan Visioni, and he has been looking at the stratospheric aerosols just from a perspective of using these runs for geoengineering. And you can see that these 2 economical configurations with middle atmosphere chemistry have higher background aerosol optical depth versus the standard full chemistry configuration. But during volcanic eruptions, they're quite similar. That just has to do with the fact that there's apparently weaker upper tropospheric oxidation of SO2. So you're not oxidizing as much, so you're getting more background aerosol. So there's a few things to keep in mind. Next slide, please. So this is a timeline of some of the physics and other developments that we're working towards right now, split into 3 different categories. So we're well into 2022 now. The top line, this is sort of our improving community support and existing functionality. So we're working on some kind of regionally refined COMSET. We would really like to support initialized prediction COMSETs, but we're not sure that's feasible given our resource constraints now. But we think, especially some of the things you'll probably see at the ESPWG meeting on Thursday, this I think would be something valuable for our community to support. We're working on a fix for TEM and transport diagnostics that are dicore agnostic sometime in 2023. And together with some folks in AMWG, trying to improve our specified dynamic scheme. Then in terms of chemistry and physics, some of the things that have been implemented are VSL halogens, updating RRTMG and the shortwave heating schemes in progress. And you can see we're doing everything from updating KARMA, which is, I would say, definitely something overlapping with CCWG, all the way to improving our treatment of gravity waves and oxygen transport in WACMEX, working towards a scale-aware gravity solution for our regionally refined COMSETs. And then what I'll shortly talk about here is our integration with the workhorse model that Julio was showing in his overview. So I'll give you a roadmap to a couple of the ways we're thinking about morphing WACM to fit into this new high-top workhorse framework, the goal of which is to move towards a whole geospace model. Next slide, please. So Julio showed some similar figures here. I'm showing right now the current WACM 110 level grid in these black filled circles, and then the 93 level CAM workhorse in the red filled circles. So this is showing you the log pressure altitude versus the grid spacing in meters. And you can see that the workhorse model at about 30 kilometers diverges from 110 level WACM and has a slightly larger grid spacing. So there's a couple of ways we want to approach this. And right now we're not committing to any particular vertical level scheme, but we would like to try a couple of different options. One is to simply stack WACM on top of the workhorse model. So essentially in the red open circles, this is our proposed solution. We sort of accept the reduced vertical resolution in the middle atmosphere in favor of a simple addition to the grid, and then simply shift the sponge layer up a little bit higher. Another option is sort of keeping the spirit of our current 110 level vertical grid, and that's to maintain a fine vertical resolution throughout the middle atmosphere and transition to the same 3 kilometer vertical spacing by the lower thermosphere. This isn't necessarily going to increase our tuning burden or our workload, because we're still inheriting the same CAM workhorse tuning in the boundary layer and troposphere by inheriting the same grid up to 30 kilometers. So I think by and large, either of these solutions would be fine. I don't think either the 128 level or 109 level is necessarily going to be a different development workload. It's more what can we get away with in terms of resolving our existing dynamics and physics and chemistry without losing fidelity with our current vertical resolution. So I would say stay tuned sometime in the next year for that. And then finally, just to summarize, I think both of these models continue to be highly valuable for middle and upper atmosphere research, and they're currently being adapted into an Earth system predictability platform. You can tell that part of our focus here is to parallelize development of these simplified and low cost configurations while keeping some of these cutting edge and high cost model configurations. And I would say for sure right now, a lot of our new developments are aimed at addressing existing model biases and also advancing our capabilities to fit with the current workhorse model that's being developed by AMWG. Thanks.
Thank you very much, both of you. So we'll move to now Chemistry Climate Working Group, and Simone Tilms will be presenting. Please go ahead, Simone.
Yeah, hi everybody. My name is Simone Tilmes. I'm here at ACOM, the new chemistry climate co-chair for this year. And we also have a new outside external co-chair, Rafael Fernandez. He's from the National Research Council of Argentina and also National University of Cuyo. We do have a new chemistry climate liaison, which is Rebecca Buchholz. And we still have our software engineer, Francis Fitt. Next slide, please. So I want to talk about achievements from the last year, but then also developments that are ongoing and also integrating to Chem 7 and the workhorse model. And I would like to start with the Musica developments. I will talk in the next slide about MICChem and Music Box. But I want to point out that we had a lot of work going on for the Musica version 0, which is Chem with the spectral element dicore and the regional refinement. We had a tutorial in the from last fall to spring about how to run this model with chemistry and also analyze it. Luisa will talk more about this on the talk on Wednesday. And we do have more work going on. There will be more talks on Wednesday, and I will highlight also some work with this model for ACLIP. So next slide. This is the MICChem is the model independent chemistry module. This is a database of chemistry mechanisms, data needed for solving chemistry. And this allows easy changing the chemical mechanism and also running the same chemistry in different atmospheric models. And MICChem has been also integrated in our chemistry box model, which is called Music Box. And you can check that out here on GitHub. And it's coming along quite nicely. You can run it on command line, browser interface, and there's more work still going on, but we do have various updates here. And there will be a talk, more discussed also on Wednesday. If you go to the next slide, please. More talks on also the ACLIP campaign. ACLIP is a field mission that will sample the Asian summer monsoon from South Korea. And we are using actually the 58 level workhorse model with regional refinement over Asia that you can see here to investigate, use this model as the forecast model. And this campaign will investigate the anticyclone over the Tibetan Plateau and the eastward shedding. So more talks will be coming on Wednesday. And if you want to learn more about it, please come to the talks. Next, please, is more achievements. You have to go further. Oh, there we go. Sorry, I didn't see that. Yeah, so more is the chemistry development. We have updates to the chemical mechanism, and there was, for instance, updates including HONO. And so some papers or several papers using Chem investigating the effects of COVID on air quality using new chemistry. We also have worked and continue working on the Melodies Monet evaluation package in collaboration with NOAA. And this is a diagnostic package that especially looks more in detail like chemistry evaluation, aircraft data, and also satellite data. There are several aerosol developments that have taken place in the last year that are in the model code now. Aerosol scavenging scheme in convective clouds by Win Pan and Shan and Xiaohong Liu, as well as online DMS emissions, and also the MEM5 new modal aerosol model with 5 modes, adding a stratospheric sulfate coarse mode, which is in particular helpful for the chemistry versions, Chem and Chem. But in addition, we going back to the CSM1 MEM4 mode widths, and those are impacting also the coarse mode sea salt and dust emissions, which will improve the simulations. So this is already in some of the concepts available and will hopefully merge into the workhorse model soon. And then next slide, I want to also highlight work that has been done with the colleagues at Harvard, especially Thibault, Fritz, Seb Eastham, and others. And there will be a talk on Wednesday on the geoschem merge into CSM 2.1. And in particular, GeoSChem is a chemistry transport model, which runs usually driven by with met data like MEROS and GEOS5. And this model has been coupled into CSM to also take advantage of specifics of CSM, like the climate interactions, cloud aerosol interactions, and so on. And the goal of this project was to really merge the benefits from these two different chemistry modeling frameworks, like identify differences in the model, differences in parameterizations, and also merge the user community and improve the capabilities. And what comes with GeoSChem is the HEMCO emission tool, which is an online emission component that we now also have integrated into CSN. I mean, the Lin et al. And the group from Harvard, together with people at NCAR. And so eventually that we will not need the pre-processing of emissions to prevent various mistakes potentially in those processing. And so things can be done more online in the future with this capability. Next slide. So on ongoing model development, I want to start with the aerosol developments. I will talk a little bit about improving the simple chemistry in chem for SOA. And I will not show an example, but we also working, or people currently also working on new dust emission scheme in connection to MEM5, as well as implementing marine organic aerosols into CSM, and we're planning to further update new schemes that were developed for the dry deposition of aerosols. The next slide, then please, will highlight some of these developments. This is a simple development of SOA. Du-Song Yo, Luisa and I are working on this. And people may know that actually running chem and chem or WCAM will give you a different radiative forcings. And this is in part due to the difference in how secondary organic aerosols are described in the model. In chem, they are much more complicated, described using chemical reactions to form secondary organic aerosols, while in chem, we just using pre-calculated offline emissions to have a precursor gas phase in secondary organic aerosol emission, which then transitions to the aerosol form, but we do get different answers, burdens, which also impacts actually black carbon and primary organic matter. And what we are doing now is adding only one basically tracer and intermediate emission SOA tracer that imitates the chemistry that is happening through a lifetime decay of 1 day. So we will actually now simulate the secondary organic aerosol gas chemistry and SOA in a much improved way. And in the next slide, you can actually see that here is the chem SOA on the left plot, seasonal cycle, and the chem original seasonal cycle is very different. But if we add the new scheme, we get much closer in the aerosol burden. You can also see that in the vertical profile. And in addition to secondary organic aerosols, we also improve the comparison with chem and chem to the primary organic aerosols and black carbon. And this will have impacts on the radiation, which makes this much closer, chem much closer in radiative forcing to the chem model, so to models that use full chemistry in the troposphere. More on this again on Wednesday in our talks. Next slide, please. Yeah, I mentioned that Xiaohong's group, in particular Xi Xiao, and also with help of Susan Bowers from PNNL and Christina McCluskey, working on a new marine organic aerosol model, which is to be implemented, is currently implemented in MEM4. And this is a much more physical-based implementation of these marine organic aerosols. You can see that it has impacts on the cloud condensation nuclei, and especially significant over the Southern Ocean in winter. And that has also impact on the radiation. We can see here on the ice nucleation particles on the right, which are increased. Next slide. I want to talk about some developments that we're doing here at NCAR in connection to CESM, the abstract aerosol interface. So you probably know that aerosols, this is to update coding of the aerosols. Many people, the aerosols are interacting with very many processes in the climate system, in the atmosphere, as you can see on the bottom, like aerosol cloud interactions, radiation, chemistry, and so on. But in the code, there's a lot of dependencies on what specific aerosol scheme is used in the model. And so it makes it really hard for developers to add a new aerosol scheme or change something, since they have to go through all these different code bases to all the different processes. And what we're doing here is to separate and identify and separate the aerosol model specific calculations in the host models, and then pull them out in just specifically one place to keep the interactions with the host model really independent of the aerosol model, which then makes it much easier to add new aerosol model and code development for this. Like, we also eventually moved to CCC compliance with this development, and this is done together with Matt Dawson, Francis Witt, and many others that work on this. Next slide. And more on this is also that we do have other aerosol options in ChemChem, the Mosaic addition to the gas aerosol exchange. And you also heard about the Hdma development, the sectional aerosol models. Those will then be integrated with the flexible aerosol interface into the development version. Next slide. And then I want to also mention what was mentioned before from Nick. We do have the very short-lived halogen implementation. Rafa will talk about this on Wednesday. And I will give an example in a couple minutes. We also have developments on diurnal cycle and vertical emissions, especially looking at the effects of fires. And I will not show much to this, but there's also developments right now on the new TUVX photolysis scheme that will be implemented online eventually in also CESM. Next slide. So this is the example on the very short-lived halogens. Very short-lived halogens are very important for chemistry, also for stratosphere chemistry. This slide highlights also the importance for integrating this new chemistry for climate. In particular, adding very short-lived halogens will change the methane lifetime. And what you can see here on the middle plot is that surface methane loss is changed on the bottom, in particular when we're adding these new very short-lived halogens. It will decrease methane loss over the oceans and increase over land. So you can see on the slide that methane lifetime is actually substantially increased with the addition. And this is from a paper by Lee et al. In 2022, presented by Rafa on Wednesday. Next slide. So we're also working on Musica version 0 further evaluation and new grids. And one example is also that we are now comparing this in more detail with existing WRF or new WRF chem simulations. And there is a talk by Wen Fu Tang on Wednesday. And Mary Bath is also already spearheading work where we are running ChemChem with MPAS in the next slide. So here, the first tests with ChemChem MPAS have been done also over the Asian summer monsoon to support the ACLIP campaign. And we have, they have already performed simulations with a 1.6 to 3 kilometer grid mesh over 32 vertical levels and with full chemistry. And further tests are ongoing right now to look at different number of nodes, check performance, and so on. And eventually this will also move to the workhorse model, the 58 level model, and 1 month simulation is planned, as well as evaluations with WRF and spectral element simulations. Last slide. And this is just, again, we have our joint working group meeting or session with the whole atmospheric session on Wednesday morning. And here are some links for you. Thank you.
Thank you very much, Simone. And we'll move to now to Ocean Model Working Group, and we'll get an update from Frank Bryan. Frank, please go ahead.
Thanks, Gokhan. I'll be presenting on behalf of the working group and my co-chair, Ian Grims from the University of Colorado, along with the Ocean Working Group liaisons, Gustavo Marquez and Alper Altuntas, who've done most of the heavy lifting on the things I'll be sharing with you today. So as the other working groups have discussed, much of our work over the last months and year have been focused on developing the ocean component model for CESM3. And in our case, that is not really just a refinement of an existing model, but complete replacement of the ocean component model. As those of you who've been around CESM for a while know, we're transitioning from the POP model that we've been using for almost 20 years to the MOM6 ocean general circulation model. So this represents the largest change in the ocean component model since the inception of CSM. So it's been a big job, and we've been working on it diligently for the last couple of years. And I think, as has been hinted at in several presentations earlier today, we're starting to see some light at the end of the tunnel and having a viable, fully coupled model using MOM6 as its ocean component. So our focus has been primarily on what folks have been describing as the workhorse model. That is a model that we feel is applicable to the breadth of CESM climate science and is usable in terms of resource requirements by a broad range of the CESM science community. And that means, for the moment, that at this point in time, we feel that that still requires that we remain in the eddy parameterized regime. There are certainly some advantages, and Steve, for example, in Steve Yeager's talk this morning, we see distinct advantages in the quality of the simulation as we move to higher horizontal resolutions and begin to resolve the ocean mesoscale, but the resource requirements are still daunting. So we pushed the resolution up a little bit to nominally 2/3 of a degree, but that still requires a parameterization of the ocean mesoscale. But the nature of the grid is somewhat higher grid quality, in the sense that it's a more isotropic and homogeneous grid than under the POP 1 degree grid. Perhaps the most distinguishing characteristic of the MOM6 model as compared to POP is its representation of the vertical structure of the ocean. So POP was a Z-coordinate grid with step-like topography fixed to the vertical resolution of the model, whereas MOM6 uses an arbitrary Lagrangian Eulerian representation of the vertical structure that gives you tremendous flexibility in your choice of target coordinate. And up to this point in time, we've been pursuing in parallel two choices: a Z-like coordinate similar to POP, along with a HICOM isopycnal hybrid coordinate that we've inherited both of those capabilities from the basic MOM6 model. In both cases, we're pushing the vertical resolution near the surface up considerably, with a modest increase in the total number of vertical levels. I should say, in this table here, comparing in the right-hand column, the items in sort of the lighter blue font are the things that we're actively working on at this moment as new developments. And so the first of those is a completely new formulation of the target grid being developed by Scott Bachman, where the choice of vertical levels is set to optimize the resolution of the lower vertical baroclinic modes of the ocean. That would, in principle, improve the representation of instability processes and wave propagation. in the ocean, offering a better representation of variability. So that is working going. Another distinguishing characteristic of MOM6, as we're using it in CSM, is its treatment of the surface boundary condition on fresh water, the way that we exchange fresh water with the other components of the Earth system. So in POP, we did not, in fact, exchange fresh water. We had what is referred to as a virtual salt flux. So where it was raining, rather than adding fresh water, we would remove salt in order to affect the same dilution effect from rainfall. There are corollary consequences. In addition to being a more physically realistic representation of the mass balance of the ocean, there are implications for the energetics of the system. This is something Gokhan touched on this morning, that require more careful coordination with the other components. And we've begun addressing those with the atmosphere and the sea ice model. That took some time, and we think we have a workable solution for the time being there. So that's sort of the basic dynamical core of the model. In addition, we basically have touched every aspect of the physics relative to what we've been using in POP for the last several versions of CESM. So in the vertical mixing, we are still using KPP through the CV mix library, but we're much more, we're pursuing a tighter coordination and interaction with the surface wind wave processes. I'll come back to that in a moment. In the representation of mesoscale eddy stirring and mixing, we are using a mesoscale eddy kinetic energy-based closure. This gives us a foundation to take advantage of developments coming out of the NSF NOAA climate process team working on that area. In addition, it gives us a foundation for incorporating new parameterizations of the inverse cascade of energy, that is the backscatter from mesoscale processes back to the large scale. And Scott Bachman and others are working on those aspects of that. In terms of the momentum closure, we are now more tightly integrating the mesoscale tracer mixing with the viscosity closure. So that closure is also based on the mesoscale eddy kinetic energy. Just briefly, the solar penetration scheme we had been using in POP is ill-suited to vertical resolutions of the 1 meter vertical resolution range that we're targeting. So we've replaced that. And the overall numerics in the POP model are many decades old, and the MOM6 framework offers more modern alternatives in all respects for that. And another area, just other aspects of the parameterizations and subgrid scale processes are also being addressed. Some new work looking at the effects of nonlinearity in the seawater equation state and how that affects the evaluation of pressure gradients, ice spiegel slopes, et cetera, is being worked on by Ian Grooms and his group. And finally, we're fully committing to the new OPSI coupling infrastructure in MOM6, and much of the new developments I've touched on with respect to coupling to other components is only being supported in the new OPSI cap. So next slide. So this, as Gokhan mentioned this morning, and I alluded to, we've begun running fully coupled simulations with MOM6 in the last couple months. And we've started within the ocean group, we started basically using out of the box CAM6 finite volume in our testing as a starting point. And we're gratified that we've been able to run century-long fully coupled simulations with resulting climate bias and climate drift at least as good and better than what we've been able to achieve with POP. I'm only showing a output from a sample from a case with the Z-star vertical coordinate here, but consistent with our work in the forced ocean model and also consistent with GFDL's experience. We have somewhat lower drift and thermocline warm bias in the temperature field with the hybrid coordinate, so that the discretization errors are still an important component of our model systematic bias at this resolution. The panels on the left side there show that many of the familiar biases we've been seeing, for many decades now in models in this resolution regime remain. This is really kind of endemic of this resolution regime. For example, the poor separation of western boundary currents, the curved shield in the Gulf Stream, you see the warm biases near the continent, the poor simulation of the North Atlantic current with the cold spot out there south of Greenland, and the warm biases in the eastern boundary upwelling, and particularly the Benguela current system, unfortunately still plague us in the MOM6 simulations, and we'll continue to work on that as new ideas about parameterization, like we heard from Laure and Galen, come to the fore. Gustavo will be presenting a more extensive assessment of these coupled simulations in the working group meeting tomorrow morning. Next slide. So while the majority of our work and resources have gone into this standard workhorse configuration, we have been, as time allowed, working with partners in the community and developing alternative configurations within the CESM framework. So all of these examples here I'm showing, you build out of the CESM repository exactly the same way as you build a fully global case at the standard resolution with a create new case, in some comp set. So examples of that are contributing to the CESM idealized modeling suite with aquaplanet-like configurations. This was work that was pioneered by Jianing Wu during her graduate studies and while she was visiting here. We are running, as time and resources allow, eddy resolving cases. This is an example basically replicating the POP 1/10 degree case. And you can see the surface eddy kinetic energy is reproduced quite similar to POP. And also regional downscaling. This is a capability that we've had taken some steps towards, not with POP, but with ROMs and WRF coupled simulations in the past, trying to somehow couple to POP. That's always been rather awkward and very difficult for us to support because it's a completely separate code base. Here we're taking advantage of a growing community of users using MOM6 and regional applications and leveraging that and being able to bring that capability into the CESM framework. Next slide.
You have about 1 minute, Frank.
Okay, next slide. So here are two examples of that, one being an Eastern Pacific simulation at 1 kilometer driven by output from a impasse atmosphere. That's a new dynamical core capability in CSM. And on the right, a 1/4 degree tropical Atlantic simulation. And Giovanni Ciejo from CU will be presenting on the latter configuration tomorrow during the working group meeting. Next slide. And as I mentioned, we're working, we have a much more focused effort in wind waves. We've begun working much more closely with EMC with the WaveWatch 3 model. In the past, we've been using a snapshot of WaveWatch 3 that is very much out of date. We're now forking right out of their main repository and sharing a neuropsy cap with them. This will allow us to collaborate much more closely with them. And then we're collaborating with Brandon Reichel and others at GFDL on coupling those the waves to the ocean circulation both through the dynamics and the parameterized processes. Next slide. So I guess you'll have to go back to the video to check all these links, but basically we've the documentation for CESM as a CSM component and the technical documentation of MOM6 itself are expanding and available. We at CSM are hosting the MOM6 forum for all MOM6 users, not just CESM, within the CSM bulletin boards. And we have a video tutorial series available on through the CSM events page. And again, we'll be meeting at 8:30 tomorrow morning. So I think I'll just go ahead and end it there. Go ahead.
Thank you very much, Frank. So we'll move to Biogeochemistry Working Group, and Matt Long will be presenting, I believe. Matt, please go ahead.
Thanks, Gokhan. I'm Matt Long. I'm a scientist at NCAR. I am a new working group co-chair, presenting on behalf of my additional VGC working group co-chairs, Gretchen Keppel-Alex from the University of Michigan and Abby Swan at the University of Washington. Next slide, Gokhan. So the BGC working group is somewhat unique in that we are not directly responsible for a component model development process, but rather really focused on the coupling or the coupled system, and in particular, the cycles of carbon and nutrients within the coupled system. So this talk just aims to highlight a few key results that have come to bear or to light over the past year or so, and provide pointers to the ongoing work. This slide shows results provided by Charlie Coven that are emissions forced coupled model integrations, exploring the lags and symmetries of the climate system response to carbon dioxide removal. The panel on the left illustrates the CO2 emissions trajectory used to force the model in black, and the response of the various carbon cycle components within the Earth system, including the atmospheric growth rate. The panel on the right shows a collection of response variables in a normalized framework. So these are the anomalies relative to a baseline. And a couple of key features to point out here are that the temperature response tends to slightly lead the changes in emissions, but that by and large, the temperature response remains proportional to the cumulative CO2 emissions, with the exception of the end of the record, where you can see that the green line is the global mean temperature or surface temperature response, really departs from this cumulative emissions ratio. And that has to do with feedback within the Earth system, specifically changes in the AMOC, a strengthening of the Atlantic meridional overturning circulation towards the end of the run. If you want to know more about these results, you should contact Charlie. The email address is there. But these are very relevant integrations in the context of leveraging the Earth system model framework to explore managing mitigation. Next slide. This is work that I've been involved in collaboration with Galen McKinley at Columbia and Amanda Fay. What we've done here is run the CESM-1 large ensemble, but censored the Mount Pinatubo eruption forcing from the integration, explicitly to explore the influence of that event on the ocean biogeochemistry fields. That was our focus, though the integration surely has applicability for other components of the Earth system, like John Fasulo is looking at sea level rise, and I think that there's probably interesting dynamics in the precipitation fields. These plots on the left show the full field response, where the simulation in blue is the control, the full CSM large ensemble, and the red is our new integration without the volcanic eruption. The plots on the right demonstrate, or just can show the anomaly. And what you can see is that the cooling associated with the volcanic event causes a large uptake of, or generates a large uptake of ocean oxygen and CO2. And so we're currently working on a manuscript to describe this in more detail. Next slide, Gokhan. This is work that was contributed by Abby Swan and her student Claire Zarakas at University of Washington. This is exploring the role of the parameterization of plant functional types in CLM in controlling global mean temperature. And so these are leveraging parameter work that has been done at NCAR. And the main point here is that by manipulating the parameters of that define plants in the land model, it's possible to generate a range in global mean temperature that is about a third of the spread in CMIP5 models. The implication here is that there is a role for focused attention in the context of tuning the coupled system on sort of these joint sensitivities between model components. And so, if the definition of plants in CLM has a strong role to play in the climate simulation, we really need to be focused on that coupled interaction. Next slide, please. This is work from Yasir Edenbar at Scripps, and he's conducted an analysis of the CSM1 single forcing large ensemble, specifically looking at secular trends in the ocean oxygen inventory. And the plot on the left shows basically the red line is the simulation, let's start with the black line. The black line is the total simulation inclusive of all forcings. The blue line is the trajectory of the system if the aerosol forcing is excluded. And the red line is the trajectory of the system if the greenhouse gas forcing is excluded. And so this analysis provides probably the first quantification of the role of aerosol forcing in mitigating ocean deoxygenation. Next slide. In Steve Yeager's talk and in Gokhan's talk, made reference to the recent seasonal to multi-scale, multi-year prediction experiments. And I'd just like to point to a few key biochemistry results in Steve Yeager's recent paper summarizing those runs. These figures illustrate the potential predictability in Siberian GPP, as represented by the anomaly correlation coefficient in the upper right panel and the anomaly time series, or sorry, in the upper left and the anomaly time series in the upper right. Next slide, Gokhan. Steve's paper also includes this figure that illustrates the potential predictability of certain key oceanographic BGC relevant fields, specifically net primary productivity on the left, carbon export on the right, and zooplankton carbon export in the center and zooplankton carbon on the right. The reason or our motivation for focusing on these fields in particular is to try to make connections to fisheries relevant predictions, considering the role of bottom-up climate forcing and driving variations in potential fishery yields. Next slide. So another focus over the past year or so has been on conducting global high-resolution experiments with CESM equipped with biogeochemistry. And here are two companion movies that Yasir provided showing the diatom chlorophyll concentration and sea surface temperatures in the equatorial Pacific. These are, there's a few groups around the world who have done these kinds of integrations, but they're big calculations, and so they're infrequent. So these are a tremendous community resource. Next slide, Gokhan. Yasir has been using these integrations to investigate the mechanisms ventilating the tropical Pacific oxygen minimum zone. And here is an illustration from his analysis demonstrating the role of tropical instability vortices in driving the subduction of new well-oxygenated waters into the ocean interior in the equatorial Pacific. Next slide, please. Okay, I'm going to transition a little bit to some of the model development efforts. I just want to point out that CESM is now includes MARBLE. This is the Marine Biogeochemistry Library that is a modular implementation of ocean biogeochemistry. We have MARBLE implemented in POP2 ocean model, of course, but also the exact same code base is coupled to MOM6. And that really enables a degree of flexibility in terms of supporting development paths. We're also working with groups at UCLA to implement MARBLE in ROMs, and DOE has implemented MARBLE in E3SM. And so this modular architecture can potentially provide a powerful way to leverage communities of practice around a single model component. Next slide. Some ongoing work in Keith Moore's group has focused on implementing variable phytoplankton stoichiometry in the model. And these are results, or a slide contributed by Nicola Weissman from UC Irvine, just illustrating the parameterization, this sort of stepwise linear parameterization for algal stoichiometry. And this is a really important control on the distribution of nutrients. Next slide, please, Gokhan. In particular, different phytoplankton functional types are characterized by different elemental stoichiometries in terms of their growth requirements. And this is an important control on the elemental stoichiometry of the export flux and a constraint on surface nutrient distributions. So if you're interested in this topic, I'd encourage you to check out Nicola's talk in the Biogeochemistry Working Group on Wednesday. Next slide. Another focus has been on coupling MARBLE to a fisheries model. And here are some preliminary results submitted by Colleen Petrick at Scripps, illustrating the output of her fish model, Feisty, applied in an offline manner to a POP forest ocean ice hindcast. And so this is really just a demonstration of a proof of concept here, showing that we see climate-driven variations in the global fishery biomass, as well as geographic variations and structure in the climate forest variability in fisheries biomass. So this is an exciting new application of the Earth system modeling framework, extending the formulations that we've developed in the context of carbon cycle science to support decision support in the context of fisheries. Next slide, please. To support that effort, we've invested in an expansion or reformulation of the marine or the phytoplankton functional types that are in MARBLE. And here's an illustration, beautifully hand-drawn illustration from Kristen Krumhart of the new ecosystem structure in MARBLE. And our hope is to move towards this sort of two zooplankton group configuration as the default configuration of marble used in CSM experiments. Next slide. And so here are just some preliminary results from a global eddy resolving integration showing this strong variation in micro versus mesozooplankton. And this type of variation in the size of prey for fish will have a big impact on our ability to model fisheries ecosystems with high fidelity. Next slide, and that's all I have. I appreciate the opportunity to speak to you, and feel free to contact myself or my co-chairs for follow-up questions.
Thank you very much, Matt. So we'll move to now Polar Climate Working Group, and Hansi Singh will be providing the update. Hansi, please go ahead.
Hi, thank you so much for having me. Elizabeth, could you just give a little click, please? Yes, thank you. So before I begin, I'd like to remind everyone on behalf of the Polar Climate Working Group leadership, myself, Marika Holland, my fellow co-chair, and David Bailey, CEIS Consortium liaison, that Black Lives Still Matter and happy Pride, because it's that time of year again. Next slide. So today, I'm going to tell you about a couple of sort of major things that the Polar Climate Working Group is doing. So the first is in the realm of model development, in particular, the road to CEIS 6. So on the road to CEIS 6, there is a lot of work regarding improving coupling, in particular, coupling to the ocean, coupling to the atmosphere. There's a lot of exciting new physics to talk about, as well as the potential for incorporating a lot of new state-of-the-art observations into the new version of CEIS. So first, I'll tell you about that. And then the second thing is science highlights, which reflect the science priorities of our working group members. So this includes the effects of winds and circulation on sea ice, the effects of aerosol forcing in the Arctic region, sea ice predictability, as well as actionable science in the Antarctic. So I will cover all of these areas today in this kind of flash overview talk. Next slide, please. So to begin, I'm going to tell you a little bit of about model development work that's going on. So here we are going from CEIS 5 to CEIS 6, and so there are many things to do here. The first thing, things to do that have already been done actually just over this past year by our wonderful Dave Bailey, who has been spearheading all of these model development efforts, is to improve coupling. And we would like to improve coupling, first of all, by including interactive salt fluxes with the ocean. So currently we have in CEIS 5 mushy layer thermodynamics. This means that the ice has a salinity to it. It doesn't have a fixed salinity as used to be in the previous version of the model. And so because of that, now we can actually couple the salinity to the ocean. And so this is work that has already now been done by Dave. And so that is now available in the model, and there is work going on in terms of testing it in terms of model climatology and variability. So the big challenge here, of course, is that now freshwater and brine, they used to be calculated in POP, and now they have to be calculated in CEIS. And so once again, this has been done, and testing is going on regarding the climatology over the polar regions. And so, of course, because the polar regions are so important for deep water formation, we can, understand that having the right salinity in here is crucial for understanding, for example, Antarctic bottom water formation and the circulation in the deep south. So the second thing is having consistent heat fluxes. So we would like to have more consistent heat fluxes between atmosphere, ocean, and ice. So when I talk about these consistent heat fluxes currently, for example, the temperatures of rain and snow that fall on the ice are construed to be 0 degrees. And of course, we know that that's not always true. And so this has to be corrected. And furthermore, temperatures of meltwater and brine that are coming from the ice are once again assumed to be 0 degrees, and that also is not true. So, there is work that is currently being done and tested to get these fluxes to be more consistent with the physics and to improve energy conservation within the model. And then finally, I have this nice picture of the Arakawa Sea Grid. CEIS 6 will have the Arakawa Sea grid right there. And so this is much better for the physics and dynamics in the model. This is work that's going to be completed near the end of the summer in an exciting hackathon that Dave will be participating in for the CEIS consortium. And so this will also be in the new CEIS 6. And then finally, in terms of coupling, please keep in mind that CEIS 6 uses NUOPSI. It is only compatible with NUOPSI, not the old version of the coupler. Next slide, please. Okay, so there is some exciting new physics that will be in CEIS 6. So what is this physics? So first of all, there's going to be land-fast sea ice. This is sea ice that grows on the coasts and ends up growing so thick that it becomes anchored to the ocean floor. And so there is going to now be a parameterization for this type of ice with the new CEIS. Furthermore, there's also a sea ice flow size distribution. This is work that was pioneered by Letty Roach and colleagues a few years ago, and now it is in the model. It is in CEIS 6. Once again, this is being currently tested in terms of model climatology. And then finally, we are going to now have interactions between the sea ice, and in particular, the sea ice flow size and ocean waves. So why is this important? Well, so below I show here a figure from Blanchard, Wigglesworth et al. 2021. And so in this paper by colleagues at the University of Washington and at NCAR, they looked at the sea ice area variability in CMIP 6, shown in the gray lines, and in observations, shown in black. And you can see that there's a huge disparity there. Literally, the observations have so much more variance than the models. And it is really thought that this is probably because this variance is highly dependent on the short timescale interactions between sea ice and waves. And so we really hope to improve the model and get it looking more like observations by including these short timescale interactions. Next slide, please. So finally, we hope in CEIS 6 to have at least some additional bells and whistles where we have incorporated observations, namely those from the latest Mosaic mission, into model physics. So the areas that we hope to incorporate include improvements in the albedo, improvements in the treatment of snow, namely to acknowledge that snow is heterogeneous, that it gets redistributed through winds, that it ages, and that rain does fall on snow and impact the snow. And furthermore, to improve melt pond parameterizations. So these are all goals. CEIS 6 might not have necessarily all of them, but we hope to at least have some. And finally, I haven't mentioned it yet, but we really hope to have at least some biogeochemistry in the sea ice if there are resources to be able to do so. So that is yet another way that we hope to incorporate better physics into CEIS 6. So now I want to talk about some research highlights, which represent the research priorities of the Polar Climate Working Group. So first, I'd like to talk about the interactions of sea ice with circulation and in particular surface winds. So here I show work by Letty Roach and Ed Blanchard Wigglesworth that is currently in review. And in this work, CESM1 surface winds just over the Arctic domain were nudged to observed winds. And so then you can see the nudged runs are shown in red here, and the observations are shown in black. And the CESM large ensemble is shown in blue. And you simply see that when you nudge the surface observations, the surface winds to observations, that you get much better short timescale agreement between the model and observations. And you see this on the left in the surface temperature, and on the right, you see it in terms of the Antarctic sea ice, the Arctic September sea ice extent in particular. It turns out that this works very well for September. It doesn't work as well for other times of year. Oh, and I just got this exciting comment from Letty saying that their paper has now been accepted. So congratulations. Always nice to hear these exciting updates live, I guess. Okay, next slide, please. So in addition to understanding how sea ice and surface temperatures change, Jinghua Ding's group at UC Santa Barbara, along with Axel Schweiger and Mike Steele at the University of Washington, have a study in which they have nudged surface winds to observations, also in the CESM1 large ensemble, but in this case, they did not apply ramping forcings as found over the historical period. And what they found here is that surface wind changes also account for at least 1/4 of the increase in Arctic upper ocean temperatures over the last 40 years, and over a half of the increase in upper ocean temperatures from 2000 to 2018. And so this is work by Jie Li et al. That has recently been published in Nature Communications. So please check that out. Next slide, please. So winds over the Arctic are expected to get much stronger in the future as sea ice declines. So colleagues at NCAR, including Alice Duvivier, Marika Holland, and Laura Landrum, have been looking at this phenomenon along with colleagues at the University of Wisconsin at Madison, including Steve Vavris. So they looked at the impact of sea ice roughness on increased surface winds. So they ran a couple of sets of experiments. One is just the CSM2 large ensemble. Another one is a similar ensemble, but with smoothed sea ice. In other words, the sea ice roughness is given to be the same as that of open ocean. And they found that when they did that, on the lower panels, you can see that the autumn 10-meter wind speed trend becomes much lower when you smooth the sea ice. In other words, the decline in roughness associated with open water accounts for somewhere between 30 to 60% of the increase in surface wind speeds with decreased sea ice. And then the other part of it is, of course, the decrease in static stability that occurs when sea ice is lost. Next slide, please. So in addition to these impacts of winds and circulation and how winds change, aerosols over the Arctic are also very important. Just last year, we heard a lot from Patricia Di Repentigny, who at that time was at CU Boulder, and John Fasulo and colleagues at NCAR regarding the impacts of biomass burning emissions variability on the subarctic and the Arctic. So in this case, myself and my graduate student, Kyle Hayblom, and Phil Rash, who's now at the University of Washington, we have been looking at mechanisms that explain why biomass burning emissions variability causes such differences in forcing depending on how it's applied. And so we ran a bunch of fixed SST experiments that looked at the forcing due to biomass burning emissions. We found that, of course, these depend on the variability of the emissions. And then if you look at the lower figure here, this shows the relationship between the aerosol burden on the x-axis and the top of atmosphere forcing on the y-axis. And you can very clearly see the nonlinearity there. So the reason why variability matters is because CSM in particular is in this very kind of nonlinear part of the aerosol to top of atmosphere impact phase space. And so you can even see this if you look at the CSM2 large ensemble, which is that little blue inset in the lower figure there. You can very clearly see the nonlinearity. And in fact, this difference in emissions, high emissions, can potentially lead up to a 2.4 watts per meter squared radiative forcing difference from 50 north to 70 north as determined by fixed SST CSM2 experiments. Next slide, please.
You have about 1 minute.
Okay. Wow. I just love talking. Okay. So in this last minute, I'd just like to highlight some work by Marika Holland and colleagues regarding sea ice predictability, and in particular, sea ice predictability in the Antarctic. And so Marika is very interested in how predictability depends on the month when the model is initialized, as well as the base climate state, whether it's initialized in 2010 or in 2030 ice conditions. And what she finds is that predictability tends to be high initially. It tends to be lost in summer, very similarly to what we see in the Arctic, and then it tends to reemerge the following winter. Next slide, please. And then finally, I'd like to highlight some really neat work on Antarctic polynyas and implications for marine protected areas in Antarctica. This figure here shows some penguins. These are areas that are super important for marine mammals and seabirds. And what she did was she looked at CSM2 through the lens of a self-organizing map neural network, and she found that patterns like, or sea ice patterns like the one with the star here, where we have large polynyas near the coast, these tend to decline. And this will have a huge implication for marine mammals and seabirds in the region, which depend on these polynyas. Final slide, please. Thank you so much for listening here, and we look forward to seeing you hopefully on Thursday morning at our joint working group session with the Land Ice Working Group. Thank you so much.
Thank you very much, Hansi. So this concludes the first 6 updates from the first 6 working groups. So we'll take a break until 2:50 p.m. Mountain Daylight Time. And we'll have we have the remaining updates at that time. Thank you again, and see you at 2:50. Will, are you there?
Yep, I'm here.
Okay, great.
Hey, I'm here too, Gokhan, when you're ready.
Okay, okay, great. We'll start in a minute or two.
Gokhan, where's your background picture taken from?
That picture was actually from Ryan. Everybody, apparently people liked it a lot, so they keep asking me about it.
It's cool.
Okay, well, let's get started slowly. Good afternoon again. And this is the last session of the day. And we will have updates from 6 working groups, starting with the land model working group. And you have about 15 minutes. If you are running late or over, I'll let you know. And then we are not taking any questions during this session. And please let me know when you need me to advance the slides. So Will, please go ahead.
Great, thanks, Gokhan. You can go ahead and advance from here. So before summarizing some of the land model working group development activities, I wanted to briefly highlight a paper that Gokhan mentioned this morning that's also in press and really underscores some of the power of the CESM2 large ensemble. And in particular, the ensemble size, its spatial resolution, the land model complexity. CLM5 is a much better model than CLM4 was. And then the requisite high frequency output that really make the CESM2 large ensemble a powerful tool for looking at climate change impacts on Earth system processes. And so in particular for this study, we looked at changes in snow and hydrological mean state, as well as changes in the variability of snow in the CESM2 large ensemble. And you can go ahead and go to the next slide. And so what's shown here is just a kind of a relatively simple explanation or illustration of changes in the model mean state. And so what's shown on the upper left is changes in SWE or snow water equivalent, with cooler colors being earlier in the historical period and later, darker colors or reds and oranges for the end of the CESM. I'm sorry, the end of the SSP 370 scenario. And then below that is changes in runoff. And this is just for a single grid cell. So you can see that this isn't new, but in a warmer climate, there's less snow that melts earlier. Really the new work that's illustrated by this paper, though, if you can advance the animation, is shown in the number of snow-free days. And so the timing of snow off really matters. And in ecosystems that are characterized by long, historically snow-covered winters, for example, in this grid cell, the number of snow-covered days is 82 days longer by the end of the record than it was in the historical period. And you can see that the trend that we're matching actually captures results from snow tail towers, which are shown in the black dots here. So snow's melting earlier and more of it's melting during the winter. So more of it's melting before that peak SWE, which is shown in the upper right-hand panel. And along with that comes changes in center timing. So the day of the year when half of the flow has gone by. So center timing is getting earlier, but it's also getting more variable. And, really the other reason I wanted to highlight this is that we're extending this work into 2 innovators projects that we'll hear about later on in the workshop. And as well as an NSF convergent research project that are starting to use community resources like the CESM2 large ensemble to help inform decision-making by stakeholders. So go ahead and go to the next slide. Another project that's kind of a major focus of the land model working group is the Ctsm parameter perturbation experiment. This is work that really was kind of spearheaded by Katie Dagon during her ASP postdoc, and then continued by Daniel Kennedy and during his ASP postdoc, and then continues on through LEAP. And so phase 0 and phase 1 of this project are finished. And Daniel will talk about what those are moving forward. And then phase 2 and phase 3 really will be kind of accelerated by partnerships with LEAP that Dave Lawrence is also a part of. And if you can go to the next part of this animation. I don't want to go into the details of the PPE, but really, I think what illustrates the power of the parameter perturbation experiment are all these spin-off projects that have come from it. So Matt Long talked about parameter uncertainty related to land-atmosphere interactions and the work that Abby Swan and Claire Zacharias are doing at the University of Washington. And I'm not going to go through all these here, but there's kind of great community interest in using the infrastructure that's built through these first 2 phases of the parameter perturbation experiment that I think will greatly improve definitely the land model, but hopefully other components of the model as well. You can go ahead and go on to the next slide. Another activity that we've been working on is this NCAR neon data exchange. And so if you're not familiar with if you're not familiar with NEON, NEON is the National Ecological Observatory Network, which is a major research infrastructure facility that's funded by the Directorate for Biological Sciences at NSF. And so the idea behind this NCAR NEON data exchange was to really broaden participation and engagement both with NEON data as well as NCAR models. And by doing that, linking the biological sciences and geological science communities through cyber infrastructure. In the real practical goals, this project aims to gap fill and format NEON observations for single point simulations with CTSM that are designed both to improve the measurements and the model. And this was a 1-year pilot program. And if you go to the next slide. So in this 1-year pilot program, we garnered some attention, and it was highlighted in this National Academies report on the next generation of Earth system science as an example of a synergy among facilities that really should be pursued in advancing Earth system prediction to include terrestrial ecosystems and biological resources. So we have a renewal proposal that's been submitted to NSF. It's somewhere in the process of going between Everett's desk and NSF. And we see this as an opportunity to really use some of the forecasting capabilities of CESM and the Earth System Prediction Working Group, as well as connections with the Parameter Perturbation Project, to also expand on larger regions around the NEON Tower and leverage some of the land model working group activities related to the hill slope model as VATES integration, along with some of the NEON remote sensing capabilities that are pretty exciting, but so far untapped. You can go ahead and go to the next slide. And along with that, we're part of this project is we're trying to bring ecologists and biologists into using tools like CESM. And so to do that, we really need to promote community engagement and access to broaden the participation of users who are able to use tools like CTSM. And so this project really, by using CESM Lab, it seeks to open opportunities for communities that typically haven't had access to advanced computing resources and that may have little modeling experience, and also extend the reach of, again, NEON data products. And so using a containerized version of CESM Lab has really accelerated this because users are able to do these single point simulations on their laptop. They don't need access to Cheyenne or other high performance computing. And so Brian Dobbins has helped a great deal in facilitating this integration of the NEON project within a containerized version of CESM Lab. I think the next part of this animation will help. And so we expanded on that just a couple of weeks ago with a CTSM tutorial. This was our first, we've done CTSM tutorials in the past, but this was our first foray into virtual tutorials. And so just a couple of weeks ago, we had 60 participants participate in this 2-day mini tutorial. For that, we used cloud computing and CESM Lab, and then had practical exercises via Jupyter notebooks. You can go ahead and go to the next slide, please. And I want to just kind of highlight this a little bit. The website, the GitHub pages is listed at the bottom of the slide. But as part of this tutorial, we really trying to create a modular and extensible set of tutorials that could be kind of made accessible and more repeatable, that were system independent, and that would really facilitate more frequent engagement with the land modeling community. And I guess this is more kind of a question. I don't know if this is potentially a model for the CESM tutorial, but potentially I think it could be. And so, we did things like I said, creating these Jupyter notebooks as pages for students to walk through the tutorial materials, as well as creating kind of live video demonstrations that are recorded and available on YouTube for people to kind of get started doing this in the first place. Go ahead and go to the next slide, please. And then I want to finish talking about some of the kind of broader efforts that we'll be pursuing for CESM 3. And so a big focus is still FATES, which is the functionally assembled terrestrial ecosystem simulator. Right now we have a global configuration of FATES that is running in SP mode or satellite phenology mode, which is kind of the first of several reduced complexity modes of FATES that are planned to be rolled out in the next year to several years. Those are being integrated with diagnostics testing for ILAM to facilitate more rapid kind of evaluation of how FATES is doing, especially compared to the kind of workhorse configuration of Ctsm that we're using now. And part of that also will involve having land harvest be active. And so Peter Lawrence, as well as other contributors with DOE labs, are working on getting land use change to work in FATES, because that's kind of the zero order prerequisite for having FATES run in global simulations. At the same time, we're also working on a number of regional applications. And so this is an example from Jackie Schumann's work, where FATES is able to capture the dynamic biogeography and biomass using fire feedbacks. And so the fire feedbacks and the distribution of vegetation, especially across the tropics, is an important feature for more disturbance-aware ecosystem models like FATES to be able to capture. And so fire determines plant survival. And Jackie's developed the Spitfire parameterization for application of the tropics, and that's being extended to work through Lawrence Berkeley National Lab across California. Some pretty exciting ways that we're able to start looking at vegetation fire feedbacks and the distribution of vegetation in a model like FATES. Next slide, please. This is kind of a catch-all for a whole bunch of other developments that are going on in FATES. And so there's work on plant hydraulics. There's, again, more work on fire and especially crown mortality, work on deciduous phenology, and just phenology in general is, I think, a key feature of FATES that still needs some attention, really all land models. But the user interface is improving. And so, again, we're working on these tutorials and Jupyter notebooks. And then the FATES team is also working on improved technical documentation. There's work to implement nutrients in FATES. There's both a coupled carbon nitrogen as well as coupled carbon nitrogen phosphorus that's active in E3SM. And we're working on implementing that into CLM. Collaborators in Norway are working on a MOS parameterization for high latitude application, which is important for both permafrost dynamics as well as hydrology and carbon cycle work. And then work that Adriana Foster's doing here at NCAR is looking at canopy turbulence parameterization, especially in mixed vegetation, since FATES explicitly represents canopy height in different patches, thinking about how that roughness length is represented both in FATES and then how that information is passed back to the host land model, in this case CLM, is an important consideration to make. And the other thing that I'll say is that I think in some ways the land model working group, it's an exciting time because there's so much happening with FATES, but there's also this challenge of duplication of efforts and things that are going into the core of CLM now that aren't necessarily being applied in FATES. And so for at least a number of, until we get FATES fully integrated into Ctsm, and that's our workhorse model, there's a number of examples of kind of this duplicated effort that's a challenge for the working group and that we're aware of and trying to address. If you can go to the next slide, it's my last one, I think. And so this is just the short list of goals that we have for Ctsm 6 and application in CESM 3. I'm just going to highlight a few of these as they integrate with some of the CAM and other groups. And so we do have this new dust emission scheme that Long Lei and Danny Leong are working on, and Danny's coming out this summer to hopefully accelerate that. There's new BVOC emissions coming from Megan, as well as ozone deposition that's supporting work in a number of other working groups. And then also we're working on getting prognostic lightning fluxes from CAM that'll integrate with the fire model in CLM and get us away from this climatology of lightning fluxes that we've been using for a number of years. So I'll leave this up, and the slides will be made available after. This is more just a resource of kind of a short list of things that we're working on. But I guess the last thing I'll say is that a number of these projects are relatively independent of one another. And so some features may only be available with particular comp sets.
Thank you
very much. Thanks.
Thank you very much, Will. So we'll continue with Land Ice Working Group, and Bill Lipscomb will be presenting.
Yes, thank you, Gokhan. I'm presenting on behalf of co-chair Jan Lennertz and liaison Gunter Legee and many others in the working group who've contributed to the highlight slides that I'll show. Next slide. So just briefly, I'm going to show some recent and ongoing results of simulations with an interactive coupled Greenland ice sheet. Also talk about some standalone simulations planned for the Antarctic ice sheet. Show some work related to increased freshwater input to from the Antarctic ice sheet to the Southern Ocean. Several paleo simulations involving ice sheets and nearby ocean circulation. And some new work involving glacier surface mass balance and dynamics in high mountain Asia. And then we'll just wrap up by talking about some plans for CESM3. Next slide. This is work by Miriam Vizcaino and colleagues at TU Delft. Apologize, there's a panel missing in the center. But the background for this is that for CMIP6, they did simulations with an interactive Greenland ice sheet with 4 times CO2, there it is, thanks, out to year 350. And wanted to continue those simulations to see with this elevated level of CO2, what's the time scale for deglaciation of the ice sheet. These simulations have been done now. It turns out that the ice sheet loses all its mass over a period of about 1,700 years, as illustrated in the lower right panel. This happens with a pretty high global mean surface temperature of 8 degrees Celsius, with values more like 15 degrees Celsius in the Arctic and Greenland itself. The margin retreat initiates in the southwest, but then proceeds rapidly in the north as well. Is very much accelerated by albedo feedback and increased sensible latent heat fluxes. And on these time scales, the negative feedback from glacial isostatic adjustment is not enough to curtail the retreat very much. Next slide. So after looking at sustained 4 times CO2, Mirren and colleagues have been looking at other CO2 increased scenarios, including 2, 2.5, and 3 times relative to pre-industrial values, with a lot of interesting differences depending on what the ultimate level of CO2 is. I'll just mention a few here. The runoff from the Greenland ice sheet is quite sensitive to where CO2 stabilizes, with much higher runoff for 4 times CO2 than for the lower values. If you have doubled CO2 sustained, then as illustrated in the lower left panel in the purple line, after the initial collapse of the North Atlantic meridional overturning circulation over the first century or two, you actually have recovery starting around year 500. As illustrated in the same plot in the gray curve, if you abruptly reduce CO2 from 4 times pre-industrial back to pre-industrial values quickly, you actually get an AMOC overshoot to above modern values before settling down again. And in these simulations, the NAMOC behavior turns out not to be very sensitive to whether Greenland is coupled interactively, that if you prescribe Greenland runoff, you see pretty similar NAMOC behavior, suggesting only a minor role for Greenland in that decline. Next slide. Then switching to the other hemisphere, this is work by Tessa Gorta and her advisor, Jan Lennertz. They've been doing experiments to look at the potential impacts on the Southern Ocean were you to have a very high-end retreat of the Antarctic ice sheet. What they've done is they've done a control simulation out to 2100, complemented by a simulation with high freshwater input associated with projected mass loss from the Antarctic ice sheet. Next slide, please. That fresh water is concentrated in the Amundsen Sea embayment, where we see the most mass loss in Antarctica today. An interesting finding of these simulations is that with that increased freshwater source in CSM, you have significantly more sea ice in the Southern Ocean, dominated by the growth of frazzle ice. And what they found is that the reason this happens is that with the increased freshwater, you not only have a fresher surface ocean, but also a cooler surface ocean. And that cooler surface traps more warm water at depth, allowing sea ice to expand at the surface. And related change is that there's a reduction of the AMOC weakening signal. This is one illustration of the importance of considering coupled ice sheet ocean effects when looking at what will happen in the Southern Ocean in the coming decades to centuries. Next slide. Several of us at NCAR are part of a collaboration on a new NSF project led by the University of Washington, looking at the response of the Antarctic ice sheet during the last interglacial about 125,000 years ago, when it's thought that most of the West Antarctic ice sheet collapsed, raising sea level by several meters. One hypothesis for West Antarctic collapse is that there was a Northern Hemisphere Heinrich event associated with Laurentide ice sheet retreat that added large amounts of fresh water to the North Atlantic, cooling the North Atlantic and warming the Southern Ocean, which you might expect could contribute to Antarctic ice sheet retreat. An initial simulation with 4,000 years of freshwater forcing to mimic the effects of the H11 Heinrich event shows that, as illustrated in the lower central panel, there's actually, while there's broad warming in the Southern Ocean as expected, when you look near the Antarctic continent at the so-called tight Southern Ocean, you see short-term cooling just off the Antarctic coast over 500 years or so, followed by a long period of slow rebound, probably facilitated by eddy transport of warmer water from the north into the region just around Antarctica. This suggests that it's certainly not a simple matter of just warming the Southern Ocean that's going to lead to Antarctic ice sheet retreat, that there may be other factors going on that would have to be explored with higher resolution models or with coupled models. Next slide. Gokhan mentioned the study this morning. It was just recently published in Nature Geoscience. This is by Marcus Lewistrom and colleagues. In previous work, he and others found that they could simulate using CSM coupled to the community ice sheet model, Northern Hemisphere ice sheet inception around 116,000 years ago, following the last interglacial. They can get an ice sheet to grow in the Canadian Arctic and in parts of Siberia. But in some cases, we're not able to get ice to grow in other regions where it's thought to have actually grown, such as Scandinavia. And what this study shows is that initially, ice sheet growth is inhibited in Scandinavia because you're close to warm waters of the North Atlantic. But if a growing North American ice sheet should be associated with closing of ocean gateways in the Canadian Arctic archipelago. And if you add that to the model, then you find that there's a diversion of fresh water from the Canadian Arctic east of Greenland. And this leads to freshening of the North Atlantic, sea ice expansion and cooling. And that climate change in the regional North Atlantic does support Scandinavian ice growth, as illustrated at the right. This is the sort of effect that could be important for other paleoclimates as well, where ice sheet growth and retreat can be associated with reorganization of the ocean circulation, which in turn further modifies ice growth and retreat. Next slide, please. One more paleoclimate study also mentioned by Gokhan this morning. When we do simulations of future ice sheet evolution, we often prescribe ice sheet basal roughness conditions to try to get a good match to observe ice sheet speeds. But on longer paleoclimate timescales, where we don't have the same sort of observational record, and we're trying to simulate things more realistically over periods of millennia, we don't have the option of just prescribing things. So we want to have realistic enough physics to actually put ice streams in the right place for the right reasons. This study by Sarah Bradley is a big step in that direction. Sarah has shown that simulating the North American ice sheet complex, the last glacial maximum, if you include a combination of realistic bed topography and subglacial ice sheet hydrology and basal till, which is weak near the southern margin where it's thought to have in fact been weak, you can simulate ice streams that are in good agreement with the paleo record throughout the ice sheet. This is with runs with standalone CESM, but as I'll say more later, we're now able to do runs with paleo ice sheets, including the Laurentide, fully coupled with CESM. Next slide, please. Some of you may be familiar with the ISMIP-6 ice sheet model under comparison project, sea level projections, which are based on standalone ice sheet models run for Greenland, Antarctica, using ocean atmospheric forcing derived from atmosphere-ocean GCMs. A couple of years ago, a paper came out with analyzing results from ISMIP-6 Antarctica, showing interesting offsets and large uncertainties in Antarctica associated with ocean warming, raising sea level, combined with sea level falling relatively as a result of increased snowfall. In those simulations, which ended at 2100, a lot of interesting things were just beginning to happen around 2100. So the ISMIP-6 is now extending those experiments, and CESM, along with other ice sheet models we're participating, several AOGCMs have been run out to 2300, including CCSM4 and CESM2, are providing this surface mass balance and ocean thermal forcing. One of the interesting things here is that the different AOGCMs show quite large and varied responses to the high CO2 levels. For example, illustrating the lower left panel, you can see the Antarctic surface mass balance anomaly relative to present day evolving between 1950 and 2300. And the red curve showing a big increase in negative surface mass balance is actually CESM2. CCSM4 has a smaller increase. So this is going to lead to some, obviously some big changes in what happens to the ice sheet on that time scale, and further raises the question of how do we understand the differences between this large negative SMB for CESM2 compared to the smaller changes seen in other AOGCMs. Next slide. We're also beginning, after an ice sheet focus for most of the last few years, we're beginning to think more about mountain glaciers because of their importance, not just for sea level, but also for regional water security. High mountain Asia, for example, contains close to half of the Earth's 200,000 glaciers and is an important part of the water supply for several hundred million people downstream in East and South Asia. This is a collaboration with René Weingard, now in Utrecht, working with Adam Harrington and others in CGD. We developed, using the spectral element dicore, so-called High Mountain Asia VR7 grid, where resolution is as fine as 7 kilometers over High Mountain Asia. René has now looked at 2 20-year simulations. The second one was informed by the first in terms of updated glacial cover and some new tunings in CAM and CLM. In the central panel toward the bottom, the blue line shows the surface mass balance simulated over that 20-year period. Exactly, thanks. So we're now less negative than the initial run, but we're still more negative than the observational estimates, which are shown at the top of that panel, indicating that we still have some work to do. It turns out to be quite challenging to simulate the surface mass balance on these small scales, even if the atmosphere model is able to resolve those small scales. So we have some more work in looking at how CTSM parameterizations, for exactly, are interacting with the atmosphere. Next slide, please. Related work, we're now beginning to run CESM as a glacier model, not just as an ice sheet model. CESM is typically run at a resolution of around 4 kilometers for ice sheets. To resolve glaciers, we have to go much, much finer to around 100 meters. So we're now working on this for High Mountain Asia and other regions. Initial results for a sub-region of High Mountain Asia from the Nepal Everest region are promising. We've been able to do a spin up where, with some tuning of surface mass balance and basal friction parameters, we're able to produce a surface velocity field that's in good agreement with observations, and also where the glacier volume is in good agreement with modern observations and estimates. And we're now in the process of extending this work to much larger scale, which has its own challenges of scale. And we would like to contribute these results to the Glacier MIP3 project, which is looking at glacier evolution in the next several decades to a few centuries. Next slide. So for CSM3, the big change compared to CSM2 for land ice is that instead of being able to just run coupled to Greenland, we'd like to be able to run CSM coupled to dynamic ice sheets anywhere, including Antarctica and including paleo ice sheets. So thanks to work by Bill Sachs and Mariana Verkenstein primarily using the NUNU-OPSI coupler, we now do have support for running Antarctica out of the box and for running multiple ice sheets in one CSM simulation, which we plan to support with the CSM3 release. And as I said, we also want to increasingly use CSM for studies of mountain glacier retreat and regional water security, in addition to ice sheets and sea level. Next slide. So a lot of developments underway. We're aiming for a release of CESM version 3 by about a year from now, with a number of ice sheet physics and dynamics changes related to the velocity solver, sliding laws, basal hydrology, calving. We're also working on some coupling changes in addition to running with multiple ice sheets. As other components begin to support water isotopes, that's something we'd like to do in CESM as well, especially given the importance of the water isotope record for paleoclimate change. We're also, Gunter and Kate in particular, our liaisons, are working in developing new grid generation and mapping tools to support the community, supporting CESM grids that go down to resolution of 1 or 2 degrees for whole ice sheets, and also developing a comprehensive land ice diagnostic package. Next slide. So I just wanted to conclude by showing our contact info. I wanted to thank Jan Lennertz, who's been the external co-chair for the last several years and is now rotating off. And I wanted to acknowledge Miran Biscano, who's going to be the incoming co-chair starting this summer. As always, let me or the liaisons know if you have questions, and please join us for a joint session with the Polar Climate Working Group on Thursday morning. Thank you.
Thank you very much, Bill. We'll move on to now Paleoclimate Working Group, and Zhang Zhu will be giving the update. Please go ahead.
Thank you, Gokhan. Hello, everyone. I'm Zhang Zhu. Next slide, please. As you may already tell, I'm a new co-chair for the working group. And we also have 2 other co-chairs, Samantha Stevenson and Ran Feng. And I also want to use this opportunity to thank the previous co-chairs for their contribution. Next slide, please. So I want to start the updates of the science projects from the Paleoclimate Working Group by reminding people the science and the research goals of the Paleoclimate Working Group. So it's easier to describe our day-to-day research activity by looking at the Earth's temperature evolution during the past 65 million years and several hundred years into the future. That's the time series plot we are looking at now. And for the Paleo Working Group, we perform paleoclimate simulation using CESM with the goal to investigate how the Earth's system responds to external forcing and how the different components interact with each other. There are 2 major advantages of this paleoclimate approach. Firstly, we have a very large magnitude of temperature change or global mean temperature change. So from the plot, you can see that the past global warming during the past 60 million years could be as big as 14 or 15 degrees C, higher than the pre-industrial temperature. And the global cooling could be as big as 6 degrees C in terms of global mean. So we have a big climate change signal. So the second major advantage is that for paleoclimate, we have real world data from the geological records to provide us this out of sample assessment of Earth system models and to contribute to the model development. Next. Here is an example about recent Paleo Working Group research. And many of you may know that CESM2 has a much higher equilibrium climate sensitivity than the previous generation of CESM models. And it is critical to figure out whether the high ECS is realistic. So the paleo group, working with other community members, we perform a paleo simulation of the last glacial maximum and the greenhouse climate of the early youth. And we find that the simulated glacial cooling is too strong than the proxy data, and the simulated greenhouse warming is also too strong than the proxy suggested data, proxy suggestion. Combining these two pieces of information, we suggest that the high ECS of CESM2 is unrealistic. Further, using the LGM information as a benchmark, we developed this paleo-calibrated CESM2. That's the cyan in the plot on the left and on the right. So this new configuration simulates much more realistic LGM global cooling than the standard CESM2 and a much lower equilibrium climate sensitivity. This new configuration well matches the present day observations, including the 20th century warming. And when we use the new configuration to do future projection, the projected warming is about 10 to 15% less than the standard CESM2 at 21,000. Next, please. So now with a more or less realistic LGM simulation using CESM2, we can really take advantage of this comprehensive representation of the stratospheric dynamics and chemistry using the Hdma. So here we work with the atmosphere chemistry observation and modeling lab colleagues. We perform one of the first fully coupled LGM simulation with the high top atmosphere and interactive chemistry. This work is important because for decades in the past, the models participated in the paleoclimate model in the comparison project. They all used the low top model without this comprehensive simulation of stratospheric dynamics and atmospheric chemistry. So the left plot here shows the LGM ozone change in our coupled CESM2 Hdma simulation. And you see we have substantial ozone change over the lower stratosphere and also in the troposphere. So if you use a low top model, you will miss this ozone change and then the associated changes in radiation and dynamics. The figure on the right shows the LGM cooling. That's a difference between the parallel Wacom 6 simulation and Chem 6 simulation. So fully coupled simulation, one with high top model, the other with low top model. Interestingly, you see that these high top processes have little impact on the tropospheric temperature and surface temperature. So the difference between the two configurations is less than 1 degree C, and in general, less than 5%. This has implication on the paleo modeling community. It tells us that the direct impact from the stratospheric dynamics and chemistry for the glacial interglacial cycle might be small, and it's sufficient to use the low top model. Next, please. We are also working on a paleoclimate perturbed parameter ensemble in Chem 6. This is a cross-working group collaboration with Andrew Gettleman and Trudy Hdma from the Atmosphere Model Working Group. The objective is to study the state dependence of the cloud feedback in the Earth's history. So again, looking at the global climate evolution, the question we want to ask is how do the cloud feedback depend on the background global climate? And conversely, how there might be a two-way interaction so the cloud feedback can help shape the global temperature change and their spatial pattern. Leveraging the PPE framework, we can investigate the parameter uncertainty and hopefully to identify robust mechanisms responsible for any state dependence. Next, please. So the left is the current model setup, thanks to Andrew and Trudy for their years of planning and hard working. So different from them, we are using the 2-degree CAM6 with the paleofixes because we are looking at extreme climates. And we perform 250 ensemble members to sample changes in 45 parameters. And for each ensemble member, we run 5 years of simulation. So we run atmosphere-only simulation with prescribed sea surface temperature, so pre-industrial SST, and uniform global cooling and global warming, so -4, +4, all the way to +16K. This very wide temperature range is designed to cover the global temperature change during the past 65 million years, so to cover both the warm and the cold extremes. The plot on the right shows the cloud feedback relative to the calculation using PRSST +4K experiment. So this way we can highlight any state dependence in the cloud feedback. Let's start from the black dots. So looking at the leftmost 2 dots, you see that compared to the +4K, if you impose a -4K uniform cooling, the cloud feedback is not that different from each other. And then if you impose an 8-degree global warming, you start to see this increase of global mean cloud feedback with warming. And this increase is particularly clear if the uniform warming is above 12 or even 16K. So this increase, you can see the magnitude is about 0.6 or 0.7 watts per meter square per K. This is huge. If you use this simple ECS calculation and plug in the changes in the cloud feedback, this increase can cause the equilibrium climate sensitivity to increase from 4K all the way to 10K if we assume the feedback strength of the other feedbacks stay unchanged. So it is critical to figure out whether this is robust and what's the physical mechanism for this large state dependence. This is critically important for understanding past warm climate and anticipating the potentially long-term future warming. And the gray boxes are the PPE simulation. So far, I only have simulation with up to 8 degrees C uniform global warming. And you see large uncertainty in the parameter space in terms of the state dependence. And here I'm showing the global mean. If you are interested in the cloud feedback over different regimes and the parameter sensitivity, please come to my poster on Tuesday. Next, please. So we are also working on this transient simulation of the Holocene. So simulating the climate evolution since the 9,000 years ago. So we use coupled CESM2 and CESM. So we have two-way ice sheet climate interaction. This is one of the novelty of the simulation. So hopefully we can combine the simulation with proxy data to study the evolution of mean state climate and the variability, as well as the climate ice sheet interaction. There are several interesting scientific questions we can look into. Here, I only talk about one example, the Holocene temperature conundrum. That's the plot on the right. So blue curve is a transient simulation of the Holocene in CCSM3. You see that the model suggests a gradual warming towards the late Holocene. However, if you look at the black, that's the data, which shows a gradual cooling starting from the early to mid Holocene. So this model data discrepancy has been termed the Holocene temperature conundrum, and this is important. So if the proxy data is correct, this implies that the model are wrong in their sensitivity, greenhouse gas, and orbital forcing. On the other hand, if the models are correct, this implies that the data are biased either in their spatial coverage or temporal sampling. So we can revisit this problem using the new CESM2 transient simulation. And right now, we only have 500 years. You see the red curve there. So it's too short to see interesting results. So stay tuned for that, for the new results. Next, please. We are also working on this past 1000 simulation. This is again a cross-institution collaboration. The novelty is that we use the CESM tool Welcome 6MA, so with this high top atmosphere and atmospheric chemistry. So for the past 1000 years, we are more interested in the response to volcanic eruptions and the natural climate variability. The plot on the right shows the global mean temperature anomaly centered around 1000 year to 1100. Let's start from the blue curve. That's the temperature evolution in CESM.
You have about 1 minute, Jean.
Okay, last millennial simulation, and the black is the proxy, is the recent data synthesis. Red is our new CESM2 simulation. You see that there's two interesting differences. Firstly, the sensitivity to volcanic eruption is much stronger in CESM2. And secondly, now we no longer have this little ice age cooling. So we need further sensitivity simulations and analysis to figure out the difference. Next, please. So we are also working on this ASD project to perform an unprecedented high set of high resolution paleoclimate simulation to complement with the IHESP simulation. Hopefully leveraging the paleoclimate data, we can study the weather and the water extremes across the Earth's history. Next, please. Besides the science projects, we are also working on better engaging the community. So we started the Paleoclimate Advances webinar series. So far, we have organized 3 webinars. The first one on temperature, second one on CO2 reconstruction. The third one is on climate sensitivity. Please go to the website if you are interested, and stay tuned for the fourth one in July. Next, please. Okay, I want to welcome everyone to our oral presentation on Wednesday. And we have 13 exciting talks. And please come to my poster if you are interested. Thank you for your attention.
Thank you very much, Jean. So we'll move on to Software Engineering Working Group, and Bill Sachs will be presenting. Bill, please go ahead.
All right, thanks. So I'll be presenting on behalf of the Software Engineering Working Group, the external co-chair of which is Ligia Bernardet at NOAA. And the work I'm going to be talking about, though, has contributions from very, very many people, software engineers and scientists throughout the CESM community. Next slide, please. This slide shows the schematic of the hub and spoke architecture of CESM, highlighting at a high level many of the changes that have been going on recently. You've heard about a lot of these, but I'll kind of summarize many of them here. First off, we've replaced CESM's driver mediator, which is also known as the coupler at the center of this figure, with the new community mediator for Earth prediction systems, or CMEPS. This is based on the National Unified Operational Prediction Capability, or NUOPSI layer of the Earth System Modeling Framework. An important feature of CESM has long been the ability to replace active components with data models. This supports hierarchical model development, along with scientific applications focused on particular parts of the Earth system rather than the full coupled system. So we've also replaced these with a new set of data models, the Community Data Models for Earth Prediction Systems, or CDEPS. These are also based on the Earth System Modeling Framework now. Throughout CESM, kind of shown all around this figure, there has been extensive software engineering as well as scientific work to incorporate new or significantly updated components. In fact, for all 7 of the classes of components of CESM, there are either now new components being added or extensive architectural changes to the existing components. So just kind of briefly going around, starting in the lower right and briefly summarizing these. On the ocean side, as you've heard, we have MOM now, MOM 6 as a new ocean component. On the atmosphere side, there's been an expanded support for multiple dynamical cores, as well as major software engineering, major software infrastructure rework that's underway, which includes, as you've heard about, the physics reordering, as well as a broader evolution towards the CEMA framework. On the land side, you heard about the increasing use of FATES, the functionally assembled terrestrial ecosystem simulator subcomponent, as well as many other changes there. There's also underway an integration of a new, of the simple land model as an alternative land component. On the sea ice side, as you've heard about, we now have the option for size 6 has been coupled into CESM alongside the older size 5. On the river component, work is underway to couple in the Mizu route river routing model as a new alternative river model in CESM. On the land ice side, as you've heard in a couple of talks earlier today, there's now support for running multiple ice sheets, typically Greenland and Antarctica in a single simulation, as well as changes towards simulating Antarctica and mountain glaciers. And then on the wave model side, we have a new component coupled in the new majorly changed version, I should say, of the WaveWatch 3 component development version that's synced up with the NOAA, shared with the NOAA repository for that. So there's been just extensive work kind of across the system to integrate new or vastly updated components on all of these fronts. Next slide, please. In terms of the directory and repository layout of CESM, one change you might notice if you look through the code is that we now have a number of new infrastructure repositories that have been split out from the single CESM repository. Now the CESM repository mainly just contains the Python-based case control system, which consists of extensive infrastructure to support setting up, building, and running a case. This case control system is jointly developed and used by both CESM and E3SM. We've now split off from that Fortran code and CESM specific configuration data. Those have been moved to their own dedicated repositories so that we have multiple repositories with kind of more cohesive purposes. And this is thanks to work by Chris Fisher and others to do this, this rework. Next slide, please. So one of the huge kind of undertakings of the last few years of the Software Engineering Working Group has been this migration of the coupling infrastructure, the driver mediator, from the older model coupling toolkit or MCT to this ESMF-based CMAPS and CDEPS infrastructure. And there will be more details on this presented by Mariana Vertenstein at the Software Engineering Working Group session Wednesday morning. In the latest CESM development code, CMAPS and CDEPS are now the default coupling infrastructure and data models for CESM. To get to this point, extensive validation was done, including multi-sensory simulations comparing the old and new and validating this new coupling infrastructure. The MCT-based infrastructure will soon be deprecated and no longer supported in the development code. However, that will still be supported as the one and only coupling infrastructure in the CESM 2.1 release code for as long as that is supported. There have been a number of updates to the CMAPS coupling over the last few years, just a few highlights of that over the last year. A few highlights of that are that the atmosphere ocean flux calculation can now be done on the exchange grid. That is the intersection of the atmosphere and ocean grids. And this is really scientifically the best way to do this flux calculation. So that's an exciting new change. There's also been an added exchange of enthalpy fluxes, which is needed for energy conservation with MOM. As you've heard about, there's now support for multiple ice sheets, which required extensive updates in CMAPS. As well as the ability to couple multiple ocean layers with ice sheets. On the data model side, in the last year, the CDEP's data model functionality has now been extended to be extensively used in multiple components, such as for nitrogen deposition read by CAM. Next slide, please. This migration to CMAPs and CDEPs provides quite a few benefits to CESM. A big one is the joint development of this infrastructure by NCAR and NOAA. This joint development has enabled sharing a lot of code between these two organizations, and this sharing has allowed testing the coupling and data models in multiple modeling systems, which has really significantly led to a much more robust code base, as well as features that one group adds being available to the others, such as is the case in CDEP's data streams. A huge advantage of using the Earth System Modeling Framework is that it provides the capability for generating the mapping weights between different component model grids at runtime, rather than having to do that as an initial pre-processing step. This means that we now only need 4 pre-generated mapping files for a given configuration, rather than the original 25. All that's needed now is those for the custom runoff mapping. In addition, we no longer need to specify ahead of time domain files that specify the land and ocean fraction. Again, those are computed at runtime now using the Earth System Modeling Framework. This new infrastructure also provides the ability to transfer 3D fields and bundles of related fields as a single packaged field, which simplifies the coupling interface and is more efficient. And CDEPs, the data model infrastructure, provides the ability to do 3D mapping from input streams, and as well as providing many new mapping types. Next slide, please. Since ESMF, the Earth System Modeling Framework, now provides more of the underlying infrastructure for CESM, advances in ESMF can often directly benefit CESM. There are a number of recent ESMF updates that are either already being used in CESM or could be used in the near future. This just goes over a few highlights. On the regridding and mesh representation side, all regridding methods are now supported on exchange grids as of recently in ESMF. There's also been progress towards adopting the mesh-oriented database, or MOAB library, for the internal mesh representation. And there's been updates to what's known as the creep fill extrapolation method. For the NUOPSI coupling layer, there's a new flexible NUOPSI alarm specification, which allows model phases like the writing of restart files to be executed less frequently. There's also new options for detailed performance profiling of NUOPSI components. There's also, ESMF has also updated its version of the parallel IO library that's used internally to version 2, and there's been a variety of performance optimizations. Next slide, please. One of the major performance enhancements enabled by some of these ESMF changes, and also worked on extensively by Jim Edwards at NCAR, is a new ESMF feature that allows improved threading control. Previously, if OpenMP-based threading was used, all components needed to use the same number of threads. But now with this new feature, each component's thread count can be controlled separately. This allows for finer grained control of load balancing between components and improved scalability, because some components perform better with threading, whereas others perform better without threading. And that can be enabled with a new XML variable. That's fine. You can go on. Thanks. Next slide, please. There's also been a lot of work towards supporting an ultra high resolution version of CESM. The current target is a 3.75 kilometer global CAM configuration. So far, we've successfully run a 7.5 kilometer F2000 case, that is a coupled atmosphere land case. To get to this point, we needed to resolve a number of memory bottlenecks throughout the system. And a number of people are currently working through additional challenges exposed with this very high resolution case. At the same time, groups are working on a similar configuration coupled to MOM, so fully coupled configuration at high resolution, along with the Texas Advanced Computing Center. Next slide, please. Work is also continuing on the Atmosphere's Common Community Physics Package, or CCPP, which is jointly developed and used by various host models across NCAR and NOAA. This slide shows an example use of the CCPP physics and framework within NOAA's Unified Forecast System. The CCPP physics is a library of physical parameterization, shown in the gray box at the bottom, with multiple parameterizations of each type. The CCPP framework then is the infrastructure that connects the physics with the host model. and it's used to auto-generate physics caps that the host model calls. As this figure shows, the Unified Forecast System also leverages the ESMF-based CMAPS mediator and CDEPS data models, which are also jointly being developed and used by NCAR and NOAA. And there will be more details on CCPP updates Wednesday morning by Dom Heinzeller. Next slide, please. There has been continued work also to facilitate running CESM on the cloud and via containers. We've made updates to our cloud and container infrastructure, enabling us to now launch Jupyter Hub deployments on the cloud on demand. We're also working now on standardizing Python Conda environments across diagnostics packages and systems, as well as doing now some production science runs on AWS nodes. Another big enhancement that's been made recently is that we can now sync accounts via an email address, which has helped hugely with using this cloud-based infrastructure for community training. On the container side, most of the recent work has been focused on the Ctsm lab variant, but soon there will be regular builds of CESM 2.3 development tags as well. And for more details on this, Brian Dobbins will be giving a talk Wednesday morning. Next slide, please. There's also a variety of work underway whose primary goal is to support running CESM in simpler model or idealized configurations, but a lot of this work should also be useful for running the fully coupled CESM with custom grids and configurations. One exciting new piece of this is a new graphical user interface that guides users through the process of creating CESM cases, particularly choosing appropriate comp sets and grids. Together with this, there's been an expansion of some new metadata, as well as a logic module that check compatibility of comp set options and grids. There's also been a development of new land model tools to facilitate creating surface data sets for custom grids and configurations, including idealized configurations. And this work is being led by Alper Altuntas and Sam Levis and others. Next slide, please.
I think that's it.
Oh, okay. Well, that'll make it shorter. Yeah, the last couple are missing. Let me say briefly. There's I think there's a missing slide there. Two missing slides. There's been a lot of work on lossy compression throughout where the goal is to use lossy compression to reduce CESM storage without negatively impacting science results. This is really important given the limitation of storage resources. Because of the diversity of model outputs across CESM, a one-size-fits-all approach isn't optimal. So evaluations are underway to predict optimal approaches for the lossy compression. And there will be 2 talks on this topic at the Software Engineering Working Group session Wednesday morning by Allison Baker and Alex Pinard. And then last but not least, there's been extensive work to develop new diagnostics packages for many of the CESM components. The Atmosphere Diagnostics Framework, or ADF, can now replicate most of the core features of the old AMWG diagnostics. Jesse Nussbaumer will be presenting details on this Wednesday morning. There's also been work on integrating the climate variability diagnostics package into the atmospheric diagnostics framework, as well as work on the ocean model, a new ocean model diagnostics package, and new development of a land ice diagnostics package.
Thank you, Bill.
Thank you.
And sorry about the missing slides. You already had, well, anyway, that's fine.
That's all right.
So we'll move on to Climate Variability and Change Working Group, and Isla Simpson will be providing the update. Isla, please go ahead.
Okay, thanks. So I'll provide the update for the CVCWG on behalf of my fellow co-chairs, Aishu Hu and Sarah Larson, and the liaisons, Adam Phillips and Gary Strand. And there are a number of other people who've played an important role in the things that you'll see here that I'll mention as we go along. So next slide. So here's an outline. I'll just give a quick reminder of the existing CSM2 simulations that have been around for some time now, but in case there's any new people or in case you're not aware of what's available, I'll give a quick run through of that. Then I'll talk about some of the newly available simulations or almost available simulations coming soon. And then the simulations that we'll be producing in the next kind of few months with the remaining allocation for this period. And then I'll finish up with a reminder of some of the resources. So next slide. So here's just a quick list of the existing CSM2 simulations that have been produced by the working group. You can see the website there and you can find the information on these at that location. So there's a series of pre-industrial controls The fully coupled simulation, which was the one that was run for CMIP6, was extended out to 2000 years. And then there's a pre-industrial control with prescribed climatological SSTs taken from that coupled run. And then there's another one with prescribed time-varying sea surface temperatures also taken from the coupled run. So there'll be a fourth one coming soon, which I'll get to in a minute, but this series at the moment can allow for exploration of the role of sea surface temperature variability and ocean atmosphere coupling and climate variability. There's a 10-member TOGA ensemble, which has prescribed observation-based time-varying sea surface temperatures in the tropics and climatological SSTs elsewhere. And then there's a similar 10-member GOGA ensemble with observed SSTs prescribed globally. And one aspect that's new here is that we've been extending this out. It now goes to the end of 2021. So if you're interested in, for example, the recent La Niñas and their role in the Southwest drought, that can now be explored out to the end of 2021. There's the CSM2 Tropical Pacific Pacemakers, which are coupled simulations, but with sea surface temperature anomalies in the tropical Pacific nudged towards observations. And then there's the SSP 245 ensemble, which is a kind of a medium ensemble, a 16-member ensemble of simulations run with SSP 245 forcing, and that was run with the smoothed biomass burning emissions that were discussed in the context of the large ensemble. Next slide. So now we're on to the newer simulations that have been produced recently. So as was mentioned by Julio in the AMWG talk, CAM is moving towards a new vertical grid. And what you see on the left there are in the blue and the red are the new CAM vertical grids, and then in the gray and the black are the older ones. And so you've got the grid spacing on the x-axis and the pressure or height within the model on the y-axis. And the Climate Variability and Change Working Group has run some simulations with the red grid on the right panel there, which is using the same resolution as the new grid in the free troposphere and stratosphere and the new model lid height. But the difference is what's circled there, which is we're not using the new boundary layer resolution. So when you start to mess with the boundary layer, you need to start to retune all the physics. And so the motivation for doing this is kind of a bit more of a clean comparison to see what are the impacts of this new grid on climate variability. So next slide. So at the moment, there are two pre-industrial control simulations that are of 100 years length. One with SC Wacom physics and one with CAM6 physics. And there's some small differences between those in how, for example, greenhouse gases are treated and what the upper boundary conditions are. And so the panel there in the middle shows that this new grid has a representation of the quasi-biennial oscillation. It also has a better representation of the polar vortices. So this will allow for some exploration of the role of the stratosphere in climate variability. And so this is currently an unsupported and an undocumented version of the model, but the data is available, but use it with care. And we're hoping to document this kind of process toward enhanced vertical resolution at some point soon. Next slide. Okay, so Gokhan mentioned this earlier. This is a big project that has been done over the last couple of years. The work has largely been done by Nan Rosenblum. So this is the single forcing large ensemble, and it's going to be complementary to the second 50 members of the CSM2 large ensemble in that it's using those smoothed biomass burning emissions. The ensemble here has all the forcings fixed except for individual ones that are or combinations of forcings that are of interest. So there's going to be 4 sub-ensembles of 15 members each that run from 1850 to 2050, a greenhouse gas ensemble, an anthropogenic aerosol ensemble, a biomass burning ensemble, and then an everything else ensemble, which includes all of the other forcings other than the ones that are in the first 3 there. And so I'd hope that we would have the paper before this meeting, but it's not quite there yet, so I apologize for that. But as soon as it's done, we'll be releasing the data, and hopefully that will be done in July. Now on the right there, you see in the black is the global mean temperature change in the overall large ensemble. And then the colors show the individual forcings, and the purple is showing the sum of forcings. So the solid purple is the sum of the greenhouse gas and the aerosols by themselves. And then the dash purple is the sum of all of the forcings. And as Gokhan mentioned this morning, the sum of the individual parts don't add up to the whole. So if you go to the next slide. So this is a little closer look at the role of the greenhouse gases and the aerosols in the overall forcing. So on the left is the CSM1 single forcing large ensemble. And there you see that the greenhouse gases and the aerosols in the purple kind of added up to the overall global mean temperature change. On the right is the CSM2 results, and there you see that they fall quite a bit short of the overall temperature change. So that's a difference. And so it either implies that there's some dependency on the model version or on the forcings or on the method that was used. And so in red there is a description of the method, and it's pretty different between CSM1 and CSM2. So in CSM1, an all but one approach was used where all of the forcings evolved in time except the one that was of interest, and that was kept fixed at 1920s values. And then in CSM2, like I described, we use the only approach where only the forcing of interest is evolving in time. So if you go to the next slide. So it turns out that a big part of this difference between CSM1 and CSM2 can be explained by the behavior of the aerosol force temperature response. So in maroon there, you see the CSM2 response, and in teal, you see the CSM1 response to the aerosols. And so we have explored a bit. Nana's run some other simulations doing the kind of inverse method for each of them. So if you go to the next slide, in the dashed here, you're seeing the CSM2 aerosol response using the all but one method like was used in CSM1. And you can see that that brings the overall aerosol force temperature change to something that's closer to what we saw in CSM1. And it has a big difference from what we see in the solid maroon, which indicates there's some method dependence there in CSM2 in how we do a single forcing simulation. If you go to the next slide, now here in the solid teal is CSM1 run in the same way as CSM2. And there is a difference there that's significant, as you can see from the solid line, teal line lying outside of the teal shading. But it's not nearly as large as the dependency that we see in CSM2. So we've been trying to understand this and explore the reasons why, and that's partly why the description paper has taken some time. Nana is expanding on the kind of maroon dashed line set of simulations, and we'll be making those available as well. So next slide. So now we're on to the forthcoming simulation. So hopefully any day now we're going to start this one, which is a regionally refined 1/8 degree North Atlantic AMIP simulation. So this is using the grid on the right that's been designed by Rob England-Wills and Adam Harrington. This is using the 1 degree model, but regionally refined down to 1/8 degree in the North Atlantic region. It's going to run from the 1950s to the present day with prescribed daily sea surface temperatures and sea ice that are taken from the 1/10 degree high resolution forced ocean and sea ice simulation from IHESP. And so the primary science goals here are that we want to explore ocean atmosphere coupling at high resolution in a long kind of climate length simulation. In particular, see does this improve the representation of low frequency North Atlantic jet stream variability, and explore whether there's any evidence for stronger eddy mean flow feedbacks at high resolution, as has been argued in the context of the signal to noise paradox that Steve mentioned in his award talk earlier today. But hopefully there'll be lots of other things that people will want to look at in this high resolution simulation. Next slide. Okay, another simulation that will be coming soon. It's being started now. This has been led by Young-Oh Kwan and Ivan Lima at Hui, together with Gokhan and others that have contributed to this. So this is the pencil model, which is shown in the kind of second schematic there, which lies somewhere between a slab ocean and a full 3D ocean. So it does not have a representation of the large scale ocean dynamics. It's basically a single column ocean model at each grid point. But what that means is that it allows for a representation of the mixed layer physics and prognostic mixed layer depths and mixing and things. So this is going to be kind of a new pre-industrial control that will be produced, and it will probably run for about 1,000 years. There were some issues that Young-Oh and Ivan and others have been working hard to stabilize this configuration, but it seems like it's probably there now. And so this long simulation is going to start. And so you can kind of think of this pencil model as being somewhere between our kind of prescribed sea surface temperatures pre-industrial control with with, and then the fully coupled run. So it's kind of like a slab ocean, but much more fancy. And one other thing to mention is that Sarah Larson, the other co-chair for the working group, they've been working not with CVC resources, but with their large allocation on this mechanically decoupled CESM, where the ocean doesn't see the surface wind stress variability. And Sarah will probably talk about that in more detail at the winter working group meeting. Next slide. Okay, one of the final big projects to be done in the allocation before it runs out is a stochastic physics pre-industrial control. This is being led by Judith Berner. And so she's implementing the SPPT scheme, which is a stochastic physics scheme that perturbs the tendencies for winds and temperature and humidity with some random patterns. And there's some evidence that you see from the power spectrum there on the right of ENSO that having this stochastic physics parameterization leads to an improvement. So kind of a long and tuned pre-industrial control with stochastic physics will allow for some more detailed exploration of its influence. So next slide. So here's just a kind of summary slide. So a reminder of the website, please go there to check out these new simulations. Also, Adam Phillips has been developing the climate variability diagnostics package for large ensembles, and you see the website there for both the original CVDP and the one for large ensembles. There's the website there for the climate data guide, and Dave Schneider is developing a new website, which will be coming soon, and I expect he'll tell us about that in future working group meetings. There's some contact details there for everyone, and please join us on Wednesday for our session. And we definitely want some input on future simulations for the working group to do with the next allocation round. And the link for a Google Doc to gather ideas is there on the slide. So thanks for your time, and that's it.
Thank you very much, Ayla. And final report will be from the Earth System Prediction Working Group, and Steve Yeager will be providing the update. Please go ahead, Steve.
Yeah, thanks, Gokhan. I'm presenting on behalf of fellow co-chairs Yaga Richter and Kathy Béchon from George Mason University. Next slide, please. So we're still a relatively new working group. We were established roughly 2 years ago. So I think it's worth giving our pitch again. We're still building our membership in this working group. The overall goal is to advance fundamental understanding of Earth system predictability on timescales ranging from subseasonal to decadal. And the objectives are to plan and execute large ensemble initialized hindcast forecast sets with and for the community, to serve and promote a collaborative multidisciplinary research hub on Earth system prediction, and to develop tools and frameworks to enable Earth system prediction research. Next slide, please. So one of the main thrusts of this working group is to facilitate the development, execution, analysis, and distribution of initialized prediction data sets that cover different timescales, ranging from subseasonal to seasonal, seasonal to interannual, and seasonal to decadal. These are really the three timescales that we're targeting at this point. And each of these prediction systems exploits different sources of memory in the climate system. And so their experimental design changes as a result of that. The S2S hindcasts are initialized weekly. S2I, like SMILE, is initialized several times a year, in our case, 4 times a year. And decadal predictions are generally initialized once per year, and that's to make most efficient use of compute resources for targeting the timescale of interest. Next, please. So our key accomplishments over the past year is basically the production of 2 key hindcast data sets using CESM2 model. The subseasonal and seasonal reforecast sets use 2 different versions of the atmosphere, CAM6 and WACM6. These have been completed, and the data sets released and an overview paper published. The S2S system has also been used for weekly real-time S2S forecasts that have been contributed to NOAA's weeks 3-4 outlook. Those simulations are ongoing and are presumably available as part of the data release after some latency. A big accomplishment was completing the seasonal to multi-year large ensemble, or SMILE project, which you've heard about. We released the data at our winter working group meeting, and an overview paper on that is available. It's still in revision. Some other accomplishments were initiating SMILE extensions. So we're working towards a seamless prediction system, and we're taking the SMILE initialization and experimental framework and extending the November starts to decadal timescale. So we'll have a seamless interannual to decadal hindcast set once we complete that. At this point, the decadal prediction extensions go back, I think, to 1970, and so we still need to extend those further back in time to facilitate analysis of scale on decadal timescales. Another project that's been ongoing in collaboration with colleagues at Scripps is a replication of the SMILE experiment using high-top cam, and those experiments are ongoing. Finally, we began work on an ESP diagnostics package, and I'll touch on that in a later slide. The S2S hindcast sets with CAM6 and WACM6, as I mentioned, are released. Here's the documentation paper led by Yaga in Mountain Weather and Forecasting. This documents these systems, and for more details on accessing the data, you can visit our new working group webpage, which is listed there. These are 45-day long reforecasts, again, initialized weekly. Here's a result from Yaga's paper. It compares the skill of the WACM6 and CAM6 S2S system with some other prominent S2S systems, ECMWF and CFS. Those are the gray and black lines here. You can see that the subseasonal prediction skill of CSM2 is comparable to NOAA's CFS system, a little bit lower, excuse me, than that of ECMWF. Somewhat surprising result is that the change in atmosphere did not result in much difference in skill. You can see that by comparing the blue bar to the pink bar here. These generate roughly commensurate skill scores for DJF global land. And again, real-time forecasts are continuing with the low top system. Next slide. So Yaga has been building off of this S2S system to explore sources of predictability. So these are some new perturbed initialization experiments that will eventually be distributed by the working group. These include rerunning the full set of S2S hindcasts with a climatological atmosphere, initial condition, climatological ocean, etc. And the interesting result that's coming out of this work is a change in the accepted cartoon of sources of predictability as a function of time. You can see that it's generally been assumed that the atmosphere is the primary source of predictability for forecasts less than a week duration. Then the land takes over and then hands the baton to the ocean at timescales longer than a month. And what Yaga is finding in this new set of experiments is that, in fact, the land is explaining the prediction skill at the shortest timescales, and then the atmosphere takes over, and the ocean really contributes very little to skill on S2S timescales. There's very little difference between initializing the ocean or simply using a climatological ocean initial condition. So this is a study that is in preparation and will be coming out sometime later this year. There's been several references so far to the SMILE data set. This is targeting seasonal to interannual timescales, which is a a heretofore poorly explored timescale in initialized prediction world. We're using CSM2 model with all of the components shown there, and POP2 is using the Marble biogeochemistry library. So we've got prognostic ocean biogeochemistry in this experiment. This is all at 1 degree horizontal resolution. The simulations are initialized 4 times per year, November, February, May, and August, and are integrated forward for 24 months. And the hindcast set spans the period 1970 to 2019. So this was an experiment that was set up in close collaboration with the other component model working groups. It uses a 20-member ensemble, so I think it's safe to say it's one of the first systems targeting these timescales that span such a long time window and uses such a large ensemble. Next slide, please. So here's some preliminary results from SMILE. These are results that are included in the overview paper that should be coming out later in the summer. This postage stamp plot shows the detrended surface temperature correlation skill from each of the SMILE start dates. Those are the columns. And then on the far right column is a comparison to the DPLE November initialized hindcasts. The rows show the forecast lead time along with the target forecast season. So the bottom row shows a 19-month lead forecast for the 3-month season shown. And what this plot shows is that, as expected, we have fairly high skill over the ocean, particularly in the Nino region at short lead times. This is our ENSO prediction skill. And that skill is significantly reduced when we get into year 2 of the forecast. So lead months 13 through 19 here. But what's interesting is that there are still some regions of interesting potential skill, even at 19-month lead times. The skill is low, but we've seen in previous systems like DPLE that this low skill hints at processes that are reflecting predictable internal variability, and that skill can potentially be enhanced either through ensemble size augmentation or model development. So this result lays a foundation for future sensitivity experiments that can explore changes that might change the skill. Another interesting thing to point out is that if you have good eyes, you can see that the SMILE November experiments show some slight skill improvements over DPLE November. So this reflects changes both in model structure, the move from CESM 1.1 to CESM 2, as well as differences in initialization methodology. But it is at least promising to see that we are increasing skill as we develop the system with each iteration. Next slide. Here's some other quantities that will be of interest on these timescales. On the right are plots of Nino 3-4 correlation skill as a function of initialization time. And on the bottom shows the all initialization average. If you compare the blue lines to the red line, the blue line is the SMILE system over this short window from 1982 to 2016. That can be directly compared to the NMME multi-model skill that span that time period. And what you can see is that SMILE compares quite well to NMME. In some cases, it beats NMME and beats all of the systems that contributed to NMME, and that can be seen in the February initialized forecast on the top. Overall, though, the system looks like it is comparable to existing systems, including ECMWF-CES5, which is encouraging. And on the left-hand side here, you can see the NAO correlation skill. This is a station-based NAO. and it's shown as a function of lead month as well as target season. And the main takeaway here is that our NAO correlation skill is negligible in SMILE, and that's quite different from some systems like the UK Met Office Depressus 3 system, which is shown in green there, thank you, that several prominent publications have come out touting their high skill, although it's still unclear what particular system design choices led to that skill. So we clearly have work to do to improve NAO prediction skill in SMILE. Next slide. I wanted to show one non-traditional result. In SMILE, we are initializing the land model from a land-only simulation forced with atmospheric reanalysis. This is something that we didn't do in DPLE. So now we can look at the prediction skill of land fields. And what's shown here is a terrestrial water storage skill. Upper left shows the skill at lead month 19 for boreal summer. And what you see is a patch of relatively high skill in the US Southwest. The time series are shown on the upper right. There's clearly large low frequency variability in the land-only simulation that we're initializing from. And SMILE, therefore, has some significant predictability just associated with the persistence of that low frequency initialization anomaly. But if we compare SMILE skill score to persistence on the bottom left, it outperforms persistence out into year 2. And so there's some skillful prediction of the actual drivers of terrestrial water storage that allow SMILE to beat persistence in the US Southwest. Next slide. One thing to mention is that to facilitate community use of these data sets, it's important that we develop and share diagnostics for efficient interactive analysis of these very large initialized prediction ensembles. And so we've got work in progress now that's being led by Tegan King. She's cleaned up and packaged some of the notebooks that we used for the SMILE overview paper into an ESP lab package that will facilitate data ingestion and skill verification for data sets sitting on GLADE. And that will include both the SMILE and the DPLE data sets. And also check out Judith Brunner's talk in the working group session for an example of other diagnostic packages that are being developed. Next slide.
You have 1 minute, Steve.
Okay. You can go ahead, Gokhan. Yeah, I just wanted to give everyone a brief glimpse of the interesting lineup of talks that we have for the Thursday morning session. I also wanted to note that we plan to have a robust discussion on potential future experiments to do with next year's working group allocation. So please come join us and share your ideas on what we should be doing that would help facilitate your work, or that would be a way that potentially you could contribute to this working group. The final slide. Yeah, we're looking for more involvement, more people to join to help in analysis of existing data sets, helping us to plan and set up new experiments and contribute to this growing diagnostic tool package that we're trying to develop. Email Yaga, myself, or Kathy if you have questions, and please check out the ESP Working Group website for more information on available data sets. Thank you.
Thank you very much, Steve. And I just found also missing slides for Bill Sachs. Bill, are you still there? There was one on lossy compression, as he covered, and the last one was on new diagnostic packages. So we will reorder the slides and make sure that they're in the proper order when they're available on the website. Okay, so this concludes today's sessions, and we will convene at 8:30 tomorrow. We will have atmospheric model working group, land model working group, and ocean model working group sessions, and their agendas are available on the CESM website. And then in the afternoon, we have the cross-working group #1 session on justice and climate change. And that's organized by Monica Morrison and Jean-Francois Lamarck. And you will be receiving connection information for tomorrow later today. And with that, I would like to thank everybody for their participation and for their interest in CESM. And I hope it was a useful day for everybody. And we'll see you tomorrow. Thank you very much. Have a good evening.